Everybody, good morning to our French delegates and good afternoon to our Indian delegates. And today is a very special day. We have two distinguished keynote speakers. One is Professor Francesca Primas and Professor Jocelyn Bell Brunel joining us. And, and of course, we have in this session 6 speakers, two keynote, and we also have 2 poster presentations. So without much delay, I think I will request Ishwar to uh, to start his presentation. And before that, just to say a couple of words about Professor Ishwar Reddy. Ishwar Reddy is a faculty in our Indian Institute of Astrophysics, Bangalore, and his main efforts are shouldering the India TMT efforts as in capacity as director. And Ishwar, without much delay, the stage is yours.
Thank you, Pandey. Thank you very much. And thank you for the organizers for setting up this wonderful series of meetings, 5 days long. And the much of the credit goes to Mamata and to Marietta. Thank you very much for having me and using this talk. So what I have seen here is lithium in stars. I'm just going to go. It's not our own work, but then it comprises most of our group's work, and with some key aspects from others as well. So you can see lithium stars, the background stars, and then lithium is there. And lithium is one of the lightest elements which can float in water, which you can see in the right corner. So why do we study lithium in stars? What is that interest in it? Because there are so many papers on a single element. One is it has a cosmological origin. And in that, Big Bang nucleosynthesis predicts lithium along with hydrogen and helium. And you don't have its counterpart measured in observations any of the objects yet. And there is still a gap between that prediction and measured observations. That's one of the things people like to solve it and validate Big Bang nucleosynthesis, a kind of. So another thing is in the more benign aspect of it is also very key. Lithium is a prozide element and which gets destroyed at relatively low temperatures, which are easily attainable in stellar interiors. You can see a couple of million degrees it gets destroyed. So its presence and amount of level of its presence, that is amount of lithium present in those stars, can really aid, is a good tracer of standard and non-standard mixing in stars. And in many places, people use actually the age indicator for the stars as well, particularly in pre-main sequence stars. So, so that's the key aspects of it. That's why lithium is quite interested. In other day-to-day life, also the lithium is quite interesting, apart from the batteries and then cell phones and things like that. And the lithium is also used in lithium carbonates, things like that, to treat mental illness, though its biological mechanism is not understood. It's true, actually. There's an empirical evidence for it. It seems there was a survey in 1990s, over a 10-year period. They found the place in the communities where the water level, when lithium is higher, and then the criminal activity is much lower in those places. And then they suggested that adding some amount of lithium into drinking water is a great beneficial effect to elevate people's mood and lowering suicide rates. And this is one of the things I just taken from Kawanaga et al. 2018, and which was commissioned paper by European Union for lithium as a strategic element for Europe. So this is a very big document, so I just took some of that. Okay, so now we'll go to our star business. This is what is the cosmic lithium. It's a Big Bang lithium production cycle, you can see. And the BBN happened during the radiation-dominated era. And you can see all these protons and neutrons getting into fusion, and then you produce these elements in the beginning. For example, we can see 3He is the one of the main 3He and 4He elements, which gets into 7 beryllium, and then 7 beryllium goes into the lithium. So based on these nuclear reaction rates, they made a predictions using a parameter, because that is a radiation dominated era. People wanted to know. There is a input parameter in the BBN, which is a free parameter till recently. That is a baryonic baryon to photon ratios. So now you can see this prediction of these 4 elements like helium, deuterium, and 3He and 7 lithium. They have a huge range. Okay, these are theoretical models. Then you got a CBMB experiments like WMAP and Planck, which measured eta, and then that puts a constraint on various. To put a constraint on these abundances. So what is the observed values? For example, the helium measured in various high G clouds and things like that. And then you can see that matches very well with the predictions. And also the deuterium is quite well constrained observationally. Of course, 3He they couldn't measure because there's still an issue there. And 7 lithium, though it can be measured in the spectra of stars, but that is way below the theoretical predictions. And we can see that the down, I can see that, you can see this red one, okay? And look at that. You can see that BBN prediction is, I just converted into that logarithmic ratio where people are familiar in stellar spectroscopic people. So the log lithium is 2.67, which is almost like 4 times larger than the measured lithium abundance in stars, that is in metal poor stars. So that is still unsolved problem, and that's what people are trying. It is a problem with the stars or problems with the BBN. If it is a problem with the BBN, they had to look at, are there any new reaction chains which is contributing to this? Or if it is the problem with the stars, and then some whole lithium is getting slowly destroyed in what are called observed primordial abundance 2.2, which is measured in metal poor kind of hot stars, which I will show you in the next slide. So this is called the observed one. You can see the speed plateau here, which is the one which I said 2.1.3. And then that is the value which is thought to be the primordial value. But then lately, and then people started measuring much more very metal poor stars, and then the lithium is much lower. So probably we don't know whether the observed lithium abundance in those metal poor stars by speed is really reflect the primordial, or it is the reduced from the primordial value over the lifetime of the universe. We don't know. On the other hand, the BBN value is slightly higher. So it doesn't matter whichever the value you take it. Over the years, lithium evolved from the Big Bang nucleus from the beginning. If you take even BBN, and then it's almost 6 times more than the primordial value, the current values. You can see how the lithium is evolving from the BBN, and then the people say the cosmic rays contribute an enormous amount of. Now you added plus stars also. Stars generally thought to be a sinks of the lithium. So, but now the BBN plus, cosmic rays plus, stars plus, you can see that green curve which is going up, and then up. This is the solar system meteoritic things, and then the current present value is slightly above those values, which comes around 3.3, but that is within the error bars. Okay, and then if you take a speed plateau as a primordial value, it's almost like 1 order of increase from the primordial value to the current value. And you can see the galaxy, how the lithium is evolving. You can see the Milky Way halo stars, and then Milky Way disk stars, and it goes up. So the lithium indeed evolved over the years, particularly in the ISM, because these stars are formed from the ISM, and these are all upper envelope consisting of these Milky Way disk stars is basically the young stars, many of those young stars. So So there is a significant enrichment of lithium over time. So where it does, okay, now look at, there's a two post Big Bang. The enrichment causes, one is galactic cosmic rays, which bombard heavier nuclei like oxygen and carbon, and they produce lithium. That is a well-known phenomenon, which is observed. Of course, that then from which stars form, and then that's where the stars have a higher lithium, particularly in younger stars you see, that's what you see. And then, of course, the lithium also gets produced in stars, okay? But then we don't know whether that lithium is really seen in the photospheres and that is really contributing to the IS. That's another issue. And this is a mechanism is called basically the Cameron-Fowler lithium synthesis in stars. That is Cameron-Fowler mechanism, CF mechanism. So our main interest is about stars here. So what happened in the stars, though lithium gets produced in the stars, no doubt about it. But the thing is, one of the major ingredient for lithium production is 3He, that's a primordial soup, which has come from there. And then with the 4He, and then it gets into beryllium. The beryllium reaction happens at much higher temperatures, closer to the hydrogen burning cell, within the hydrogen burning cell. But the problem is the beryllium itself is a bit unstable and then gets into back to 4He and 4He if it stays there. So if it survives, somehow it brought to the slightly cooler temperatures within the star, and then that can convert it into 7-lithium. Then that 7-lithium has to be quickly transported to the photosphere so that it can contribute to ISM through mass loss or for us to see it. Because the lithium destruction happens at a couple of million degrees, so normally you don't see lithium in stars because it gets produced and it gets deleted, destroyed in the star. So this is the theory. This is the way the nuclear reaction rates provide you, and that's exactly the standard models tell us also a lot of theoretical models starting from even 1967. So they produced that initial lithium, which was starting from the main sequence. So the stars, if the star started with the lithium abundance of ISM, currently ISM, stars form from ISM, from the natal clouds, assuming that the lithium from the clouds to the main sequence is not destroyed. So it started with a maximum amount. So what they calculated based on the mass, and the lithium gets destroyed by 30 to 60 times by the time it crosses the first edge of itself. So what they said is the maximum lithium you can see, at least in the red giant branches, not more than 1.8 or 1.5, depending on the mass. And then, of course, they also have other predictions, for example, the mixing predictions from the standard theory. Carbon isotopic ratios, for example, sun has 90 on the main sequence, and then by the time it crosses the first edge up, and then it has 15 to 30. If you look at actual Arcturus, which is a typical K giant, and which has a 12G by 13 is 10, and the lithium abundance is minus 0.6, which is much less. So theory works very well. And indeed, it works well for most of the stars, predominantly. So, for example, I can just show you one of these things from Global Cluster Study by Lind et al. 2019. So you can see the lithium here. I'm showing the left panel where for the main sequence stars, it started with say around 2.3 or 2.3. That is the initial value for that cluster, because lithium can destroy it before it comes to onto the main sequence. So, and then once the stars leave the main sequence and then enter into the first red jump, you can see because of the first red jump. During the first red jump, what happens is now you have a helium core at the center, which is the inert core, and then surrounded by hydrogen burning cell. So within the hydrogen burning cell and then surrounding it, and then you have these PP chain reactions where some of these elements can perform. Okay, for example, CNO reactions, and then carbon to nitrogen, some of these oxygen. Lithium also can be formed from the beryllium, things like that, or it can destroy it because of that. So when you see here the first red jump, what we are seeing is all this is photospheric abundances. So there is a significant reduction in lithium from main sequence value from here 2.5 to the 1.5. Okay, because there the convective envelope reaches much deeper. So then it brings out to the diluted material from the interior, so effectively reducing the lithium amount. Later on, and it's stellar internal structures, and then the envelope recedes, and then for some time, and then lithium doesn't get reduced for a while, and then suddenly it start decreasing it. That is exactly the place where this called luminosity bump happens. Luminosity bump is the one where the stars stay for longer time, and that is the place where, because of the core increase in the center, and then hydrogen burning cell moves outward and gets enclosed into the convective envelope, and which gets more, the protons into that, and then star gets slightly cooler, and then it makes the reverse evolution there for a short period, maybe 10 to 15,000 years. And then that's why you see there small bunch of stars, because of that they stayed longer there. Okay. So basically now what I want to say is both theory and observations predict that lithium gets destroyed in stars. Basically stars are sinks. So, but then what happened? In 1982, there is an outlier. And this is what the Wallerstein and Steeden discovered a star in which lithium was extremely strong. You can see that one down, lithium is extremely strong. And these are normally lithium normal stars. 99% of the stars you should see this one, any giants, okay? But then there are outliers, something like this, and which adds rich to the subject too. And they thought it's a quite unusual, probably this is getting synthesized somewhere in stars. The field not progressed much in the beginning because not availability of large number of high resolution spectra, because you can't get lithium rich stars so easily. If I go to the telescope for 100 days, probably may get one day somewhere. So it added over the years, a couple of them, few more stars. And so then people thought it's maybe because of the various processes, various mechanisms put forward. One is lithium cannot be easily produced. Maybe probably it is just preservation, in the sense the inefficient mixing in these stars, which is basically retain these natal main sequence lithium abundances. So, but that is now disproved because you can see the serious mixing in those stars, because some of these stars towards CP13 is quite low. And also some of these stars, lithium is more than what you see in the ISM values. So that's taken out. And then what about planet and brown dwarf engulfment? That also came into the picture, because when planet discovered, some people thought because Earth-like planet, because Earth has a lot of lithium, and then less amount of hydrogen, because that hydrogen is evaporated at the time of formation. So if you just put large amount of the lithium into the convective envelope, devoid of hydrogen, that increases the lithium in the photosphere. But that requires a large number of the planets to be merged with the atmosphere. So we don't know what, but the theory has got a credence because of the fact that some of these stars also see infrared excess and also have seen certain rotational velocities are higher, because the mergers create infrared excess because of the bombardment. And also the infrared the rotational velocity is basically the induced momentum because of the merge. That was based on not more than 6 stars that time of thing. And then another is nucleosynthesis and mixing, but we don't know which one is which. So another influential paper came from Charbonneau and Balachandran in 2000 in Astronomy and Astrophysics. They took the audit of these lithium-rich stars that time available. You can see there are very few stars which are clustered around luminosity bump. You can see there are 3 or 4 are there super lithium-rich stars. All of them are there. Then some of those lithium-rich stars, which is, so anything is called lithium-rich at the in the literature is greater than 1.5. That's because it came from the theory. So they put all these things on lithium-rich, and then they said probably the lithium is getting produced during the luminosity bump evolution, because that is the one place where hydrogen burning cell is moving upwards. And there is some kind of extra mixing is happening. So somehow it's solved the entire lithium to the photosphere. But of course, it get reduced, and because of longer convection period, that's what they said, something to that effect. So then we got into in 2020 again by accident, and then we discovered one of the lithium-rich giant, which was taken from Pico Dias survey. They were doing T Tauri stars. This was our post-AGP stars, and then which happened to be slightly higher Vicini and also had infrared excess. So we thought these are all because of planetary engulfments or merger of some brown dwarfs, which is happening. So we all thought of. So then we thought of, then what is the external versus in situ? So now two problems came. Is it because external scenarios, planet engulfment or red dwarfs, or internal issues? So what we did was we took a much longer survey here in India. With my student Kumar et al. This was much before the Lamos surveys or Gala surveys. So we chose 2,000 stars, which can be suitable for IAA facilities like Himalayan Chandra telescope and then Vanuatu telescope. So we took some of the stars which are low mass stars because all those stars go through luminosity bump and also the helium flash. So those are the sample, which starts from the red one is the red curve here is the starting of the first red jump. Okay, we took some of these stars, and then you see these red marks on the evolutionary tracks, which represents the luminosity bump for that particular mass star. And then you can see this yellow thing is a what's called red clump region for those stars. And you can see that it's very difficult to distinguish those red clump and some of the evolutionary stages in the RGB itself. So that's another difficulty which will come to the later. So we took quite an amount of spectra, all that for 2,000, good spectra. Kumar did a wonderful job staying with all these observatories for long. And derived abundances using the low resolution spectra. As far as we know, we understand that this was the first time we did using the low resolution, and then we developed techniques how to get reliable abundances with certain uncertainties, maybe 0.3 or 0.4x. So we wanted to only have the stars which are greater than 1.5 because we can't get, because of this low resolution, any less than that because lines get much more weaker in those spectra. We use both calcium line and then lithium line there for various systematic efforts. So what we got is, surprisingly, we got some 13 lithium-rich stars, among which 4 are super lithium-rich stars. That means that lithium abundance is more than the ISM. And then what we found was that increased the sample almost like by double the lithium-rich giants, and then almost tripled the super lithium-rich giants in the literature. And then you can see where the stars are now. They're all in a particular luminosity, the band, okay? And when we plotted all of these stars, which is the known lithium stars in the right panel, you can see the lithium-rich stars peaking at luminosities of 1.5 and 2, which is exactly matches somewhere both the luminosity bump and also the red clump region. Red clump region is the one which is post-helium flash and that means the end of the RGB phase. So what we learned from this is most probably it is not external scenario, planet or brown dwarf engulfment, because if that is the case, you would have seen stars. You don't need to see in the particular luminosity place. You should see either below or above this as well. So looks like it is a internal scenario, and then we don't know where it is happening. Is the luminosity bump or the clump? Now our focus moved to in situ equations. Is the bump or clump? Because it says an issue which has two different mechanisms. So people say extra mixing of the luminosity is the one proposed scenario, Okay, that's the place also because the standard model doesn't predict very, very extremely low values of 12C by 13C and a high nitrogen in RGB stars. So then the extra mixing was invoked over and above the standard models near the luminosity parameter that explained very low values of both lithium, 12C by 13C, and nitrogen. So the suggestions of lithium also get produced there. It is very unlikely. We thought it's a bit paradoxical because that is the place where you reduce the lithium at the same place. In some places, the lithium cannot come out. That's the one reason we want to take up the new survey. Another thing is there must be a single source of lithium rather than multiple sources, as many theories suggested. But then the key constraint to know bumper clump is knowing the precise evolutionary phase of these stars. Because these giants overlap many phases of evolution in luminosity temperature effect. Because these regions are just differed by 50 to 100 degrees in many places and 0.2 to 0.3 dex in luminosity. So distinguishing and separating these stars either way is extremely difficult. That's why there's confusion. And then there was unconstrained, so many theoretical models popped up. So one way of solving this problem is just go to globular clusters and solve the problem, because the globular clusters have well-defined RGB bump. You can see the RGB bump here, and then red clump also you can see. But the problem in those things is you can see in my rightmost diagram, and the background stars are basically the upper limits, because measuring them accurately is extremely difficult, and then getting spectra is also very time-consuming for large number of stars. It's not something like I go to the cluster, you can get some lithium stars because these themselves are rare, and then you may not get them. Because you have a definition greater than 1.5, because people look for that. So, but we don't know that's the limit or not. So we'll come to that later. So this I tried actually a couple of years ago, but then we thought it's not possible to get a meaningful way now. So the another thing is you need to have a large number of stars, field stars themselves, so that you can define these things. And then for which lithium abundance is also derived. Okay, thousands of stars. Okay, so that's another one. So there is another one. We can go for it. Is astroseismology that came into a few years ago. And then what the astroseismology does, it has a characteristic frequency and parameters to see what kind of core in the center of these red giant branch stars. For example, it has a RGB stars, the first time ascending this RGB, and they have a hydrogen burning cell outside, and then there is a helium inert core, and which has a different density structures. And then stars which have passed RGB phase, and then they have a helium burning at the center, that is the one, the red clump stars. And they have a different characteristic parameters, okay? So that parameters are called, one is average period spacing between whatever mixed G modes, which is G mode is mostly associated with central core. We can see that here, y-axis. There are two different ways of measuring delta P and delta pi, both actually are what's called average period spacing. There is a frequency. When you plotted this, what you can see is most of the things in the plots, actually the below are RGB stars. They have very less delta pi compared to red clump stars. Red clump stars are very distinctive delta pi numbers, which ranges anything more than 100 now is called red clump stars. Anything is less than this, probably some stars. You can see these all. So very distinct. This was published in Nature 2011. So, but problem is the Kepler has a limited field, and then none of the known lithium-rich stars or super lithium-rich stars are in that Kepler field when we looked at it. But then when we were looking at Lamo's survey, and then two of them really bright stars also happened to be in the Kepler field. Then we thought, okay, now let us get these parameters from the Kepler astroseismic data and derive these delta P and delta nu for these parameters, and then get these observations. So we did get these observations, our newly installed HESP spectrograph with HCT. And you can see the Lamo spectra on my left side. this is 18,000, 1800 spectra. You can see the lithium line there. And then you can see our right diagram where the lithium line is very strong. We derived these are both are the super lithium stars. And then when you got these delta P and delta nu and plotted, you can see where these two stars are there. They are incomplete in the red clump. I think these are the first really stars measured accurately. Their phase is known from independent method using the astroseismology. Okay, and this is a great new twist to the entire story of lithium-rich giants. Of course, there are now other couple of stars also reported earlier. They're not super lithium-rich stars. So now together there are 4. But is it now signaling something? This is the entire thing is probably because of the helium flash, or something is happening in the red clump, not on the RGB. So then came another study, which is basically large number of stars. When we combed the entire Gala survey, which has a resolution of 28,000 resolution, and that provided a huge number of stars, almost 50,000 stars. Plus, when we plotted this luminosity versus T uptake temperature, you can see there the clump above one. You can see the clump in the box of black box. And then you can see that in the red box, that is a, black box is the clump, and then red box is the luminosity bump. Luminosity bump is the one stars which are going up the RGB. And then the clump is the one which are passed the RGB phase and then went through RGB tip, and they have gone through the helium flash. So this is the key. So what we did was we looked at their lithium abundances, and then it's really surprising. Most of them are indeed lithium-rich giants.
Hi, Ishwar.
Yes,
you have
yes.
Another 5 minutes.
Yeah. So we put a cutoff of 1.8 as a lithium abundance. You can see here my right box, luminosity versus lithium at this point. So many lithiums are popping up, which are all luminosity clump. But we don't know exactly these are real luminosity clump. Probably most of them are luminosity clump based on this, but we don't have the astroseismology for these stars. Okay. So this resulted in a huge number of lithium-rich stars because of the definition. Of course, we discovered some 20 super lithium-rich stars. And then things really now moving towards, away from the RGB to now concentration to the luminosity, red clump region. The red clump region, another major event preceding to the red clump is actually the helium flash. Probably that is one which is created. We want to look at that aspect of it. Then we went to another survey, that is LAMO, that is the Kepler survey itself. Now took all the Kepler stars and then looked at it, all of them common with the LAMOST. And then we found 12,500 giants as common between them because of the lower resolution spectra. And then we confined to only very strong LAMOST lithium line spectral stars. So of which we discovered some 24 super lithium-rich giants, and all of them astroseismically classified as red clump stars. Red clump stars means the post-helium flash, so end of the RGB phase. So that is now we more or less now closing to, we are moved away from the RGB, which doesn't work, and then looks like all the lithium-rich stars are associated with red clump. And then probably with the luminosity, with the helium flash. This is again from our group. This is again very influential paper. And then all of now we took audit of this entire thing. This we published recently in the Nature Astronomy. Large scale systematic investigation among red clump stars itself. And then what it showed was all lithium-rich stars have high levels of lithium for their evolutionary stage, which is almost like a factor of 40 over the end of the red giant branch stage, which is a stark tension between the theory and observations. Here, what we see here is the brightness in the lithium. What you see this curve, this is the best the theoretical curve, which is available now with the standard theory plus extra mixing processes. When you can see very clearly, and the lithium gets reduced, and then luminosity bomb, it gets further reduced, and then as to go to the RGB tip, there is slight increase at the time of the RGB tip. When you come down and the models now predict much less lithium as you go towards RC phase. So by the time stars reach the tip of the RGB, the lithium goes down to almost like a -1 dex. But you see RC stars, which is the horizontal, those magenta stars, they're all higher than that limit from RGB tip. So now we say all low mass stars undergo lithium production phase between the tip of the red giant branch and the RGB tip. That's probably near the helium flash. So we also now came up with a new definition, that definition which is used so far in the literature, that 1.5 doesn't work to classify lithium rich stars, because now the lithium is mostly produced in red clump stars, and then anything which is above the RGB, end of the RGB, can be a lithium rich. So we put an appropriate limit as anything more than -0.9 dex can be a lithium rich among RC stars. So these all prompted quite a number of direct theoretical models which came very recently. And then many of them are on ad hoc. They produced various mixing processes, and then some went into nuclear reactions, and then come up with various issues there. These are the two papers which came very recently explaining this current our results. So summary is, our studies demonstrated giants ascending RGB for the first time only deplete lithium, reaching as low as lithium is equal to -1 dex. Lithium excess phenomena is only associated with the red clump giants of core helium burning phase. Limit of lithium 1.5 dex, now it's more not very appropriate for classifying the lithium rich giants, at least among RC giants. So far now we don't have any lithium rich giants RGB star, and for which classification is available based on the Kepler. Since helium flash is the only major event between the end of the RGB and RC phases, site of lithium production most probably lies during the helium phase. So now there are models suggesting mergers of white dwarfs that can initiate even helium flash itself, that we are now looking at that aspect of it. So, and with my other student, we are looking at early AGB's connections. A lot of early AGB stars also have a lot of lithium. So we are looking at that connection with these helium flash aspect as well. So I think that's what I have. Though I didn't include our recent study, now we have a fairly good idea of where the lithium is coming, and then looks like the helium flash. And then we are also putting it real time constraints on those, and then which is now under review. And then hopefully in a couple of weeks that will be out. So thank you very much for your attention. I'm happy to answer.
Thank you, Ishwar, for very interesting talk and very exciting results. And can we have a couple of questions?
Yeah, sure. Brijesh here. Yeah, thanks for this nice talk. Can you comment on this narrow band photometry to find lithium richness in this your sample, particularly globular clusters? Have these been tried out?
No, we didn't.
Yeah, because considering the large number of stars and also the wide field of global clusters, probably it would be.
You can have a filter at lithium, is it? That can be.
Yeah.
That's very nice to do. Yes, that's the best thing. Yeah, we didn't do that.
Okay. Thank you.
And how is TMT going to help us with these studies in globular clusters?
Yeah, I don't know the TMT, but the MSc certainly is going to do, because we have a multiplexing on MSc, and it can go much further as well. And not only here, but then there are a lot of issues along the way, early AGBs and AGBs. And then particularly we really look at it, their contribution to ISM, which is important to see the level of contribution from the stars to account even the BBN issues. Thank you. Yeah, certainly the TMT also will help in looking at other galaxies, dwarf galaxies, in much more serious way. And particularly, you also need to look at, see, we are looking at very strong line 6707, but of course, you need to also see what happens to 6 lithium and things like that, isotopic ratio or something. But now those are not possible because of this limited resolutions. But of course, thanks to these all large surveys like, Kepler, Lamos, and Gala, which made all the difference. It's a quite significant improvement in the last 2-3 years in this field.
Yes.
And I'm so happy that much of the things came from our group.
Let's thanks again, Ishwar, for a very interesting and lot of exciting results, and looking forward for more on lithium.
Thank you.
Now we move on to our next speaker, Professor Ramprakash. Ramprakash, can you please upload your talk?
Yes, thank you, Andre.
And it's a pleasure to have Ram Prakash with us. Professor Ram Prakash is a faculty with IUCA, and his thrust is mainly on making instruments, and he, along with the Ishwar, is heading the India TMT project in capacity as associate director. So his talk is loaded, and I invite Ram Prakash for his presentation. Ram Prakash, all yours.
Thank you. I hope you can see the screen and hear me well. Thank you. So my talk is basically about WALLUP and PACIFE, two complicated acronyms. So let me start with, of course, this entire talk is on behalf of a very large WALLUP PACIFE collaboration. I will try to tell you what that collaboration is at the end. But right now, the acronyms mean the following. WALLUP stands for Wide Area Linear Optical Polarimeter. It is a very wide field, half a degree by half a degree field of view polarimeter to measure linear polarization in starlight, and to very high measurement accuracy, better than 0.1%, because the targets we are looking at are very low polarization, 0.4%, 0.3%, and so on. And PACIFE stands for a survey we are planning to do with two of these instruments, two of these WALLUP instruments. And PACIFE stands for Polar Areas Stellar Imaging and Polarization High Accuracy Experiment. Please pardon me for this very complicated acronym expansion. We have Greek collaborators, so we need to have a Greek name as an acronym. So we had to figure out how to fit a Greek name into the survey we are trying to do. Okay, so let me try to get on with what we are trying to do. If you need to know more about it, please read Tassis et al. 2018. It's on the archive, and archive reference is given here. We all know that when you look at galaxies in polarization, there's a lot of very impressive polarization we see. There are mainly two causes of polarization. One is either extinction or emission by dust grains which are aligned by some mechanism. They're predominantly aligned by some mechanism. And of course, there is a well-known synchrotron emission from electrons accelerated in the magnetic fields. In both of these mechanisms, the magnetic fields are important. They play a very important role. But in the study which we are going to concentrate on with this instruments, we are mainly focusing on the extinction or emission mechanism of aligned dust grains as our probe of the interstellar medium. Now, to understand how that is, many of you may already know, but let me just have a quick primer here. If you look at the galaxy, there's a lot of magnetic field intertwining the galaxy structure. And if I take a local region where the galactic magnetic fields are in the direction as marked by these green lines, the dust in the interstellar medium, because of various mechanisms, I don't have time to explain those, but let us take it for granted that this dust end up spinning very fast, and this end up, because of the spin and their ferromagnetic nature and the orientation of the magnetic fields, they kind of statistically align themselves in the direction as shown here, where the short axis of the dust is parallel to the magnetic field. Now, if you look at a dust cloud like this, through the dust cloud, it's a star behind the dust cloud, and assuming that the star is emitting unpolarized light, as the light passes through such a dust cloud, the extinction in the short axis direction would be very less compared to the extinction in the long axis direction. So you would end up getting a preferred partially linearly polarized light from the star looking through the cloud. Now, these same dust grains also absorb all kinds of radiation and thermalize them and then re-emit them, predominantly in the millimeter, submillimeter, microwave kind of regime, depending on the temperature. And most of those submillimeter emission is preferentially aligned along the long axis, because that is where the emissivity per unit area, then the area is more. So the submillimeter emission will be more polarized along the long axis. But mind you, it's the same dust grains which produce these two effects. One is the extinction effect, which leads to partial polarization, and the other is the emission effect, which leads to again partial polarization. This is in visible wavelength, typically visible near IR, and this is at longer wavelength like submillimeter and so on, which is emission, and this is thermal. But they are just orthogonal to each other. But that's a trivial fact. Now here is a Planck map of our galaxy, and it's a dust opacity map really. And you can see, as we expect very well, the galactic disk is really dense, a very high opacity. And as you go away from the disk, there are these fantastic structures which extend pretty large distances. And towards the galactic polar regions, you see these areas where there are very little dust. And in Planck collaboration, they fitted a modified black body to this dust. This measurement is at, this particular map is at 545 gigahertz, and then determined the dust temperature to be about 20 Kelvin on an average for the best fit black body. It's a modified black body. I'll come to that in a minute. And then if you look at the dust emission itself, you can see it follows the opacity as expected, and that's what you would expect. The more opaque regions would extinct or emit more, and then the dust polarization will align with those features. And this is at 353 gigahertz. And if you then convert that into magnetic field features, and you can see that magnetic fields are pretty well aligned along the structure of the dust maps or dust emission maps. They are pretty tightly correlated. And this is something which we would be trying to use in what we are trying to do. So what are we trying to do with Wallop and Pacific? To understand that, this is a cartoon of the history of our universe since the time of Big Bang. And for various for explaining various observational features of our universe as we can observe them today, we believe that the birth of the universe was accompanied in the very, very early phase with a phase called inflation, which was a very rapid expansion to many, many orders of magnitude size and very rapidly. And once the inflation suddenly switched off, and then the current epoch of acceleration, the slower accelerated expansion started. And we know that at late times, this expansion is actually accelerating further. Now, this inflation has been forced on us for various reasons of observational, explaining various observational things as of today. There is no direct evidence of it. We have not directly picked why, whether inflation happened or not with a direct observation. One of the predictions of this inflationary period is that the gravitational waves which formed a background during that phase would imprint themselves, their signatures on the cosmic microwave background. And the cosmic microwave background, as you all know, would have decoupled from the matter as the universe expanded and things cooled down. Radiation did not stop seeing the matter, and the path lengths became very large and the radiation became free. And they carried all that information of the gravitational wave background. And one of those signatures is what is called the B-mode polarization in the cosmic microwave background. Now, this is a particular type of polarization, the E-mode polarization, which is mostly caused by scalar perturbations or density perturbations. But the density perturbations do not lead to B-mode polarization. So if B-mode polarization is detected, that is thought to be a direct evidence of inflation, because that's only the gravitational wave background during the inflation is the only source of creating B-mode polarization. Now, there had been attempts to measure this B-mode polarization. People like BICEP2 collaboration for a while believed they detected this a few years ago. Then they joined hands with Planck and did an analysis of the data again. And then they figured out that what they detected was not really the B-mode polarization, but something else. Now, what is that something else? That is the following. This is just a plot of RMS brightness temperature of the sky emissions from various sources as a function of frequency. And if I look at our interesting wavelengths, we will see that the cosmic microwave background and the thermal dust emission are the most dominating factors. So if we do not remove this thermal dust by properly modeling it and taking it out from the total radiation you measure in any direction, you are not going to get down to CMB. This thermal dust is also, as I explained earlier, polarized. And to get down to the B-mode measurement of CMB, you need to get rid of this dust emission very, very accurately. And this was not possible in that time. The reason why we believe they got it wrong is the following. And this is a prediction of at that time made by Tarsis and Pavlidov in this paper. If you look at submillimeter emission in any direction, the emission is coming from potentially multiple dust clouds. Because any sign of sight in the galaxy will have multiple dust clouds, and each of these dust clouds will have different physical conditions. Its temperature would be different, if the magnetic fields strengths will be different, orientations will be different in general. So what you measure here with your satellite, like the BICEP experiment, is the net effect of all this. And then when you translate, and then you fit a black body or modified black body to that emission, and then scale it to the CMB wavelengths, you will get that right only if these two clumps have the same temperature, they have the same physical properties like magnetic field, strengths, and orientation, and so on. If these properties are very different, this is one kind of black body with one temperature, there's another kind of black body with another temperature. You're measuring the net, fit a net black body and modified black body and scale it to another temperature, another wavelength. You are not going to get that right. So the models won't work. This was the prediction. In general, the CMB community was dismissive of this possibility. They said, look, we have got it right. We don't expect so many line of sight decorrelation effects. And this may not be the most dominant cause of the mistakes they made in modeling the foreground. But over time, the community seemed to be turning around and beginning to accept that this is an important effect. And this effect needs to be adequately addressed if we want to model the foreground accurately and get down to the CMBB modes. Here is an experiment we did. We looked at a region which is pretty close to the galactic pole and in H1, and then try to count the number of H1 components along each of the lines of sight. So, and then plot a histogram of them. So we can see that almost 90% of the lines of sight has at least 2 components. And then at about more than 60.6 of the times, or the relative fraction, you get 3 components and 4 components. So clearly, even due towards the low dust regions, toward the galactic pole, any random line of sight you pick, there's a very high chance that there are multiple dust components along the line of sight. And unless you adequately account for them, you are not going to get the results right. And this is a more recent survey we did by Panopoulos and Lenz et al. Recently published it, and we reconfirmed this to a much more comprehensive study. And we see again here that a large number of lines of sight, or almost all lines of sight really, either towards the North Galactic Pole or towards the South Galactic Pole, will have multiple dust components. So this is now definite. So what next? What we are proposing to do then is to see if we can get a handle of the situation by decomposing the three-dimensional structure of the galactic magnetic fields and the polarization sources by using starlight polarization. Now, as I explained before, the millimeter, submillimeter emissions measured and the visible light emissions, they come from the same kind of dust grains, and there's a very reasonable expectation that they will be the emission from and the polarization degree at visible light and emission at submillimeter would be correlated, and that's what we see from Planck data here. So what we are proposing to do is to use this correlation that will convince us that it's the same population of the dust which is doing both, and measure V-band fractional polarization using stars as lampposts towards different lines of sight, and measure the three-dimensional galactic magnetic field structure and dust cloud structure. Now, if you want to try to do that, here is a problem. Here, this is a histogram which shows galactic latitude on the x-axis and the number of stars per square degree on the y-axis. And as you go to very high galactic latitude, we have very few number of stars per square degree, like hardly a star or 2 per square degree is what is measured. So if you want to measure the magnetic field orientation, etc., toward these directions, you don't have enough sampling because the number of stars are very few. And that's why we are planning to do a massive survey of the galactic polar regions, both on the northern polar region as well as the southern polar region, above about 60 degrees latitude. What we're planning to do is to build 2 instruments, one in the northern hemisphere and one in the southern hemisphere, 2 polarimeters that will measure very low polarization towards these galactic polar regions using the Pacific survey. The northern survey will run from the Skinnaker's 1.3 meter telescope. The southern one will run from the South African Astronomical Observatory's 1 meter telescope. It is a 4-year survey. We are supposed to start this year, but because of COVID, we most probably will not be able to start this year. Sorry, it was supposed to start last year, but we will start later this year, and it will run for 4 years hence and cover a large area of sky above P equal to 50 degrees. And we will deliver 1 million measurements of line of sight polarization along different star directions. These are the 2 instruments. These instruments are both being designed and built at IUCAA as part of the collaboration. This is the instrument which goes to South Africa, and this is what the instrument which will go to Greece and the Skinakers Observatory. Since we have to do a very large area in a very short time, both these instruments have a very large field of view, half a degree by half a degree. And since the polarization signals we are measuring toward these galactic directions are very low, they need to be very, very sensitive. And the noise floor should be better than 0.1% or so. So it is a big challenge building half a degree by half a degree field of view instrument to measure linear polarization down to 0.1% at very high efficiency, because we want to finish the survey in a reasonable time. And that's going on. We plan to commission the first instrument later this year in South Africa, and then early next year in the second instrument in Greece. And you can learn more about the optical design, the challenges, etc., from this paper, Maharana et al. And the full text version is available at that archive reference. Now, what we plan to do is change the state-of-the-art scenario by at least a factor of 1,000. We will measure polarization to such a degree that the number of stars per square degree we can capture would be increased by a factor of 1,000 compared to the state of the art. That's what we plan to do. And then our main scheme of things is you look at different stars, and you can see that there could be multiple dust clumps along the lines of sight. But if you look at this star, the polarization induced in this star is coming only from this cloud, while the polarization induced in this star is the net effect of this cloud as well as this cloud. And there might be stars in the foreground also, and so on. And by measuring the polarization of these stars very accurately, and then from Gaia, we will know the distances to these stars, and combining this information from the distances to these stars and the polarization along different lines of sight, we can then build a picture of where the dust clumps are, what polarization they are inducing, and then using certain effects, we can also even get a handle on the magnetic field, not only the direction, but the strength. Now, in order to demonstrate that this whole scheme works, we have been already doing some preliminary work with an instrument called RoboPol. RoboPol was an instrument which was again built at IUCAA through a collaboration of mostly the same partners, and it's currently operating at the Skinakers Observatory. This is just a picture of the observatory. It's at 2,000 meters altitude in Crete. But that instrument was built to do a massive survey of blazars, a large number of blazars. But the advantage of that instrument was that while blazars were point sources, and you could put the blazars in these dark spots in the middle, it did have a field of view of 13 arc minute by 13 arc minute, from which you could measure polarization. As you can see this four-fold structure here. So each star is divided into 4 images in the detector. And by combining the light from the vertical images and the horizontal images, you could measure the linear polarization in just one shot. Typically, to measure linear polarization, you have to make multiple measurements. But this one-shot approach makes the whole instrument very efficient. The systematic noise is very low, and we can get down to the required sensitivity. So we use this RoboPol to do a pilot survey. The problem here is, so if you look at the submillimeter beams, they are like 1 degree or 1 square degree, 1 degree by 1 degree. But you are picking stars through pencil beam lines of sight. So you need sufficient number of stars, first of all, to fill this 1 square degree area to get an average polarization within that area which typical submillimeter beams collect. That is one problem. So you need to have enough stars. Will we have enough stars when we are looking toward the galactic pole regions so that we can measure them accurately? That's one problem. The second problem is, even if you have enough number of stars, will they be polarized enough? There might be multiple dust clumps, but each of them may be producing very little polarization, and will we be able to measure them? These are the two questions we wanted to answer. So what we did was we picked up one of the darkest spots in the Planck map where the dust is almost nil, negligible, and picked a large number of stars towards that region and painfully measured polarization toward those stars one at a time using RoboPol, and then looked at the numbers. So we saw that the polarization toward the darkest spots in the Planck map still induce polarization at the level of about 0.4%, 0.3%. So if we can measure this reasonably, 0.4% polarization with at least a signal to noise ratio of 3 or 5, we are in good position. Now, so the instrument we built should get down to that kind of accuracy. And then the next question is, will we have enough numbers? As indicated here, if we have an observer sitting here and looking at through multiple dust clouds, each of these dust clouds will have extinction, although they are very thin, and the polarization that induced can be very low. But do we have enough stars in each of these regions to disentangle the magnetic fields and the polarization structures of these different dust clumps? So to understand that, we again used RoboPol and looked at a part of the galaxy where if you look in this image on the left side, the black circle shows a part of the galaxy where if you look at the H1 map, this is an H1 map, you see two velocity clumps. So these two velocities pick up two H1 clouds in that direction. One is an intermediate velocity clump and then low velocity clump. That is toward the black region. And so this image actually focuses on the low velocity clump. So you don't see the intermediate velocity clump here. But in here, you see the low velocity clump has come up. Intermediate velocity clump has come up in the foreground. And you can see that if you look at the red region, it is just that which is dominating. Now, looking at these two regions, one has the effect of both low velocity and intermediate velocity, the two dust clumps, and this has only one dust clump in the line of sight. Comparing the polarization along these lines of sight, measuring the number of stars you can get to, and so on and so forth, we demonstrate that this whole approach is feasible. And that result is published in Panopoulos et al. In 2019, demonstrating that the whole tomography approach of measuring the line of sight polarization in the stars and the disentangling the 3D structure of the galactic magnetic fields is possible. Now the question is, do we have enough number of stars, and how faint do we have to get enough number of stars? We need to get at, yes.
You have another about 5 minutes to go.
Sure, I will skip some slides, but I will finish in 5 minutes.
Thank you.
If you go down, if you look at this picture, this is the number of stars per square degree further than a certain distance, which you can measure. So if you go down to 16th magnitude, for example, this blue line, you can look at this blue line. And if you need a few hundred, let's say more than 100 stars per square degrees, that is where you need to stand at. And then you can go down to 1000 parsecs, and the required sensitivity is up to 16 magnitudes. So you have to go as deep as 16 magnitude stars, measure polarization at 0.1% or better, and have to do that over 10,000 square degrees of the sky. And that's the challenge. Now, the main problem with this is, of course, an instrument like this would work well only because we are measuring very low polarization. They will work well only if we have enough calibrators around the sky. So one of the problems we have is we have very few calibrators across the sky, and they are all clumped in certain array directions. And this is a list of all the polarization standards which are existing at the moment. And whatever are marked as V here sorry, I will come to that in a minute. Anyway, so this is a list of the whole polarization standards. And this is the list of interstellar standard with a reasonable amount of polarization. The previous one was low polarization, and this one is reasonable high polarization. Now, when we looked at this in polarization standards with a RoboPol instrument and measured them multiple times, we found that many of them are variable in polarization at the level at which we want to measure, at the 0.1% level. These standards, so these standards are nearly not standards for us. Yeah, they are variable. And there are only few of them. They don't cover much of the right ascension range of the sky for an all-sky survey. So they neither meet our requirements. So we had to create a polarization standard. Again, this is a paper actually by Bastien et al., which says here, therefore, they should no longer be used as polarization standard stars for precision work. They looked at a set of published so-called polarization standards. And then they said out of the 13 standards, 7 are variable, 4 may be variable. So whatever people have been used as standards for polarization, only 2 may be usually usable at this level. And this is a really difficult position. So what we did was, while we were building the wallops here at IUCAA, we used RoboPol to measure. We identified stars in the RoboPol blazar fields and identified several of them and monitored them over a long period of time, over the past 3 years or so. Here is just an array deck coverage of the polarization stars candidates we looked at. And this had been going on from 2017 for few nights every month. We were looking at these stars and keep doing that month after month from the Skinnekes Observatory using RoboPol. And we have now 46 stable calibrators confirmed at better than 0.1% all across the sky, covering the whole range of sky. This will form our reference grid across the sky, and this would be a legacy source of references for all kinds of other polarization studies. So in addition to providing accurate polarization measurement toward the galactic polar regions, we also have already provided a set of calibrators across the sky. This is my last slide, I guess. So who are we? I have been referring to we for many times. So our collaboration includes people at the University of Crete, Tarsis et al., and they have been the real originators of this idea. And then Caltech, South African Astronomical Observatory, University of Oslo, the Cosmic Microwave Group, who understand foreground polarization, foreground of measurements and removal of foregrounds, etc. And then NICER, Bhubaneswar in India, and IUCAA. And IUCAA is where the instruments are being built. And the instruments will go to the observatories of South Africa and Crete for carrying out observations. And we have been very lucky with a bunch of sponsors. All our money comes from, almost all our money comes from 2 private foundations, the Stavros Niarchos Foundation in Europe and the Infosys Foundation in India. And then we also have, I have a faculty position, visiting faculty position at Caltech. Through that, we also obtained a National Science Foundation fund of another $1 million grant. So each of them is $1 million grant. And then we have our collaborators in South Africa as a National Research Foundation grant. And more recently, we have also got a European Research ERC grant, our European collaborators in Oslo as well as in Crete. So this is fantastic times, and we are all waiting with bated breath to get the instrument commissioned on the telescopes, first one later this year and the second one early next year, COVID permitting, and then get on with our surveys. But that is our immediate goal. Our real ambition in the long run is to do an all-sky polarization survey, hopefully to 16th magnitude or better. And to do that, we need telescopes with large field of view And we will be looking for such telescopes both in the northern hemisphere and the southern hemisphere. Our estimate is for 9-hour nights, assuming 200 nights a year. That is, these telescopes are fully dedicated for this survey and certain efficiency. We need 10 telescope years to complete the whole sky. So if you divide, we have 2 telescopes already. So if we have 2 more, that is a pretty reasonable, and then 2 more similar instruments on those telescopes. That's a pretty reasonable survey to complete, an all-sky polarization survey. And collaborations are welcome from interested people. Thank you. And if you need to know more about Pacific science, please go to this link. We also have published a recent paper, Pelgrim et al., where we demonstrate that actually in the Planck data, we see the frequency decorrelation effect due to multiple dust clumps along a line of sight. And this has been in the news, one of the recent news releases of A&A, press releases of A&A, and is also being reported in Nature Astronomy, news sports. They come up with these news sports collected every once in a while. And this has also been reported in Nature Astronomy news sports as something to watch out for. Thank you very much.
Thank you, Ram Prakash, for an excellent presentation. We have just time for one question or so. Any questions, please? I don't see any questions in the chat box.
Yeah, I have a question. This is Annapurni here.
Yes, yes.
Hi,
Yes,
Ram, it was a very nice presentation. So with respect to, you said some collaborations are welcome. So for different science cases or similar science cases, or can you just elaborate on that?
Yes, great. So Annapurni, the main science driver is the one which I touched upon in my talk because of limitation of time. But if we get a data set even toward the galactic polar regions, and if in future for all sky, it is a gold mine. The amount of science you can get out of that is enormous. So we have a couple of collaborators who are interested, for example, in Princeton. There is a collaborator who is not really part of the main collaboration, but he is interested in looking at very high polarized regions. There are these anomalously high polarized regions in the galaxy. So he is interested in looking at those regions and finding out what is going on there. There are people in South Africa, Steve Potter and others who are interested in looking at compact objects and their measuring polarization, white dwarfs, and so on. And this magnetic cataclysmic variables, so on. So there are there's a lot, quite a few science cases which we had identified, but I think the amount of work you can do with such a data set would just limit it to imagination. So when I say collaborations are welcome, if somebody wants to carve out another area of science, either another area of science or collaborate with one of the existing collaborators, all possibilities are open at this point of time.
So this is a survey, so you can just use the data for those particular objects from the observed data. Is that right?
Yeah, we will produce the survey, and that data initially will be under some proprietary thing till we produce the results which the collaboration is interested in. And then eventually we would like to put it in public domain. For example, the standards catalog which we have produced, there will be a RoboPol workshop in May where we will be publishing that data. The Blazar data we collected with RoboPol produced a bunch of papers. We have kind of finished what the collaboration wanted to do with it. That data is already in public domain. Anybody can download that data and use. So similarly, our plan is to make this data also public eventually. But then that data is what we observe. But if somebody has a specific science interest and a certain kind of observing strategy you want to do to maximize that science interest and so on, then you need to be part of the collaboration to influence our plans.
Yeah, thanks. Thanks so much.
Thank you, Ram Prakash, for an excellent presentation. Now let's move on to our next speaker.
Thank you.
Dr. Smita Subramaniam. Smita, are you there? Yes, excellent. I see Smita's presentation. Smita? Hello?
Yeah, can you see my screen?
Yes, yes, yes.
And you can hear me well?
Yes, very nicely, very nicely. And okay. Smita is faculty with Indian Institute of Astrophysics, Bangalore, and she will talk about dwarf galaxies. All to you, Smita.
Yeah, thank you, Pandeyji. First of all, I would like to thank the SOC members of this meeting for giving me an opportunity to present some of my recent research work in this conference. So I have slightly modified my title, Probing Galaxy Assembly Process on Small Scales, basically on about dwarf galaxies. As you all know, are you able to see my screen changing?
Yeah, no. We are on your first slide.
Smita, you might have to, are you using Mac?
Yes.
So you might have to do that Control-C or something, right? After every slide.
Yeah, but okay.
Just
now
get the cursor on and then change.
Yeah, but now you can see my slides changing.
No, they have gone off the screen now.
No, we are not able to see your presentation also, even not even the first slide. Yes, now we see your first slide. Can you, yeah. Can you just try changing? Yes. Yes, perfect.
Yeah, thank you.
Go ahead.
Sorry for the glitch. So as you all know, galaxy evolution are mainly driven by interactions. And when we say interactions, they can be classified into mergers and flyby events. What I mean by mergers are like when physically two galaxies collide with each other. They can be subclassified again to two categories, which are major mergers and minor mergers, where depending on the mass ratio of the two interacting systems. And we also have like flyby events. There are also flyby events, which are when two galaxies pass by and then they interact and then later they move away. So during the close passage, they interact with each other. So these events in high mass regime are relatively well studied, both observationally and theoretically. And we know that they induce morphological changes by converting disk galaxies to spheroids, and they induce stellar and gaseous streams around the galaxies, trigger star formation, induce gas inflows leading to nuclear starburst, legion activity, etc. But these kind of studies in the dwarf galaxy regime are rare. So why are they important? Because regardless of redshift, these dwarf galaxies dominate the population in the universe. And according to hierarchical assembly process, these kind of interactions are expected and it is scale-free. And majority of mergers at all redshifts are expected to be between low mass galaxies. So because of these reasons, they are study of these dwarf galaxy interactions are essential. And why are they limited? Because of observational studies limited due to the challenges in detecting these galaxies and substructures around them, then significant theoretical challenges in simulating large volumes to provide realistic cosmological context, and also simultaneously resolving galaxies down to the dwarf regime. But can we extrapolate what we see in the massive galaxies to dwarf regime? It may not be exactly correct because these are low mass systems, hence low tidal effects, low potential wells. So these interactions, whether they actually induce star formation, they change morphological changes, drive gas inflows, etc., are not may not be similar to what we see in massive galaxies. And also they are prone to environmental effects and also feedback processes and different from what we see in massive galaxies. So in this context, I want to present briefly two topics on this context. One is about an individual system of interacting galaxies, which is the Magellanic System, and again a sample of dwarf galaxies in a very underdense region in the universe, in the local volume, of course. So first, Magellanic System, it is nearby interacting system of galaxies. Here you can see that this is a combined optical and radio image. You can see the large Magellanic Cloud here and the small Magellanic Cloud here, and you can see gaseous stream around them in pink from H1 data, and they are a really interacting system, very nearby minor merger event kind of system. Now, what we know about this system, like based on simulations, are like most of the observed gaseous features. So here there are the two plots from gas and the stellar density from simulations from Vesla. So observed gaseous features are mostly reproduced by tidal models like LMC and SMC interaction. But when they are tidally interacting, you expect stars as well, because they also get affected by gravitational forces. So presence of intermediate or old populations. Why I say intermediate or old? Because most of these features that you see in gas and are, like, according to simulations, are formed in the last 300 million years, like mostly the bridge part, and so that is the region where you expect mostly tidally stripped stars as well. So stars older than 300 to 400 million years, I call them as intermediate or old stellar populations. So we expect them in these regions. There are studies which find these kind of stellar populations in the Magellanic Bridge region, that is this region in between these two galaxies, but whether their origin, whether they are tidally stripped or part of the overlapping stellar halos of the MCs is still debated. There is a lot of multi-wavelength data available for this system, and it covers a large area in the sky. And I mainly concentrate on this survey, which is the VISTA near-infrared survey of the Magellanic Cloud system using 4-meter VISTA telescope. So here, this is the sky coverage of VISTA VMC survey. So this is the small Magellanic Cloud, and this is the large Magellanic Cloud connected by these tiles, also in the bridge region as well. So most of the studies found earlier stars in this region, but they couldn't conclusively say whether they are part of the overlapping halos or whether they are tidally stripped from these interactions. So to understand this better, we mainly concentrated on the outskirts of the SMC, the entire SMC, mainly concentrating on the outskirts connecting this bridge region to see whether we see any stellar substructures here. So for that, we used stars, which are called red clump stars. Ishwar introduced the stars in the previous talk, but another important property of the star is they are standard candles. So we can estimate the distance to these stars, and they are numerous and distributed all over these galaxies. And they are intermediate age stars, which are stars older than 2 gigae. So we looked at the stars distribution. I'm not going into the details of it. And what we found finally is that in the eastern regions, that is in these regions, which are here these and connecting to the bridge part, we see a stellar substructure, actually a foreground stellar substructure around 12 kiloparsec in front of the small Magellanic Cloud. But we are again limited by the survey data, because we don't have this entire coverage here. And when we go to the outskirts, the density decreases much. So we could not do more, but what we found is that this from the infrared survey. So some of the discrete fields here, it has already shown this kind of feature in optical surveys, but the entire continuous kind of coverage was obtained from this near infrared survey. So with Gaia is very excellent because we know that it provides the data for the entire sky, and also it gives kinematic informations of star. And here, we see this is the coverage of the LMC and SMC in the Magellanic system, and this is the study which we did with VISTA survey. And here in this particular study, we looked at the entire region of the SMC covering the bridge, major part of the bridge as well, to see whether this feature is seen outskirts. So we located the same feature in the eastern regions to around 12 kiloparsec, so to up to around 5 to 6 degrees. Beyond that, we didn't see that, whether it is due to a density effect or whether we don't see it actually is still not understood well, but we do see them up to around 5 to 6 degrees in the eastern part. And the advantage of Gaia again is it provides kinematics, and we also found that these two populations, like the foreground stellar substructure, is kinematically different from the this is the main body population, and this is the stellar substructure. So this is actually kinematically different from the main body. So these all suggest that it could be the due to the form during the tidal interaction of the two clouds. Now, moving on, we compared this with the simulations, which are from Besla and Dias and Becky 2012. So here we compared, so this gray points are from the simulations, and magenta are the main body region, and cyan are the stellar substructure we found at different distance. So here you can see it is not very much matching, but they are comparable with these features here. And we also checked with some disk models, spheroidal model for the SMC, and we think that it is mainly coming from the disk of the SMC, this population. But also we can see that these kind of features behind the galaxy is not found in our studies. So these are something which is yet to be understood. And along with that, we don't see this kind of feature beyond 6 degree to 7 degree, where also we expect these kind of features. So then another, as I told, as these are tidal, all kind of populations, stars of all different ages are expected. So red clump is one, because we could find the distance to them. RLI rays are another stars for which we can estimate the distance, but they are older stars, around 10 to 13 giga-year-old stars. In that, we didn't see this kind of feature. So that is also, again, something puzzling, which we are yet to understand. But we think that if RLI ray stars and spheroid part, that is why that might not have been stripped. If it is in the disk stars are being stripped, but there could be also some role of ramp pressure effects in this. So what we finally require is a 6-dimensional information, like we have position, distance, then the proper motion measurements. Then what we miss is a radial velocity measurements. And especially this is important to compare the stellar and gas kinematics. For the gas kinematics, we normally get only radial velocity measurements. So these are faint stars, so it's difficult to obtain radial velocity measurements for a large area of the sky. But for red giant branch stars, we do have these kind of radial velocity measurements, but the issue is that they are not standard candles. So we miss the distance information here. We try to mitigate this by, in this study, by comparing the Gaia proper motions of the red clump stars, for which we have the distance, and for the red giant branch stars, for which we don't have the distance, but we have the radial velocity. So interestingly, the stars in this eastern region, where we see this substructure in red clump, we do see a radial velocity variation. And then when the proper motions are comparable with red clump and RGB, we think that this variation in radial velocity could be due to the stellar substructure effect. And based on that, we estimated the epoch of interaction, and we found that it was around 350 million years, which matches with the simulation. But still, these kind of information, by comparing the proper motion, won't be is not straightforward. So it is always better to get the entire 6D information from the same tracer. And we have some attempts made using Flame's instrument at VLT and GMO's instrument at Gemini South. So the observations are being carried out for these red clump stars, but these are for very small fields, but hopefully we will have more data and more confirmation about these results. And future instruments like wide field instruments like Foremost will be very useful in this kind of study. Now so this Gaia, as I said, it covers the entire sky, and it is really interesting to see the LMC part also, which is a kind of disk galaxy. Most of the previous studies were limited to a very inner region. Now we have the entire disk covered from Gaia. So what we found is that by modeling the 3D distribution of stars, using again the stellar distance indicators and modeling it as a plane, we could identify a kind of U-shaped warp in the outer disk of the LMC. So earlier studies were limited up to these kind of regions where it was not very clear, and later on we found that in this study with a larger spatial coverage, we could see that there is a warp in this. We are still trying to understand what are the causes for this. It looks like these are all due to the interaction events. So what does the study of the Magellanic system say? It suggests that dwarf interactions create substructures and warp, and we also see in some of our earlier studies that it enhances and triggers star formation in these galaxies at same epoch when they interacted in previous epoch. So moving on, so these kind of systems are like whatever I suggested are mainly, whatever I presented is mainly based on very individual system and very detailed studies and very much focused, but numerous panchromatic surveys which studied dwarf galaxies did not actually focus on the impact of interaction between galaxies on their evolution. So these are again some of the individual systems which we see here. This is a dwarf galaxy again, DDO68, and these are the substructures that they observed using HST and LVT facilities. And this is again another galaxy at around 10 megaparsec from here. So recently there are progress, like there are a lot of like surveys coming up in this context to understand the galaxy interactions, dwarf galaxy interactions in their evolution within 10 megaparsec using these surveys. And we also have improved simulations which will allow to compare the observations with theory in dwarf regime. So one of the interesting results from simulations that we see is that typically they drive moderate increase in the star formation rate for low and intermediate redshift, like 2 to 4. This has been seen in some of the studies by this group, but here we would like to look this in more detail. So we want to understand the dwarf-dwarf interactions in different environments.
You have a couple of more minutes.
Yeah, sure, thanks. So this is an ongoing work, and here this is a project in which we want to understand the evolution of low mass galaxies in different environment. So what I mean by environment, here you can see that there are underdense regions in our universe called voids, and also very dense regions like clusters of galaxies. So these kind of regions we can look at for these kind of population and try to see how the environment affect also. But it is always good to go for underdense regions, because like if there is a massive neighbor, and that will have more impact than the dwarf-dwarf interactions. Like so, it's always good to go for void underdense regions. But it's good to have a comparison sample in different density regions as well. So in this, and there are low mass galaxies in void regions. The majority of the dwarf galaxies in voids are isolated. Like there are studies which say that observations which show that around 20% galaxies are in pairs or triplet systems. Like this is one from GMRT observation, like from Jairam and team, where they found that this kind of dwarf galaxy has a large envelope, H1 envelope, and there are different components. So this is mapped in the same region using GALAX observations. So, so here in the same one of the void regions, which is the Linus Cancer void, which is around 80 megaparsec from us, and in that galaxy we using the sample provided in these papers and the parameters, we identified 43 dwarf galaxies, 14 are interacting and 29 are isolated. And we used the GALAX data to find the integrated star formation rate and results. So this is the entire sample, and it is over the entire stellar mass and the SFR log plane. And these red points are the interacting ones, and the blue one are the isolated. So here in this plot, it looks almost all of them are really together, but we need to see that there is a large range in star formation rate. And also in this part and this part, we don't have enough sample. Already we don't have many sample, but to look at a relatively better region, we looked at this part, and this is what we found. The median star formation rate is found to be like around 5 times more in interacting dwarfs. So this is very preliminary results. We are checking individual systems and also like what are the properties. So like these off points, like one of them, like as I told earlier, so some of them are really merging features, like you can see in H1. But this kind of galaxy where it is off, this is just a flyby event, because we think that it is a flyby event because in the outskirts you see some signatures of interactions in the optical images. So the better sample selection with different range of interaction will be useful. So, and again, like to understand it better, like we have a pilot study going in UV and optical H-alpha using these facilities. So this is a UVIT image where you can see the improved spatial resolution compared to the galaxy in the previous one. Previous image. So this helps to understand, this will help to understand the spatial distribution. So these observations are going on, and we have observed, we have data for a couple of them, and we have also complementary data from other facilities. And I'm also part of a UVIT Virgo cluster survey. As I mentioned, the dwarf galaxies in this cluster will be interesting to look at and compare with this region. So then the plan is to extend the study to a larger sample. So this is the summary slide. So the main takeaway is that the hierarchical galaxy formation model predicts galaxy interactions in all mass range, and from individual systems like Magellanic system to a larger sample, like these kind of features, the effects of interactions are seen, and future facilities like foremost moons, JWST, INSIST, etc., will significantly enhance our understanding in the local universe and at different redshifts. Yeah, with that, I conclude. Thank you.
Thank you, Smita, for a very interesting talk. I think we are running late. We have time for just one question. One quick question, please. I think let's move on to our next poster presentation. And we thank Smita again for a very, very wonderful talk. Thank you for finishing in time. And yes, we have Ramya Sethuraman. Dr. Ramna Sethuraman is with us in Indian Institute of Astrophysics, and she is a great help for our TMT project. Smita, no, Ramya, are you there? I saw your poster.
Yeah.
Yeah,
Yeah.
please.
Can I share my screen?
Yeah. Yes. No, I'm not. Yes. Yes. Please go ahead, Ramya.
Yeah. Thank you, Professor Pandey. Can you hear me all right?
Yes. Yes.
Yeah. Okay. Thank you, Professor Pandey. I wish to thank the organizers for giving me a chance to present the ongoing work on low surface brightness galaxies. We are trying to understand their formation and evolution. So this is the work which is ongoing and is being done with my supervisor, postdoc supervisor and collaborator, Professor Leha from Shanghai Astronomical Observatory. So thanks to many collaborators, I was introduced to low surface brightness galaxies when I was doing my PhD work. There we searched for AGN activity in giant low surface brightness galaxies, which interested me to learn about low surface brightness galaxies in more detail. So then we try to obtain a systematical search of low surface brightness galaxies using the SDSS DR7 data. So there are already many catalogs existing, but we wanted to improve the catalog based on the bulge disk decomposed data of Meet et al. Again, they have about 600,000 galaxies, which is a bulge and disk decomposed into two components. So we are using that particular catalog to obtain more of low surface brightness galaxies. So the working definition of low surface brightness galaxies is that the central surface brightness of the disk in B band is fainter than 1 magnitude fainter than 21.6 magnitude per arcsecond square, which is 22.5 magnitude per arcsecond square. So we have the bulge disk decomposed data of 600,000 galaxies, and out of that we obtain, using the criteria, we obtain the low surface brightness galaxies to be about 1,280 in the sample. And from that, we also try to obtain the giant low surface brightness galaxies. The total number of giant low surface brightness galaxies is about 248 from the total 1,280 galaxies. So out of all the catalogs available, which is the bulge and disk decomposed catalog of SDSS galaxies, we found that the Meet sample was the best catalog because we did 100 galaxies bulge disk decomposition ourselves and found out that our values match very well with that of MEAT catalog. So that's why the MEAT catalog was selected. So giant LSBs that's selected will be the largest known so far, 248. Giant LSBs were selected based on this diffuseness criteria given by Sprayberry et al. Note that there is no requirement of a bulge here in this particular catalog. Even that there is no requirement of a bulge, when we see the 248 giant low surface brightness galaxies, there are about 50% of them having a prominent bulge with Sussex index greater than 2 and masses greater than 10 to the 10. So we cross-match the sample with MPA-JHU catalog to obtain other properties like star formation rate, stellar masses, and this is what you see for HSB galaxies in gray and low surface brightness galaxies in blue. The specific star formation rate was a stellar mass. And you see, as expected, the star formation rate is slightly lower when compared to the HSB sample. As I mentioned to you that
You have just 1 more minute to finish.
Yeah, thank you. I'll do that. As I mentioned to you, there is more than 50% of the giant low surface brightness galaxies which have a bulge, prominent bulge. That is what is shown here in this blue histogram over here in comparison to LSBs and HSBs. So we also estimated the stellar mass surface density versus stellar mass. This is a very tight plot, which is already known. And for giant low surface brightness galaxies, it occupies a location much lower than the normal high surface brightness galaxies. So this could be one of the criteria to select giant low surface brightness galaxies itself. So the final one, what I want to show you is the mass size relation of low surface brightness galaxies. We put LSBs and giant LSBs on this size stellar mass relation. What you see here as gray and red dots are bulges, and the pink and blue dots are for disks. This is the first time that the LSBs are put on the size mass relation, and we see that the bulges, bulges are hosting locations which are similar to that of massive early type galaxies, which means to say that the bulges are more massive and compact. This is and might have formed at z is equal to 1, while disks are very extended and very large, and in comparison to the SD irregular galaxies in the local universe at z is equal to 0. So so this is quite interesting for us because we don't know what is beyond this. Do we see more extended galaxies than what is expected? The deeper surveys like LSST and other surveys will be very helpful. And the next step in our study would be to understand, using the IFU data, understand the stellar populations of bulges and very extended disks. And we would like to have an IFU data which is almost about 4 times the, which goes to the 4 times the effective radius of the disk to understand the stellar populations in them. I stop here and I thank you for the opportunity.
Thank you, Ramya. Now, I think we can have discussions in the Slack group. In the interest of time, we will move on to our next poster by Mahopatra. Abhishek Mahopatra, are you there? Yes, yes. I can see your poster. Please go ahead.
Yes. Thank you, Professor Pandey. I'm Abhishek Mahapatra from NIT Rourkela, and I'll be talking about low G C3 observer galaxy connections. I first thank the organizers for giving me this opportunity. So basically, as you know that there is a medium between galaxy and the intergalactic medium, which is known as the circumgalactic medium, which contains most diffuse gas which are outside of the galaxies. And it can only be observed in the quasar absorption because the gas density is very low, it is diffuse, so you cannot observe them directly in emission. So what we do here is basically we observe such gas using quasar absorption, and then we study the host galaxy properties whenever we detect a galaxy, and then compare the connection between both the observer and the galaxy. That's why, and we took particular type of gas, that is the double ionized carbon gas. So we have done this for both high Z and low G, which is like 2 to 3.3 and 0.2 to 0.9 using HST cos, and the high Z data is from VLT UVS. So after detecting all these gas in quasar absorption, we do a photoionization model using cloudy to derive all sort of physical properties of this gas, which you can see in this figure. So the density, the metallicity, the overdensity, and the size of the absorber each suggest that these gas are indeed from the circumgalactic medium, and we see different evolution of these observer properties in this figure, where I have shown a different, I have beamed these observer in different redshift and show the PDF plots of these properties, for example, this metallicity properties. And you can see that there is a significant evolution between metallicity of these observers from low Z to high Z. It signifies that the circumgalactic medium is different for low Z, and it is completely different for the high Z gas observer. So that means that the host galaxy should be different compared to in accordance to the circumgalactic medium. So then to study the observer properties, what we have done is we first start the gas at a higher temperature and allowed the gas to cool from higher temperature to the actual gas temperature, and we calculate what is the time taken for this cooling, and we multiplied this with the sound crossing time, which will give us the cooling length scale. And we see that whatever metallicity and cooling length scale correlation that we see in our observer, we can get this exact correlation from this cooling model. And this signifies that cooling takes place for this circumgalactic medium observer and plays an important role for the stability of the gas clouds. Next, we check whether there are two different kind of observers in the circumgalactic medium or not, and we find that there is indeed two different. Exists a biomodality in the C3 observer. For example, you can see that these are high metallicity observers in the red, and these are low metallicity observers in the blue. And high metallicity observers show a strong correlation with the column density of C3, that is the size of the observer shows a strong correlation with respect to the column density of C3, whereas the low metallicity observer do not show that correlation. Then we sort of see how the metallicity evolution are compared with a known kind of observer. For example, the damped Lyman alpha observer, which sort of trace the galaxy environment, and then there are Lyman limit system or partial Lyman limit systems. So we find that the low metallicity observers sort of trace the partial Lyman limit systems, whereas the high metallicity branch observer trace the damped Lyman alpha system. So basically what it tells you is that the C3 can be used as a tracer to trace the galaxy environment as seen in the DLAs and Lyman limit systems, whereas you don't see so much of DLAs in quasar absorptions, whereas you can find out many metal absorptions in the quasar absorption. So basically you can use it as a tracer to trace the galaxy environment. Then what we do is basically we look at the galaxy properties using the SDSS DR16 catalog. Basically, we look at the quasar fields. We like at a particular impact parameter. Sure. Thank you. So we look at the, we find the galaxies and do a SED fitting tool using backpipes, which are implemented in this code QA gals, which we have developed to find out the galaxies around this observer. And doing that, what we find here is that indeed the star formation rate of some galaxies that are associated with the quasar absorptions are indeed showing a strong correlation with the metallicity of the observers. That is, whenever we find a strong metal clouds that have higher star formation rate of the host galaxies, whereas when we find low metallicity cloud, it has less star formation rate of the host galaxies. That means that there is a strong correlation between the CGM observers and the galaxies. This we need to confirm because these are all photometric data. We do not have confirmed redshift of these galaxies, because then only we can associate these galaxies with the observers, that is using the dispersion velocity. You need to have the confirmed redshift, which can be done using follow-up spectroscopy observations or multi-spectroscopy observation, as Professor Anupuni was showing that on the first day. So we are looking forward to have this kind of facilities to have spectroscopy of this data to confirm this trend more accurately. So thank you.
Thank you,
So these are my
Abhishek.
summaries.
Very
So if you have
interesting
any
presentation.
questions.
I think we will have the questions in the Slack group. I think in the interest of time, we move to the next speaker. Our next speaker is Dr. Shanti Priya. Shanti Priya, are you there?
Yes, Pandey sir, I am there.
And good, please upload your talk.
Sure,
And,
sure.
Shanti Priya is with Osmania University. She's a faculty head of the department. And yes, we can see your presentation. Can you just try to go to the
Okay.
next slide, please?
1 second, I'm trying. Yes. Okay.
Okay. Are you able to go to the next slide? Can you just check?
Yes, I am. Yes, I am. I've checked it.
Okay, perfect. Please go ahead, Shanti Priya.
So good afternoon, one and all. Greetings from Department of Astronomy, Osmania University. As Pandey sir said, I am Dr. Shanti Priya, Head Department of Astronomy, and I'm very happy to present my work today before you all. My talk today focuses on comprehensive study of interesting neglected closed binaries, and I'll be discussing on the work done related to this. Sorry, a prominent statement that I came across in literature, which I am sure you all will agree, quotes a good theory needs a good observational basis. So being a stellar astronomer, our current understanding on existing stellar models is well explained by observational evidences. And one of the primary reasons or sources being binary stars. So my research interest focuses on closed binaries, and closed binaries are considered to be effective research tools to determine fundamental stellar parameters like mass, radius, luminosity, etc., their distances, and to test stellar evolutionary models, and vital to understand the physical phenomena with respect to their magnetic activity, mass transfer between the components, their common envelopes, their Roche loop filling, presence of third bodies, and so on. And closed binaries also tend to be very interesting sources due to the diverse nature that exists with respect to their components that are present. I listed out various components that are observed in the closed binary systems. Thus, we can say that closed binaries, in whatever form they are existing, whether it is algols, beta Lyrae, eclipsing, etc., are important sources to stellar astrophysics. So I would like to present a few scientific results on closed binaries that were concluded from data obtained using available ground-based facilities in India. So to begin with, I will talk on a low resolution spectroscopy of a few algol systems that we have carried out. So here we have analyzed the spectroscopic data of around 30 algol systems, short period algol binaries, which mostly had primaries belonging to B and A spectral type. So before I go ahead, algol systems are basically semi-detached closed binaries, mostly with massive primary and low mass late type companion. So in our study, we highlighted the results of low spectroscopic observations collected from 2-meter Himalayan Chandra telescope of Indian Astronomical Observatory. We have tried to interpret the state of activity in all these listed algols. And we have done that through their equivalent width studies. So here I present the sample result. This is one of the result out of the 30 that I have listed. We have done period variation on all the objects that for which data is available, and photometric light curve observation was done, and the spectral reduction was carried out. And from the spectral reduction, we have studied the prominent lines and their behavior, and also we tried to identify the activity levels along with the accretion disk, if at all it is present, and how it will be affecting the algol system. And to move on, specifically we have taken H gamma line into consideration, which is thought to be a very sensitive line to gravity and temperature, and derived log G values for all the algols in the study. And from the analysis of the effective temperatures and the spectral analysis, we have come to a conclusion that algols with late type of secondaries, almost all the listed objects had late type secondaries, and they seem to show some strong chromospheric activity than the single stars which have similar spectral types. So moving on, another interesting object that we have studied is TYC 5532. So this is one of the contact binary. Contact binaries are again closed binary systems in which both the components share a common outer envelope. Such class of binaries, as you see here, they share a common envelope, and such class of binaries, being short period objects, provide a good opportunity to investigate evolution of common envelope and also merging process, which is observed to be a final evolutionary stage in these kind of systems. And also they seem to be very good progenitors for planetary bodies and also exoplanets. So this particular object which we have studied, the TYC, is catalogued to be one of the bright contact binary in literature, but no significant work was given in literature. So we try to observe it photometrically and spectroscopically using 1.3 meter JCBT telescope and 2.3 meter VBT telescope for both photometry and spectroscopy respectively. And also we have taken data from the archives, ASAS, NSVS and CSS to do a long-term observation and to understand the behavior of this object. So here when we have observed from ASAS, which was around 2008 till 2016, we observed that the object showed a totality, but there was no significant activity which was observed in the light curves. This was in contrast to what we have observed in the spectroscopic observation. So when we have done spectroscopic observation, and we observed few prominent lines focusing on H alpha and sodium line, we observed that they have displayed a varying fill-in effect, indicating that there is a high chromospheric activity which is going on one or both the components. So here I have displayed the comparison of both the H alpha and sodium line with varying phase, and to understand it better, the chromospheric activity which is visible in spectroscopy, we moved on and conducted a period variation study. Period variation study. And in this period variation, we observed a period decrease over 11-year time interval, and we could see a sinusoidal nature in the curve. And we wanted to check what is the aspect of the activity which is being visible in spectroscopic observations, and mostly these period variations that are observed in these objects is attributed to either angular momentum loss or presence of third body in these systems or mass transfer. So after varying it through our calculations, the period change which we observed, we attributed mostly to the angular momentum loss, with a negligible contribution from the third body. The mass of the third body that we have derived is around 0.6 solar masses, and we suspect that it is either a faint, very faint main sequence star or a dwarf. Further long-term observations will play a key role in confirming the nature of this tertiary component that is evident in this system. So the next object that we have worked on is a SDB plus DM type of binary. It is a subdwarf binary, wherein such SDB stars in general are hot subdwarfs, which are core helium burning stars with thin hydrogen envelopes, and their masses are around 0.5 solar masses. And a large population of these SDBs tend to be short period binaries, and the variable which we have selected, 3/C3315, is one of the hot subdwarf binaries with a low mass main sequence companion. And we carried out detailed photometric and spectroscopic analysis. The object is a very faint object, so we couldn't get any photometric data for it, but we managed to procure some spectroscopic data for this object. So for photometry, we have taken data from TESS archive. So using the latest available data, we have done the photometric analysis, and we could observe that this is a non-eclipsing SDB plus DM type of binary. And the light curve showed a reflection effect. To check this activity, if any activity is there in this, again, we have, as I've told, we have taken few spectral observations, and we tried to analyze the spectra, and we could focus on H beta line this time. We couldn't get the H alpha, and a few helium lines which were available. So from the variations that we could observe, we have majorly attributed the variation that is observed in the lines, majorly H beta line that is observed, is due to the reflection effect that is observed. And we also checked the period variation for this system, and we observed that the variable shows a decreasing trend, parabolic trend, with a dp by dt of minus 1.36 into 10 to the power of minus 7 days per year. And the possible reason for this variation observed is attributed to the loss of angular momentum due to gravitational radiation, which is majorly seen as a cause in these SDB binaries. We have come to this conclusion after ruling out role of mass transfer or magnetic braking, as this is a detached binary, and also the presence of third body, which is not evident in the period variation and also in the calculations. So we have, from the photometric results that we have obtained, we have calculated the absolute masses for this system. And from the absolute parameters that we have resolved, we observed that the system in the study is within the extreme horizontal branch. And further calculations, we concluded that as this is in a detached system, is a detached mode, it will evolve into semi-detached configuration, and it will start mass transfer in less than Hubble time. So such kind of objects, studying such kind of objects will enhance the idea of evolutionary theories with respect to the post-common envelope binaries, as most of the SDBs are HW Virginis type of stars, which tend to be post-common envelope binaries. So moving on to the next set of binaries that we have worked on, these are interesting variables, notedly.
We have 2 more minutes to finish.
Sure. Variables named as ultra short period binaries. So in literature, the minimum short period cutoff that is given for contact binaries is around 0.22 days. And there are various theories given to explain the observed short period cutoff, but it still remains an open question. So in contrast to that, there were several ultra short period binaries discovered with periods less than 0.22 days, and very handful of objects have been spectroscopically studied so far and are commonly observed to show spot activity, and also they are known to host third bodies and exoplanets. So taking in view their significance with respect to their evolutionary state, we carried out photometric analysis of 8 such binaries from Ogle photometric data, and all of these 8 objects tend to be towards the galactic bulge. We also conducted a statistical analysis of the objects studied so far in literature, and we observed that a substantial observational studies are needed with respect to ultra short period binaries. And we tried to calculate the absolute masses from the photometric results that we have got for the objects, and we observed that most of these objects had primary masses less than 0.63 solar masses, and this indicates that they fall in an instability. They'll indicate that there is some instability in the mass transfer, and that may lead to probable coalescence of both these components which are present in the system. Now, there are many uncertainties existing in study of ultra short period binaries, which can be addressed through the observing facilities that have been discussed so far in this conference. And most of these objects, all the objects that I have discussed, tend to be faint sources and need good optics to study them spectroscopically and get a radial velocity studies done. So if we succeed in that particular thing, the discrepancies that exist with respect to the evolution of these objects, especially ultra short period binaries, proper observational evidence can help in solving those discrepancies, at least reaching and giving a new idea of evolutionary theory. So I would like to conclude by saying that we aspire broad prospects in the study of closed binaries with the upcoming observing facilities that promise very high sensitivity and good resolution, spectral resolution, and we may expect new outstanding discoveries as this is one of the good promising research field, and this is my research group, and I thank the organizers for giving me this opportunity to share my work. Thank you. Thank you.
Thank you, Shantipriya, for a very interesting talk. We may have a time for a quick question. Any questions, please?
Yeah, can I ask one question?
Yeah, yes, please.
Yeah, so
Yes,
in your estimation of variation in sodium lines and H-alpha lines, so were you phase, could you match with the phase of the variation?
Yes. Okay. Yes, this is phase matching only. So with respect to the phase, in a corresponding phase, how they are varying, we have observed it with respect to the phase.
Okay, and then that
so
is why you're
at 0.5 it's the best
phase.
thing. Yeah,
Okay.
yes. It is with as a function of phase.
Okay, thanks.
Okay. Thank you, Shantipriya, again for a very nice talk. Now we have Dr. Rukmini Jagirdar with us, but she has provided us with her recorded talk. So may I request Mamta to play the recording?
Yeah, I'm playing. Mamta is doing that? Okay. Okay, thank you.
All right, so we will start with this talk.
So Rukmini Jagirdar is again from Osmania University, Department of Astronomy. And Muthu, please.
I think Mamta has uploaded.
Organizers.
Yes, let's start.
Hello everyone, I'm from Osmania University, Hyderabad. Before I present my talk, I would like to thank the organizers for giving me the opportunity to present our work and on this platform. I'm going to talk about why we are proposing for a long-term investigation of short-period contact binaries. This is our abstract, wherein our primary objective is to build the catalog of contact binaries with the totality. And in the absence of spectroscopic studies, such kind of such catalogs would provide an important information. Binary stars as such are systems comprising of two stars orbiting periodically around common center of mass due to mutual gravitational interaction, and they show mutual eclipses. if the orbital plane makes a large angle with the sky plane. And the concept of contact binary being a class of eclipsing binaries was introduced by Kuiper. And since then, there has been an extensive study of these kind of binaries. The components of these contact binaries are in physical contact and share common envelope. The components are strongly distorted, and they fill or overfill their Roche with mass transfers taking place between the components. They show stellar rotations synchronized with orbital revolution, and observationally, they show short orbital periods with a continuous light variations in their light curves. Most of them show O'Connell effect, which is due to the stellar spots, that is magnetic activity. And they also show period variations, which is due to mass transfer between the components, or it could be due to angular momentum losses from the system, or the presence of tertiary components. Contact binaries which are studied in clusters give an independent means of distance determination for the clusters as well. So it is also understood that with the evidence of blue stragglers being formed through coalescence of contact binaries, a small but non-negligible fraction of blue stragglers should be contact binaries in these clusters. So their studies would reveal important information about stellar absolute parameters, limb darkening coefficients, their distances, the stellar ages, the stellar evolutionary models, and they also help in studying stellar evolution in extreme environments and in characterizing tertiary objects that are orbiting around the binary systems and are interacting with the system. The work that I am presenting here is for the objects for which data was collected from various ground and space-based observatories. The data includes long-term observations for some of the objects, and it also includes one of the observations taken from our own observatory, Japal Rangapur Observatory. The period and epoch of these binaries was estimated from the time series data using Percy, and the phase-folded light curves were obtained. The light curve analysis was performed using Wilson and Devaney code for some of the earlier research, and then for the latter part of the research, Phoebe was used, which also actually runs through Wilson and Devaney routine. The initial parameters for the analysis were taken following standard procedures with effective temperatures adopted from Allen's tables and Gaian. And one of the important parameters for binary system is mass ratio Q. So, which is nothing but ratio of mass of secondary to that of the primary component, M2 by M1. So, after a careful Q search, the secondary temperature T2, primary light L1, inclination I, and the critical potentials omega were taken as adjustable parameters, and iterations were performed to get the synthetic light curve and the light curve solution. These are the observed and synthetic light curves plotted for the partially eclipsing contact binaries, XZ Orionis, and variables in open clusters NGC 6791 and B33, and variables in the globular cluster M4. This table gives you the details of best fit light curve solutions for the contact binaries. All the contact binaries studied here are of short periods with a range of effective temperatures, and the light curve solutions have resulted in mass ratios ranging between extremes, say from 0.063 to 1.2. And the absolute parameters we have derived using the Gaussian relations for short period contact binaries, and the distance were estimated from the Gaia. So we have conducted period variation studies for some of these objects. Most of the contact binaries, due to their dynamical nature, are found to be showing orbital period variations, which are studied using eclipse time variations between observed and calculated times of minima over a long period of time. So these studies, they help us in understanding the structure of structure and evolution of the binary system, and provides additional information also, such as the angular momentum lost by the system through the stellar wind, mass exchanges between the components of the system, presence of additional components, stellar or substellar, which are orbiting around the binary system, And when their signatures are not significantly observed through the light curves, additional light curves or transits in their eclipse periods. And they also provide, the period variation studies, they also provide interstellar, inner stellar structures and testing of general relativity by means of apsidal motions. And they also give an opportunity to study magnetic activity through quadrupole moment, that is Applegate mechanism, and activity cycles if possible. So we see that the period variation studies become a prominent tool for understanding the reasons for periodic and cyclic changes in the binary system configurations. Here we performed the period variation studies for the 6 contact binaries of the globular cluster M4 using the data from the case database and determined the period variation rate. Here it is observed that mass transfer between the components, which is a common feature in the contact binaries, results in either increasing or decreasing trend in their periods. However, the observed change could be a part of a long-term periodic oscillation in the orbital period as well, which is due to the presence of the tertiary component or Applegate mechanism. With further data, we can further confirm the same. In the search for magnetic activity and activity cycles in the contact binaries, we came across the flaring binary DX2. So for which flares were discovered and period decrease was reported. So in addition to the long-term archival data available from the various sources, we studied the data which was available from the test database. So we have performed the light curve analysis, flaring activity studies, and period variation studies for the same. So after finding interesting results, we tried to perform the similar studies on other eclipsing binaries, other flaring binaries using the test database. So these are some of the prominent flares that we have identified from the test data for all the 5 flaring binaries. The light curve analysis of BX3 using the Wilson-Dibeny code is listed here in the table, along with those derived for the other binaries, which was reported by the other authors. All the 5 binary systems are of spectral M spectral type, and definitely they would show a strong magnetic activity. So the light curve analysis of BX3 has revealed that it is a marginal contact binary. And the table here lists the details of the flare studies performed on the 5 flaring binaries. It is observed that BX3 showed highest occurrence rate of flares with low energies, whereas GJ3236 showed least occurrence rate with the high energies. However, this could be due to the limited period of observations, observational data available from the test. Or it could also be due to quiescent phase in the magnetic activity cycle of the components of these binaries. So additional long-term data can confirm the same. We performed a check on the rise and decay times of the flaring activities observed on these binaries, rising and decay times with energies. And we could see clearly that similar to that of solar flares, the decay times were longer than the rise times. That is, there was a sudden rise and a gradual decay of these flares. And they also showed a power law trend with energies. We studied the flare energies with the period of the binaries for the 5 flaring binaries and compared the results with those studied by Huang et al., who had performed similar studies for objects from the Kepler database. And we found that GJ3236 followed a power law trend along with those studied by Huang et al. And one of the flares of GJ3236, which was observed to be a super flare with energy of the order of say 10^36 Earths, is shown in the insert here. So it is interesting to observe and report that there are quasi-periodic oscillations in flux during the decay of this flare. we have seen that the other 4, including BX3, were all grouped up into the lower left end of the plot, which could be as such due to the quiescent phase of the system, or it could be due to the insufficient data taken from the phase. Here you can see orbital phase distribution of number density of flares observed using the test data. And we could see that for GJ3236, the higher number of flares were detected during the primary eclipses, indicating that their origin could be on or closer to the secondary component of the binary system. And for BX3, we found that large number of flares were detected both near 0.25 and 0.75 phases, wherein the origin could be on either both the components or closer to that of the Lagrangian L1, which is hypothesized by the earlier theories, wherein it is suggested that magnetic reconnections in the extended atmospheres of both the components around L1 may actually lead to the flaring activity, may actually lead to the super flares. So we have also attempted to see hourly occurrence rate with energies for the effective temperatures of the system, but we think that larger database is needed to conclude any significant understanding of the same. So we performed period variation studies on BX3 using 80 times of minima from TESS and equal number of times of minima from other archival databases, and could see the period decrease with a superposition of sinusoidal variation, which could be attributed to the presence of the third body or Applegate mechanism, or it could be due to both as well. So we performed the period variation studies for the other 3 binaries as well using the test data only, as there was no other data available from the other sources. Here you can see the summary of the period variation studies performed for all the 4 flaring binaries. An attempt to attributing Applegate mechanism to the origin of magnetic activity in these binaries clearly showed that the value of quadrupole moment was insufficient for causing the observed activity. Hence, we are concluding that the presence of tertiary component could play a major role for the observed period variations. And because of this interesting fact, this work is under preparation for publication, and we are as well planning to send observing proposals for UV observations through the AstroSat. There is an abundance of photometric data available through Space Telescope databases to explore, and it is observed that studies of partially eclipsing contact binaries provides a poor estimate of primary parameters of binary system, their mass ratios especially, and which may lead to only an estimate of absolute parameters. So which can be reliably deduced only through spectroscopic studies. Now, but photometric studies of totally eclipsing contact binaries provide an equally reliable mass ratios and hence the resulting absolute parameters. So studying more number of such totally eclipsing contact binaries in short period cutoff range allows in building up of a robust stellar and binary evolutionary models. So with that same intent, we performed photometric light curve analysis of 61 totally eclipsing contact binaries and observed as observed through various ground and space-based observatories. The light curves of all these binaries are shown in these 2 slides. So here you can see phase-folded light curves of all the 61 variables, and you can as well see these are showing total eclipses. That means they are showing flat minimas during one or both the eclipses, where one of the component of the binary system is completely eclipsed by the companion in the system. The following tables here list out the basic parameters and the derived light curve solutions for all the 61 totally eclipsing binaries. Because of the totality, so we confirmed that the mass ratios estimated here are very reliable. So we try to see if there is any period mass ratio relation for the all the contact binaries which we have studied so far, including say other short period flaring binaries as well. We have included some of the short period flaring binaries as well, which are not contact binaries. So it clearly shows that we need additional data for any conclusive comments. However, the period color diagram plotted here in terms of T effective, along with the database taken from the catalogs provided by Pribulla, Sismedia, and Ibn Singh for short period contact binaries. This clearly shows the totally eclipsing contact binaries to be forming another branch below the SPBE line, the short period blue envelope line, which is seen as a trend in the catalogued objects. So we have obtained the mass versus radius plot. Here, the blue symbols represent primary component and the red symbols represent the secondary component of the binary systems. It is observed that totally eclipsing contact binaries clearly follow a trend both for the primary component as well as the secondary component. The primaries found to be existing between the TAMS and ZAMS, whereas the secondaries are evolved and they are existing beyond the TAMS. So we plan to go ahead with the building up of the catalog of totally eclipsing contact binaries by using available photometric data. And we would also like to use the multi-wavelength observational facilities being highlighted on this platform currently, both national and international level. And we would like to conduct a long-term correlation studies. And I would like to acknowledge various researchers and various ground and space-based observational databases for allowing us to use the data. And I would also like to acknowledge the support of my colleague Dr. Shantipriya and our team of research scholars, Raghu Prasad, Raviraja, and others, especially for extensively data mining their databases and for the selection of the totally eclipsing binaries. So, thank you for your kind attention, and I would welcome any questions on my mail ID as well as on the slide. Thank you very much.
Let's thank Rukmini Jagirdar for this nice recording. And as she has suggested, let's for the questions, please write to her on that email address. And now let's quickly move on to our next speaker, Dr. Sriram Kandulapati. He is from Osmania University again, from Department of Astronomy. Sriram, are you there?
Yeah. Yeah, Gajendra, can you hear me?
Yes, very clearly.
Can you hear me?
Yes.
Yeah. Yes. Can you see the? Yeah.
Yes.
Okay. Good afternoon. Good afternoon, everybody. And I thank the organizers for giving me the opportunity to present my work. I especially thanks Mamta and Muthu Mariyappan for wonderfully handling the meeting. Yeah, so my talks will be like very similar to Shanti and Rukmini, but I will be concentrating on the presence of third bodies in the short period binary systems. And these are my collaborators and the students. So I will not discuss much more about this short period binary system as it's been spoken about it. But I would like to highlight two things, that the light curves of the binaries are of particular interest because they show period variations. We can understand mass transfer rate, stellar activity cycle, and possibly the presence of third bodies. Of course, we can understand the mass loss because of the activity going on. And these systems are very, very important because possibly the theoretical model suggests that possibly they will merge to form mass transfer, to merge rotating stars, or they form blue stragglers. So about the third bodies, basically we use a method called O-C, observed minus computed method, to understand the long-term variation. This is the quick and easy method to know about the third bodies in the binary systems. And generally we model the O-C base using this light travel time effect, which is basically caused by changing the distance of a binary in the hierarchical multiple star systems. And nonetheless, this O-C, the observed minus complete variations, could be due to magnetic activity. Especially this is very important because if you are studying the later binary systems. So these are some of the graphs, some of the O-Cs, which I'm showing it to you. This is from Borkovich et al. 2015, using Kepler eclipsing binaries. You can see this is a contact binary where the binary system period is of 0.25 days, but the third body, if you assume that O minus C modulation is because of the third body, then it is the third body orbital period is 844 days. Similarly, for this system, the orbital period is 0.74 days and the third body period is 750 days. So this is the LTT equation. Basically, we try to fit this equation and try to get various parameters like eccentricity, true anomaly, eccentric anomaly. So this is the general statistics. So out of 2,600 Kepler binaries, 160 systems have third bodies with a period range from 95 to some 9,000 days, Borkovich et al. 2015. Hajdu has studied Coro database and he found that 4 eclipsing binaries, they show period changes as well as the third bodies in among 1,500 eclipsing binaries. And ASAS database, All Sky Automated Survey, close to 8,000 eclipsing binaries. Out of 17, 1,700 shows period change. However, the systematic search for third bodies has not been done. And very recently, Catalina Sky Survey, Papagargio et al. 2021 studied close to 4,600 eclipsing binaries and found that 100 eclipsing binaries show cyclic period variation. So what I want to conclude from this that 8 to 10% of the contact binaries or short period binary system, they have third bodies or possibly a stellar activity. Both are extremely important because the formation of these contact binaries or short period binaries are not well understood. How can you form such a low angular momentum configuration binary system? So third body is going to play a very key role. And of course, the other part is the stellar activity. We don't know the stellar activity cycle in many of the binary systems. Even that data is very rare among a single star also. So since few of these systems are often covered by various sky surveys, both by ground and space-based observatories, and they can be used to study long-term period changes, detect the third bodies, or constrain the stellar activity cycle. So this is from one of my work from 2016 AJ. Observations were made from JCBT, Indian Institute of Astrophysics 1.3 meter telescope. And this binary has a very small mass ratio. As Rukmini told, the totality shows that the accuracies of these photometric solutions are very good. And mass ratio is 0.06. Hardly there are 3 to 4 contact binaries of this mass ratio. Of course, this needs to be spectroscopically confirmed. We used the ASAS data as well as this is JCBT data. And we found a clear sinusoidal kind of variation. This could be possibly a third body with 8.25 years, which cannot rule out because Borkovich has analyzed a large sample and the time period by us and their time periods are quite well matching. This is another source, again observed from JCBT. It got observation from Kepler, and this we observed from Ayuka telescope also, 2-meter telescope, Ayuka Girwali Observatory. Here you can see clearly there is a difference in the maximas from 0.25 to 0.5. This is so-called O'Connell effect, and it's because of the particular cool spot, and because of this cool spot, there is a slight change in the magnitude at the maximum phase. And we modeled these light curves, and we found that considering a spot, we found that the correlated found that the spot radius is changing during the evolution of this light curves. We also performed the O-Cs, and again, you can clearly see if you consider LTT effect, the third body has a period of 16.23 days. There is a period variation of close to 10 power minus 6 days. Yeah, this is another source which we studied, again, Kepler database. We used various epoch times of minima from ASAS, KELT database, Kepler K2 database, and Hofscher et al. 2012-2015 and Lau. And we can clearly see that there is a period decrease and then there is a period increase, and period changes of the order of 0.13 seconds per year. And when we've used a LTT equation to find out the orbital period, we found that it has to be the third body has to have a eccentricity of 0.51 days with an orbital period of 8.66 years. Now, recently, we have been working on M67 cluster. You can see one of the image observed from JCBT. So these are all variable stars which are highlighted with a circular circle, and we are concentrating AH Canceri and EV Canceri. Both these AH Canceri and EV Canceri happens to be a member of this cluster. EV Canceri is very interesting because it is a blue straggler, and this is the phase light curve. Again, it has a very low mass ratio system, 0.1. So this is the O minus C. These are from the previous reported epochs. The last points are from Kepler as well as from JCBT. The period change is of the order of 0.06 seconds per year. And of course, we can calculate the mass accretion rate also, assuming that there is a conservative mass loss. This does not include the mass loss from the stellar wind. And this is the O minus C residual. You can clearly see a sinusoidal kind of thing. And if you, by fitting the LTT equation, we found that the third body has to be with a period of 42.21 days. These last two data set points are Kepler, and these points are from JCBT. This is again EV Canceri. It is a blue straggler in this particular M667 open cluster, not well studied. So we perform this. So we can clearly see that O minus C clearly show a period decreasing trend. That means the star is merging, which is quite good with the theoretical models of BSS. It strongly says that they are formed from a binary system and they merged at some epoch of time. And this is the change. We couldn't find any third body from this system. So right now we are working on one of this particular source, ASAS. It's a K-type source, K-type main sequence, period is 0.239. This is the ASAS dataset. This is the TESS dataset. So ASAS doesn't confidently shows any O'Connell effect, which we can say that there is a stellar activity going on. We analyze the TESS light curves. These are the TESS light curves. We can see that these are at different times during 2018 to 19 TESS observations. Here you can clearly see that there is a O'Connell effect, which strongly suggests that there is a stellar activity going on. So we think that it's because of the stellar activity, or it could be third body. We are trying to find out more set of databases which will fill in the gap of this and which will robust the orbital period, not the period of the stellar activity or third body. So yeah, we model these light curves with a cool spot on the secondary, because K types generally show magnetic activity, so they are very convectively active. So spots, the presence of spots is obvious, and we can clearly say that the spot radius is changing. Yeah. So in a nutshell, contact binaries or short period binaries are extremely important because they will try to understand what is the mass transfer rate, whether mergers are possible or not, whether third bodies are present or not. So they are the potential sources to detect the third bodies. As I told you, 8 to 10% of the contact binaries have third bodies. And one more important point is, since a low mass ratio system, the secondary has masses less than 0.15 solar mass. And for such low masses, the mass radius relation is still poorly understood. So these systems will really help us to understand the mass radius relationship. However, spectroscopic observations are required. So performing long-term photometry using JCBT 1.3 IAA, HCT 2.2 meter IAA, DFOT and DOT with Aries for studying these contact binaries will be very useful, and they will lead to a very important results. And with this, I would like to thank all of you to listen my talk. Thank you very much.
Thank you, Sriram, for a very excellent talk, and thank you for finishing well in time. And
thank you, Gajendra. Thank you.
Time for a couple of questions.
Yeah. Sure.
Yeah, Sriram, I'm Brijesh here. So
yeah,
when you say third bodies, this is a third body, or maybe some other components also? Are you able to say something on this?
Yeah, so basically, this is the third body which I'm showing you right now. But if you take the residual out of this, then again say there is a fourth component, but statistically they are not significant. Sometimes in some contact binaries, people report the fourth component also. Yeah, Brijesh, I think I have cleared the doubt.
Yeah, thank you.
Yeah, can I ask a question? Annapurni here.
Yes, ma'am.
Yeah,
Please.
so in your light curves of contact binaries, I don't know whether you can see them, but then do you see any indication of mass transfer?
Yeah. So this particular thing, for example, you take this O minus C. So this is a parabolic fit, and in parabolic fit, one of the term is mass transfer rate.
Okay.
So from there, you can get the mass transfer rates. For example, this JD naught plus PE, where P is the orbital period, binary orbital period. This Q is basically half of dP by dE. Okay, so dP by dt. And assuming that there is a conservative mass transfer, you can derive the mass transfer rate from these binary systems. Yes, of course, you can get the mass transfer rate information by studying these systems.
Yeah, but I'm saying that in the light curve, at what point of the orbit the mass transfer is happening? Because sometimes it's not continuous, right? So I'm just asking.
Sometimes it is not continuous.
Yeah, so in your light curves, is there an indication at what? Because some of the orbits are also not circular.
No.
Elliptical, right?
From the light curve, directly from the light curve, you can't say that there is a mass transfer. You have to do the O-C studies in order to say, in order to know the mass transfer rates. From the light curve itself, you cannot say anything.
Okay, no flare is not flare related to mass transfer.
What, madam?
Flare.
I couldn't get it.
Flare. You see some flare in the light curve, right?
You are
stellar flares?
No. We don't. These are not the flare. The sources which I have studied, I couldn't find any stellar flares yet, madam.
Okay.
Very few systems show stellar flares. Very few systems show stellar flares. More importantly, these contact binary systems, because of their very thick convective envelope, the stellar flares are very, very low in number compared to their single stars counterparts.
Okay. All right. Yeah. They don't have a common envelope, right? There's no common envelope. They are separate.
They have a common and very thick common envelope. Yeah.
Okay. All right. Thank you.
Thank you, madam.
Thank you, Sriram, for a very excellent.
Thank you, Gajendra sir. Thank you very much.
And now again, I thank all the speakers of this session for giving excellent talks, and thank you again. And I would like to pass it on to Mamta. Thank you, Mamta, for all your support.
Okay, thank you very much to all the speakers, and thank you again, Gajendra, for chairing the session since this morning and keeping up with the time. That's very important. So now we are going to have a 5 minutes break. I guess it's very much needed, and we can't extend beyond 5 minutes, I suppose, because we have a long day afterwards as well. So let's take a 5 minutes break and let's meet at 11:25 French time. So I guess we can just have a break now. Thank you, everyone. Hello, good morning.
Good morning, Mamta. How are you? Nice to meet you.
Same here. I'm so happy to see you, actually.
Yes.
It's really great that you could join and you're willing to give this talk.
Of course. I really look forward. Yes, I think it's been very interesting so far.
Yes, Oh, you have been following some of the lectures. I saw you.
Yes. Actually, yesterday I got them later on. Thanks to the YouTube channel.
Yes.
Because I had another meeting in the morning, so I could not join. But I think it's a very good idea the way that you have organized it. So
yeah, we're getting some good returns. Thank you very much.
Yes. Okay.
Yeah, getting some very good returns, even from the CNRS women department, like who are supporting women in research. So
that's very good.
Yeah.
This is exactly what you want.
I guess so, yes. And we have to like make it more visible.
Yes, more visible, and all action count at the end. So that's the important thing. Yes, of course.
This is why I think your presence matters a lot.
Well, thank you. I don't think that I'm, but yes, I mean, it's always important to talk and to keep talking. And I think that this, I'm very glad to see that in the end, instead of having one session all concentrated in one day where everybody's just running away, distributing a little bit across the whole conference. I think that it's really, I also tried in one general assembly of AIU, and it was received extremely well. People were, first of all, they need to talk about these things and to share. Yes. And, if you get a little bit every day, I think that it's just easier, and people then start thinking.
Yes, exactly. Yes.
Take home the message. Yes, exactly. Yeah. Okay, so maybe I should try to see if I can share my screen.
Yes, please.
Yes. So let me just go ahead and I will share this.
Yeah, perfect. You can see it.
You can see, and I just needed to make it just like that.
Yes.
And that works, right?
Yes.
So I can move and okay, very good. Okay, so I can leave it like this, or
yes,
I could, as you like it. I mean, it's.
Yes, I guess you may leave it like this. I think.
Anyways, short enough a break.
Yes, we have got still 3 minutes of break.
Yes, that's fine.
After your presentation, it's Professor Jocelyn Balbernal.
Yes, I saw your message, so I'm really happy actually. Yeah. Very good.
On the same day, so I think it's going to be great. Yes, she also tried to connect. She had some problems.
Yes.
But finally, she was so willing to again be into this meeting and to give talk and to support this whole idea that it's wonderful that she could join us. Yes.
She tried again, yes, for a different day. That's good also that you could accommodate that, right? Because sometimes it just doesn't happen. It's not so easy to switch around speakers, and yeah, excellent.
So just out of curiosity, are you going to talk about this, sorry, one moment. Yes, the European Platform of Women Scientists. Are you going to talk about that?
No, that I will not actually talk. I don't have it. I mean, it's a bit detached. I have some, it's one of the many, let's say, initiatives at European level. And at certain point, you cannot really be active in all of them.
Yes, yeah.
Otherwise you risk really to lose a little bit of the focus. So no, I'm involved in many other.
Yes.
But the European platform, I had joined it at the beginning, and now I'm just reading, I mean, whatever, their newsletter or journal and so on. It's, I think that there is a lot out there.
Yes.
And the EU has invested an incredible amount of money in so many projects.
Yes. Yes.
And yeah, I think that we are at a stage where it would be really important to evaluate a little bit, the effectiveness of all these actions. Exactly. Because I always have a feeling that it's very hard. I mean, it's easier to identify the problem.
Yes.
We are scientists, so we start collecting the data, we do our statistical analysis, we try to draw conclusions, we try also to suggest what could be way forward.
Yes.
But then, because of the time scales involved,
yes,
of course, it's very long term. You forget, you join the next project, you forget about the ones that you were part of 5 years ago. And, some of the results may appear only 5-10 years after that you started to change a policy. And I think that it's not being identified yet clearly, at least to me, a body
yes,
that is going really to see and say, yes, actually, this practice is really a best practice.
Yes.
And then I think that we waste time in the end, because we are always reinventing the wheel, because I'm sure that some projects that are starting now, they will tackle something that maybe somebody else has already tackled 15 years ago or 10 years ago.
Yes.
And, you know, the memory is being completely washed out.
This is exactly what we expect from IAU, right? To kind of keep a record of this and give people kind of package of whatever is existing and whatever they think is the best strategy that was followed.
Sure. I mean, IAU can do that. I always show something. I mean, the direction that IAU has taken, of course, it does not have any power on each single country, you know. So I mean, they cannot just enter and say you have to do that. So and that of course is the weak part, let's say, of the IAU, right? Does not have that type of power.
Yes.
But I think that it has other sociological powers. I mean, that they can use in a sense.
All right. So I think we are almost there. So,
okay.
So we will start with today's session then. Yes, we have people. So I'll quickly introduce you and then we can have the presentation.
Okay.
Okay, so again, good morning and good afternoon, everyone. And we are starting with our EDI session for today. And it is great to see that we have Professor Francesca Primus today joining us. And we feel happy and we feel privileged to have her because she is, first of all, she's giving the first talk of the EDI session for today. She is a professional astronomer at ESO in Germany. She's leading intergovernmental science and technology organizations in astronomy. And actually she obtained her PhD in Italy. And then she has been working in US for a while. And then she has been in ESO for quite a long time. Between 2006 and 15, she was the head of the user support department of ESO, and she is now a full-time observer astronomer, and she's a chair of the ESO faculty. Besides all these great qualities, scientific qualities, she is also the advisor of the executive committee, a working group of women in astronomy at the International Astronomical Union. So that's really great. And she has a vast experience. She's going to share us all her knowledge on this topic, which is so important and which she advocates. And she's also a member of the European Platform of Women Scientists. So that's another point, but I guess we are not going to hear much about that. And it's really great to have her. And we are going to listen to her talk about the Gender Gap Project results and recommendations that she proposes. So Professor Francesca.
Yes, thank you very much, Mamta. I hope that you are hearing me well. And I mean, you are being way too generous actually in your introduction. So I'm very happy and I really look forward to any type of discussion that may follow. And I'm very happy to present you actually the Gender Gap Project and the final recommendation that came from this project. I think that we have heard in the talks of the previous days actually a lot of interesting facts, a lot of nice presentations, and I'm not going to tell you anything extremely new because we do have this gender equality issue that we are trying to discuss openly and to solve. So I think that it should be clear by now on the fourth day of the conference why gender equality matters. And we can look at it at our own, in our own small group, department, institute, organization, but we can also look at it in not even only in the astronomy field, but in a significantly broader context. So, I mean, there has been tons of evidence right now of studies that have proven and show that it promotes economic growth, that actually teams which are better gender balanced, they are more creative, they enhance productivity. Maybe these things are not so important for astronomy, but I feel that actually creativity is one very important factor also of our work. And however, if you look at exactly in this broader context, if you look at some of the world leading economic forum, for instance, I mean, there are a lot of these institutions also at the United Nations level or other intergovernmental organizations that they do report, they do monitor every year And the most recent report from the World Economic Forum, for instance, you see, I mean, the titles are scary, right? I mean, so gender parity will not be attained for another 100 years. And I think that if you actually follow the last reports, I mean, these numbers, first of all, does not change. And if it changes, it goes in the wrong direction. So actually it keeps adding. So we are moving forward in time, but I mean, that number stays the same, or actually it gets larger. And if we look at economic participation and opportunity, so basically in very rough and simple words, I mean, the salary gap as we know it, it will take even more. So it will not be my daughter, it will not be my grandchildren, it will not even be my grandchildren who actually can hope to have that type of parity. Therefore, since I mean, we cannot simply overlook and dismiss one half of the world's available talent. And that's very simple to say, and I think that is common sense, and everybody would agree to that type of statement. And still, we are still here today, I mean, just talking about gender inequality and why it exists. And in the previous days, we have heard, of course, many of these, because, I mean, they're always the same culprits, I mean, that get into why we have gender inequality. I mean, there is stereotyping a lot, that probably we can try to fix it. There are implicit biases that is much harder to fix. We can only be aware and just keep that awareness, especially in the moments that we take decisions and that we talk and that we speak and that we educate our children, our students, and so on. There is a lot of discrimination, as for instance, Praival said yesterday, I mean, in her presentation, so it comes out more and more again, and always again and again, I mean, discrimination in the field, discrimination not only in astronomy, of course, I mean, broadly speaking. And discrimination has been actually considered by the United Nations, has been identified as a key barriers to enhancing the women's status. And after this Beijing Platforms for Action in 1995, the UN actually checked again the progress that different countries were making in this respect. And in 2005, actually, they raised already a red flag and say, here something is not going well, because actually the countries are not changing the discriminatory laws that they have in place at the pace that they are supposed to change them. Of course, I think that, to be fair, and we are all scientists, or we are scientists, and we like math, we like statistics, we like data, reliable data and reproducible data especially. So, you know, there could also be very well justified choices that women make at a certain point, and they just say, no, that's not the career. So maybe they study. We see that numbers have significantly increased at the level of education, of higher education, and then master, doctoral studies, university studies, and so on, where I'm not saying that we have reached parity, but I feel that in many countries actually we did. And still we are losing women along the way. Or we are losing them even before they enter the profession, so they don't even start with a postdoctoral path, career path, or we lose them then after they enter, maybe they get a junior professorship, and then, I mean, somehow they leave the field. So there can be personal choices, so it would be very important to complete actually this view and ask all the women who are leaving the field, I mean, for a kind of exiting interview, if you wish. Why are they leaving? Is it because, for instance, of lack of role models? Is it because they saw that, I mean, it's such a uphill path, I mean, to get anywhere, that they have better things to do in their life? They are very pragmatic, usually. They have all these different levels of empathy, and they usually have most of the caring responsibility. So they have busy lives anyway. So they can probably have a happy life and satisfactory life, even if they leave the field. So what's wrong with that? I mean, of course, this gender inequality, we need to understand. We need to be able to answer this question: why are they leaving, or why they are not getting to the field? And they can be different. So we could have a different talk actually only about this with different things. I mean, women are still the ones who are mostly taking part-time, and part-time is paid less. And that is going to affect, of course, the salary gap. And the wage and career penalties have been found about between -7 and -10% per child. That means because of motherhood breaks in the career. They have extra workloads. And let's not forget that, I mean, still today, I mean, there is a very different educational attainment between girls and boys. And therefore, I mean, girls are always behind, I mean, are always catching up. So Now, in all this gender inequality, let's say, discussion, right? I mean, there is something, of course, now I depicted probably a little bit too negative. There have been a lot of efforts, a lot of initiatives, a lot of also progress, I mean, that has been made at the national level, at the organizational level, and also at the unions level. So, I mean, you can expect that big bodies that represent a given professional or community, research community, like astronomy, for instance, and we belong to the International Astronomical Union, not all of us, but still it is our representative body, if you wish. They must have it on their agenda. It must have, it must be a top priority. And so you see that probably you know already, you're very familiar. So here are just a few data. I mean, the International Astronomical Union celebrated its 100th anniversary a couple of years ago, and it has about 12,000 members from 100 different countries, from PhD level above, and I will come back to that because that is a junior membership that has been open only since a couple of years. It has a very well-defined structure and is responsible for organizing a lot of scientific meetings. Therefore, I think that actually there is a very good area where we can make progress, from selecting, from calling the scientific organizing committee, invited speakers, and attendance, and having all this type of discussion as well. So here is just the numbers. So you know that the IAU keeps updating their numbers on a monthly basis right now. So the gender disaggregated statistics, and you see that the women are around 20%. And I think that this has been actually an increase, because 10, 15 years ago, actually, we were still around 12, 14%. So there is being an increase. And if you look at it, something that I've looked and look at this data recently, this is actually a distribution of the women, so that 20% in age beams. And you see that also astronomy, as has been noticed in many other fields, I mean, they do show a larger fraction of female exactly in the youngest beam. So there is the hope that that 40, 45, 46%, I mean, will continue growing in a sense, will continue moving along the career ladder. And here is a geographical mapping that I started doing several years ago and ended up in several IAU reports. And this shows, again, I mean, it's based on country, it's beams of female fraction. However, this is just to have a nice picture, a nice visualization, if you wish, a quick visualization. It has a lot of caveats behind. Like any other statistics or female or gender statistic, disaggregated statistic of the IAU, because the IAU does not represent, it represents the astronomical community, but it does not have all astronomers members of the International Astronomical Union. Therefore, 12,000 members does not, we do not know actually how many astronomers in total exist in the world. And the caveats behind this map is indeed that some countries have thousands of members, some countries have 2 members. And if that 2 members, 2 females, oh no, actually there is no such a case, but there is 1 female and one man, and 1 male, then of course you are already immediately 50% counted in these gender disaggregated statistics. So of course it has significantly less value than looking at a member state or a member that has several hundreds, or at least, or maybe thousands, and where it's probably a little bit more representative. Okay. So I must say that in all the years that I've been collaborating with the IAU on these topics, the engagement in equity, diversity, and inclusion has been extremely strong and growing. And this is a very positive fact, I think. So the Astronomical Union has been discussing actually gender inequality and lack of women in key positions in the astronomical community since the end of the 80s. So second half of the 80s. And they already held a meeting, which was very well attended in one of their general assembly at the beginning of the 80s or beginning of the 90s. And then they formalized this need to discuss and to pay attention to these aspects by founding, basically by supporting the creation of a working group that reports directly to the Executive Committee on the Women in Astronomy. And that was back almost 20 years ago. And at the same time, 10 years later, I mean, a working group more focused on equity and inclusion. and especially for to give voice and research accessibility to underrepresented groups. Of course, one could say women are the most populous and of the underrepresented groups, but this is really, they work a lot for research to increase research accessibility for people, for instance, with different levels of disabilities. Okay. The two major projects that IAU did in the last few years, the most recent one, I mean, there is a gender gap project that I will be talking about, and there was a full symposium dedicated to astronomy for equity, diversity, and inclusion, organized in Tokyo in 2019. There is also the strategic plan for the current decade that has several areas of interest identified, several goals, and inclusiveness is one of the main and most recurring words in all these goals and strategies that the IAU is trying actually to enforce. So let's go to the project. That was a significantly more global project, not only for astronomy. It's very hard actually to run these projects on its own and just per union. I mean, you can do something. Here is really, it was a very ambitious interdisciplinary project that has involved several unions in different STEM fields. And then we were joined, as you can see here on the right side, all the members, and we were also joined by UNESCO then, and the Organization for Women's Science in the Developing World, and Gender Insight, so not really unions. All the others were chemistry, computing machinery, mechanical engineering, biology, astronomy, physics, and so on. So the idea was, this was a project approved by the International Science Council in response to a call for grants that they issued back in 2016. And it was to provide, our project was indeed Gender Gap in Natural Science, how to measure it and how to solve it. Again, very ambitious also the title, I would say. It was to provide reliable data. So what we said was that we would have provided reliable data, therefore evidence, and a set of recommendations for implementing better policies and starting new actions, and then a collection of material, useful material, especially for what concerns initiatives. So as you can see, this joint global survey of scientists was really a major part of the whole project. It was a continuation, if you wish, so it was an expansion of the 2010 UPEP, so the Physics Union survey, so that the American Institute of Physics, that they have their statistic research group and unit, could continue and could monitor the data and could compare the data, at least for the Physics Union, to the 2010 survey. It reached outside the academic world, so we wanted the targets were working, have worked, or were educated in STEM. So everybody, even people who are not working anymore and left. And we got a total of 32,000 respondents, a little bit less than what we were expecting, and a little bit less than 10% from astronomy. So here you have a little bit of more information about the data. So how they were split according to geographical region. You see that Western Europe actually scored very well. There were 68 questions, so extremely long. And it was organized in 6 sections, and following basically the people from the very early years, asking even basic questions like, I mean, who really made you interested in science, to university studies, doctoral studies, then career development, work-life balance, and then people could have left, I mean, they were encouraged to leave comments and other items and other issues that they may have had. They followed, the snowball sampling, which means that just because actually we do not have a complete list of all astronomers, all physicists, all chemists, in the world, especially even since we wanted to target not only the academic world, but also outside, so even the industrial world, if you wish. Therefore, this means that the results are not statistically representative of the intended population. So I cannot say that this is representing the whole astronomical community. We can only say that based on the respondents, these are the trends that we are noticing, and that's all. The analysis has been quite complex, I would say, even for the statistical research unit at the American Institute of Physics, because of course of all the different disciplines, all the different geographical areas, different languages, because the survey was translated in 7 languages, which means that also the results had to be then retranslated back in English for them to understand and to try to put together all the results. It was done first, and this is what I will show mostly, with bivariate analysis, and specifically considering only the gender differences between men and women. And then you can also do that by discipline, by region, by Human Development Index. I will come back to that. And then the next step is to try to identify, to account for potential confounding factors with a multivariate analysis that is coming. I mean, there are some preliminary results. So I also had to make choices, very tough choices on the graphs that I want to show, because there is so much material out there that it's not possible just to go quickly through all the different aspects. So I chose career progression, discrimination, salaries, and harassment, because I think that these are very important. And for the numbers, I will mostly show women versus men. So very simple, mostly for astronomy. So all the white and blue and white graphs are basically for astronomy. And a few of the graphs that I will show you are across geographical regions, and then I will get back to this Human Development Index. So let's start with career progression. One of the questions was to compare your own career progression against colleagues that you know that have finished the studies more or less at your similar times. So that you have had the same number of years, let's say, after the studies. And you see that from these, probably the questions was not formulated in a very interesting or intelligent way, if you wish. I mean, so I think that the answers that we got, they were not very informative. It was a perception that actually more or less, you know, that there is a kind of distribution and same distribution between men and women. They answer more or less similarly. There are not major differences. However, when the people were asked what was the impact of parenthood on their career, as we have already seen and learned also this week, I mean, right? I mean, that is extremely strong. You see that the graph changes completely. I mean, you have very high female bars answering up to almost 40%. And astronomy is actually, this is across disciplines, as you can see at the bottom. And astronomy is where there is the highest percentage of women who have declared that they were slowed down by parenthood. Compare. But you see that more or less all the fields, they are more or less at least at 30%. If we look at discrimination, and this is discrimination by gender, there are other factors that have been taken into account. The second important discrimination factor is age, and then many others, but they have significantly less impact. So have you ever felt discriminated in the assessment of your achievements? Yes. And you see that for astronomy, the percentage is very high, is about 56%, 57%. We are not the highest, so we are not really the worst among all the disciplines. Again, please be reminded, this is just among all the ones who identify themselves as astronomers, or who have studied astronomy, and they answer then this question, I mean, and is not representative of the whole astronomical community. The range across disciplines, so if I were to show the across disciplines like the previous plot, I mean, what you would say is that the female fraction that said that they have been discriminated because of their gender ranges between 45 and 62%. So there is at least 45%, almost half of a fraction of women who said that they were discriminated in the assessment of their achievements. The highest are in astronomy, computer science, and physics. Okay. Now, if we look at across geographical regions, you see that again, I mean, the bars, the green bars are always significantly higher than the little, small, and low orange bars that represent the male responses. And you see that we have North America, North Europe, and Oceania. So among significant, I mean, they are highly developed countries with well-structured university educational systems, if you wish, and, you know, with lots of opportunities. And still, I mean, we do have this incredible discrimination issue. If you ask the reverse question, who never experienced discrimination, of course, I mean, the bars go up and down. I mean, so they are completely reversed. So let's go to salaries, the perception about salaries. This is also, for instance, versus colleagues with similar qualification. That is a difficult one. Again, probably was not formulated at its best because it's your perception. You don't usually ask your colleague how much money you're making in order to give a proper answer. But I think that the bottom plot is significantly more informative. So when you are asked about, how you compare your salary versus your partner, there, of course, you have significantly more information, detailed information. And you see that there is a higher percentage of women who says, actually, my partner is making more money. And one thing that I would like to make you notice on this plot that I added on the rightmost side of a graph, you see that the percentage of the people, how they answer to the question, my spouse is employed or not employed. And there again is something that is indicative, right? I mean, so there are more female spouses that are actually not employed, but they just stay home. Not to say that has anything to do specifically with the salary, that is something that just tells us that, again, something that we know already, that more men are with a job, in the job, and more women tend to stay home for whatever reasons. Of course, I'm not saying that the women are all at home just because they've been kicked out or because they had issues. And finally, let me touch about harassment, because I think that harassment is an issue that we need to face and we need to discuss and we need to find actually a solution. I think that these numbers are too high. And you see that at the questions, if you have personally experienced sexual harassment, not only harassment, at school or at work, I mean, we get basically 30% women saying yes. And that I think that is unacceptable. And we need to do that. I mean, in the last years, I mean, of course, we know that there is a problem. The problem has started to surface, also to get press attention in the last few years. There are a lot of reports from different universities, also very important and leading university across the globe. So it doesn't even depend on geographical regions too much. Harassment is there, and we don't really have, I believe, the tools actually to handle that, because I think it is very hard to get the people to speak up and talk. Even witnesses are not actually. They don't feel comfortable in speaking up and denounce this type of behaviors. There is a similar disparity between women and men across geographical regions, and also I would say, I mean, that is a kind of average of women 30%, and there are very few fields in which that fraction is significantly, actually there is no discipline where that fraction is significantly low. Now, here comes in the Human Development Index that I wanted to touch upon. This is a composite score that takes into account different aspects from health, education to standard of living. This is the UN, so the United Nations HDI, and they have 4 different levels: low, medium, high, very high. Here for this project, we just coupled the low, medium, and high, very high. I'm not saying that this is actually representing the ultimate truth about actually if you are developed or not developed. We have discussed with a few representatives from few countries, said, well, but that does not match actually my country. Okay, but this is to show actually specifically here for the harassment that there is no really a very strong difference, at least to me. Okay, in the less developed or in the more developed, I think that actually the fraction of women declaring and denouncing or saying that they experience sexual harassment, I mean, is way too high. So for me, that is a problem that affects basically the whole globe. So let's get to the findings. And so the finding is, of course, a little bit depressing at first, but I think that we can deploy some actions in order to try to reverse. And we do have a lot of initiatives going on and also some progress. But just to look at face value of these numbers, even if they are not statistically representative of their communities at large, I think that the basic finding and the basic conclusion is that the gender gap is real in science, and it is true, and it is so across all regions, all disciplines, all development levels. I mean, so there is not such a big difference to say that regions or that country or that discipline actually they are doing very well. No, that's not the case. And women reported more difficulties overall compared to men, and in terms of more interruptions in studies, lower pay, more instances of harassment, as we've just seen, more discriminations, lower career progression. So the recommendations are, of course, they are all based on the same type of pillars, if you wish. So, you need to raise awareness and keep raising awareness, and educate the people to talk about these things and to make them understand, to present data, of course, always with reliable data in your hands. You need to promote women, to promote underrepresented groups with events, giving visibility, but also try to look back where the people, where the children, where the girls or the boys become biased, becomes gendered in their views of the world. Actually, it's very, 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 very early on. Therefore, I think that we need also to look at school study material, educating the teachers. There is still a very strong gender imbalance among the science teachers. They are mostly men. There are no role models from that point of view, right? We need to actually, I will come back now in the next slide. And then, I mean, there is something for organizations, because these recommendations of this project were done for unions, for organizations, for educators, and even for parents. And the change, of course, here in the yellow box, I mean, it is for organizations, for institutions, for unions, to try to look at their hiring and promotion policies and procedures, how to best account for career breaks, and how to handle the harassment cases. And just let's remind, this is not a women's only problem. So the other day, actually, I played the game, as I always play at all meetings, especially when there are talks about EDIs. I mean, how many men were in the audience and how many women? This is not a women's problem, okay? We should not try to fix the women. There is nothing to fix, actually. But we don't even have to fix the men. I mean, that's not the point. I think that we need actually to be able to develop an allyship. We need to have more men involved and supportive and discussing with us, also from their point of view, in order to make progress. And otherwise, it will always look like a women forum where we all discuss and complain sometimes, because this is the feedback that I get sometimes. Oh, you're always getting together and complain. If we go a little bit more in details, I mean, so here you see that there is a list of more detailed recommendations for the different levels, as I said. So for unions, of course, unions, we have to remember that unions cannot impose anything on their member countries. Therefore, they can just act by example, and then hope that some countries will follow those examples, and the ones who do not follow actually will feel so bad that they will follow, they will start following. So it's a kind, again, it's a snowball effect, right? I mean, so you try, or a cascade effect, if you wish. But I think that the IAU is on the right track, and for sure they have this EDI, I mean, on the top of their agenda. For organization, they can do more. There is a clear, for instance, indication that each institute should have a gender equality type of officer. So really a person, you invest on a person who deals only with that. Because even if you have a committee, the committee is done of people who have their own job, and then they have actually to tackle this type of problems. And the progress is extremely slow, even in my experience, because of course, it comes always out of your free time or the very little time. And I think that if we are serious about it, then you need to have really people devoting full time to this type of initiative projects, evaluations, and so on. And then, of course, the parents and instructors, I think, because of what I said, I mean, the bias starts and the stereotype starts very early on. So we need to minimize, and especially to address the negative self-perceptions of girls. And we cannot just ignore them. We know that they are there. So the teachers have to be prepared and instructed and educated in order, so properly trained, if you wish, in order to talk about this negative self-perception and to change them, and to bring back actually a significantly stronger and higher self-confidence. Now, the effort does not stop just because the project has stopped. The unions actually thoroughly enjoy to discuss together and especially exchange information about the successful initiatives, which is exactly what we were talking before with Mamta. I mean, that we are missing this closing the loop after all these initiatives. So they thought about setting up, it is already set up, a standing committee for gender equality in science. There are all the unions, but there are many more unions, not only in STEM. So we're talking about the Union of Physiological Sciences, of psychology, or geography, and so on, where there is a platform where you can really discuss this type of topics, try to improve. I cannot say how successful that will be. We will see. I mean, it is about communication, to keep a channel open in order to share frustration, but also a lot of successes, hopefully, in the future. So basically, at the moment, they support 3 projects. The Gender Gap in Science, which is a closed project, is finished, but they want to follow up, and I think that is the right way to do it, the implementation of all the recommendations. Because otherwise, if you let each union to do its own job, I mean, you will never know actually if they did something, or if they just put it under the carpet and just forget about it after a few years. They are sponsoring and participating in the organization of a symposium on gender gap in science, which will be part of the next History of Science Congress. And they are also supporting the gender equality event for the International Year of Basic Science for Sustainable Development that is next year, 2022. And finally, especially for the IAU, you know that this is the outcome of a symposium that I mentioned before, that it was on astronomy for equity, diversity, and inclusion. So there are actions for IAU, there are actions for IAU members, and also for individuals. So I think that sometimes when I get attacked or let's say questioned or challenged by somebody in the audience asking me, so we are still talking about gender equality, aren't you tired? This means that actually all the initiatives are not working because we have been talking for decades. I think that each of us can do something. I mean, it's very hard for a union like IAU, actually, yes, they can lead by example, but then they need to, they don't have the power. But I think that each of us in our even small group of 3 people or 2 people or 5, 10 people, our organization then is the next level, or department and then organization. I think that we can work together. We can change things. We can bring up these topics and discuss them. Okay, and very, very final. This is an initiative by ESA, so the European Space Agency, by the IAU, by ESO, so my institute, and by SKO. We have launched this project on space science and astronomy research accessibility. This is not specific to gender equality, so seen as, you know, try to get a better gender balance, but it's really just to open up, to try to see what we can do in order to make our research field more accessible. And it's dubbed as SARA. We had our first meeting in November last year, and we hope to have actually the main meeting towards the end of this year. And I believe that with this, I will thank you very much for your attention.
Okay, great. It was a wonderful talk with lots of information. And I think that's the way to present really the whole, the core of the problem via statistics, via all sorts of problems which are addressed and which are not addressed and hidden sometimes. And all sorts of efforts and big effort that is needed at the very grassroots level and even at the top level, and being connected. So it's a great project. Thank you very much, Professor Francesca. We have a few questions. So first one coming from Firoza Sutaria. Yes, Firoza.
Thank you. Okay, so Francesca, I was really fascinated by your presentation. Thank you very much. It was very good. I'm really interested in the segment where you say that 30% of the women claim sexual harassment. That's astounding and appalling. But I was wondering if your questioner also asked whether women scientists have faced non-sexual harassment, especially from their peers and senior peers who might, out of jealousy, etc., or just fear of losing their own seniority, whatever reasons, drive vilification, dishonest claims against of data misappropriation, etc. Was it only was the question only biased towards sexual harassment? Was there no other kind of harassment the women scientists were supposed to have experienced?
So I believe that there was, and I apologize actually if I don't remember exactly all the 68 questions, because I mean, sometimes when you put all together, so I apologize for that, but I can look up, and come back to you and get back to you. But overall, I believe that there was a general questions about harassment, and then you could interpret it. And I believe that there was, for sure, there was a text box where people could have expressed actually what type of harassment. And I would need to go back and check exactly what are the percentage and how male and female have answered these questions. And here I'm showing sexual harassment also to be a little bit provocative, because I believe that that is coming out as an issue.
Sure.
I mean, I'm aware of some reports also in Australia, from some campuses and some universities. So, the percentages are there. And I think that we better also in North America. I've been discussing with many colleagues, and we need to do something about that. This is, of course, does not make the field very attractive, especially if it gets press attention and too often, because then people could.
The point I'm making is that harassment need not necessarily be of one kind, and it is entirely possible for the aggressor to belong to either gender.
Yes. I think that this is probably true. I would expect as well, like you, I would think the same way. Yes.
Okay, thank you very much. Thanks.
Any other question? So I just have a very naive question, and perhaps not really, but I mean, kind of consequence. I want to know what are the consequences of the actions that we take. So you show in one of your plots that the women who are having children are the ones who are kind of laid back, financially dependent, and all sorts of problems that they can face related to their kind of slow back in their career. So what if the next generation women pick up the idea of not having any more children and just pushing themselves, especially astronomers, in the career, and the smart astronomer ladies, intelligent ladies, stop making children and push the career?
Well, I think that would be very bad, actually. And in Italy, actually, we are already there. So we are already saying that if women do not start, I mean, not astronomers in general, we have a very low natality fraction and percentage. I think that is not the right way of going. I still hope that organizations and institutions and university will start changing. There is, I do not know if you're aware, I mean, there is this DORA initiative from the US, but there is a lot of Europeans as well, I mean, involved. And that is actually a charter, a platform, a forum, a discussion forum where they are trying to change, for instance, the way that we evaluate peers, our students, our, you know, when promotions and so on, right? So it has to come from different aspects. That, of course, it looks like a mountain in front of you. You do not know sometimes, you know, where should I go from which side should I start tackling the problem? But we need to tackle it. Sometimes you have to go into completely blindly, in a sense that doesn't matter if I hit my head against the wall, but I'm sure that if I continue, it's like making a tunnel in a mountain. I will see actually light on the other side at a certain point, because, I mean, there is no other way. I mean, we need to work on how we evaluate, how we account for career breaks. There are still too many, way too many biases that we introduce, sometimes involuntarily, because, I mean, unconscious bias, as I said, I mean, we have it. I'm also having unconscious biases, and you just always need to be very, very focused and aware of your biases. And we need to act. I think that hiring, promotions, and evaluation of performance evaluation and achievements, that is something that has to go all together and be rethought a little bit, so that families can continue to have children and enjoy their children. And still, I mean, we have a better society and a better astronomical community, more creative, if you wish, more balanced under many other aspects as well.
Yes, thank you very much. That's exactly the answer that we expect.
Yes,
but it's good to.
It's a long way to go, probably, but still.
Right, we have a question from Professor Ani Puni.
Yes. Yeah, I'll be short. I think there is, I mean, we are running behind schedule as well. So actually, relating to what Mamta raised, I kind of think that it may be quite required to have a mentor group of senior women to actually guide young researchers through, because there would be certain questions one would be asked, having in the mind, but wouldn't know where to, you know, brainstorm it and ask and see how things may turn out to be. So even when you are taking a step regarding your increasing your family or expanding your family or having a dependent at home to take care of things, etc. So there are so many questions comes to your mind, you know, and also goes into kind of, it just eats up your a lot of worries. It adds to your worries. Am I going into the right direction? Am I sacrificing something? Okay, so these kind of things, a lot of questions come to your head. So I think it's quite nice, will be nice to have a you know, mentor group to kind of counsel or at least address certain things so people can actually openly discuss. So is it part of the plan or in any forum to have a mentor group?
I could not agree more with you, and I will tell you also why. Because what I'm noticing, for instance, at ESO among the young generations, is that sometimes when you talk about some of these aspects, they look at you like if you're coming from Mars, or those things were happening at your age when you were young, or now that you are in your age, and so on. And I think that because we have raised the numbers of, and we have a better balance, gender balance, in the young generation, so where they get out of a master of a high school, or they start university degrees, they have in some fields, in some STEM fields, they even have parity, even getting PhD degrees, they think that actually there is no problem anymore. And what I fear, for instance, if there is not this communication between the older generations, the more senior generation who have experienced some discrimination and some issues and very strong challenges in their career, if there is not this communication flow with the young generation, I fear that they think that the problems have been solved, but they will face them in 10 years from now, where maybe actually we will be retired or we will not care anymore. Maybe, I mean, I do not know, I mean, about this. So I think I see this as a major problem to tackle, or one of the aspects to tackle. I'm not aware of setting up a specific senior board, let's say, that this standing committee for the gender equality in science, of course, is all senior people. There are no young people part of it. But one could think about try some initiatives where you try to have a forum, an extra forum of female senior scientists around the world, because I feel it is extremely important also to go by geographical areas, because the problems that you may experience in your society may be different from my society. And I may need to tackle different things, but we need to bring these generations together and discuss and continue discussing. On the other hand, there are some initiatives that are setting up, for instance, training for career development training. For instance, I'm part of an international network that is looking at gender equality plans in physics. And we are finishing up now a module of career development training that we hope to give at different institutions and so on. So, and that of course is the place also where to tackle, right? I mean, maybe this training actually should become part of a curriculum of every student in STEM, for instance, right? I mean, a university should discuss this. They should prepare on many different aspects, not only about gender. I'm talking, I mean, there can be many challenges in an academic career, right? And also different careers that can open after the degree. So thank you very much for your point. I agree.
So just a quick note, we did started it at Leo University, where we were meeting with all the lady professors from various departments, medicine, engineering, pure science, and we were actually having this kind of discussions. Yeah. So maybe it could be a platform to extend it further and make it better. Yeah. Maybe I'll try to get in touch with you at one point.
Of course, more than welcome, actually. Yes, thank you very much.
Okay, thank you very much, Professor Primus.
Yeah, no, Professor. You can just call me Francesca. It's enough. Thank you. Thank you, Mamta.
It's great to have you, and we can go on talking, but I think we'll have to stop.
Sure, yes, and I look forward to the next talk as well. So.
Yeah. So let's go further. I'll hand over to Professor Aniponi, and then I'll give a brief introduction about Professor Balbana.
Yeah, so good evening, and we are very thrilled to have Professor Jocelyn Bell-Burner with us, and I'm very happy that we could sort out the issues and we can have her on board. And welcome to you. And I don't think she needs any introduction to this audience. She's a trailblazer as a researcher, working tirelessly in science, public initiatives, as well as education. And of course, she happens to be a woman astronomer. I would like to put that way. So I last met her just before the entire world came under the COVID thing. We met in Chiang Mai when she was there to inaugurate the Astro Park, and she was a special invitee of the princess, Thailand's princess, and she gave a wonderful talk and mesmerized everyone as usual. So happy to have you. And before moving on, let Mamta introduce the speaker. Thank you for joining us. Yeah, and fitting in your busy schedule.
Thank you very much, Professor Aniponi. So just to go further to add to all these wonderful talking that we are having, I'm very excited actually to introduce you all, Professor Bell-Burner, and I thank her a lot for coming back again, and because I've been writing her many emails, and she's a very busy lady, but she has been always replying. So she's very modest and kind in that sense. So it's a great honor and privilege to have Professor Jocelyn Bell-Burner today with us, who's going to talk about women in astronomy worldwide. She is a true role model, much to be admired. Not only has she made groundbreaking contributions to astronomy, but has supported the future of science by generously helping young people who may feel marginalized to work in the field of physics. So that's amazing. I'm sure all the radio astronomers know her. We have all read about her in the Radio Astronomy second edition book by John Krauss in the 9th chapter on pulsars. When I started my radio astronomy studies and when I saw her picture in this book, it made a stamp on my mind. And I turned all the pages to see if there were many other women photos, but there were none. So that's exactly what I remember about it. And that makes an impact indeed. So I'm sure all the radio astronomers know her. For those who don't know Professor Belle Werner, let's give a brief summary. So as a postgraduate student, she discovered first pulsar in radio astronomy in Cambridge, 1967. She was credited with one of the most significant scientific achievements of the 20th century. Their discovery was recognized by the award of 1974 Nobel Prize in Physics that was given to her supervisors, despite she being the first person to discover the pulsar. She has held many different roles in different branches of astronomy, working part-time while raising her family, and stands out today as the true role model for many young women working.
Okay, or do you have any suggestion?
To have a career in astronomy. She is now a visiting academic member of Oxford University and Chancellor of University of Dundee in Scotland. Professor Belle Werner has served as the President of Royal Astronomical Society from 2002 to 2004 and President of Institute of Physics from October 2008 until October 2011. In 2015, she was appointed as the first female president of the Royal Society of Edinburgh. She is among the small set of women who have set up Athena Swan Group, a framework which is used across the globe to support and transform gender equality within higher education and research. She has received many honors throughout her career. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics. Following the announcement of the award, she decided to give the whole of her £2.3 million prize money to help female, minority, and refugee students seeking to become physics researchers. The resulting funding scheme to be known as Belle Werner Graduate Scholarship Fund. So that's why she stands out as a true role model for everyone. Being a lady astronomer, she has added the sensitivity in the workplace towards public appreciation for research, and understanding of science has always been important for her. She's always in big demand as a speaker all over the world, as we have already heard, and she likes to, in her spare time, do gardening and listen to carol music. We are really delighted to have her with us today. And Jocelyn, looking forward to your talk and to hear you. Please unmute yourself.
Thank you very much. That's a very generous introduction. Let me now bring up my PowerPoint. So can you see a PowerPoint okay, folks?
Yes, it is working. We can see.
Great. Thank you very much indeed. Francesca may already have covered quite a lot of this, I'm not sure, but perhaps I will have some things to say in addition to her splendid talk. So I'm using IAU data to study the number of women as members of the IAU. That's a proxy for women in astrophysics worldwide. And I'm also going to say a little bit about a UK initiative called the Athena Swan Scheme, which has, I think, is having quite an impact. So the International Astronomical Union, the IAU, back in 1990, the General Secretary was one Derek McNally from the University of London. And he was approached by a group of women concerned about the status of women in science, in astronomy, and could the IAU help or even take an interest? And Derek McNally's response, doubtless having consulted the president and other officers, was that the IAU sees the status of women in astronomy as essentially a social issue. And broadly speaking, the IAU doesn't think social issues are part of its remit. So no, the IAU was not going to take an interest in the issue of women in astronomy. Move forward just 7 or 8 years, The General Secretary is Johannes Andersen, who died just recently. And Johannes is a Danish man. His wife, Birgitte Nordstrom, also an astronomer, also in Denmark, although she's originally Swedish, I think. She was having tremendous difficulty getting jobs in astronomy in Denmark, whereas Johannes was not. And Johannes wondered if gender was something to do with this. And then he realized that as General Secretary of the IAU, he was in charge of the membership data. And the IAU has individual membership as well as membership of countries. And Johannes started recording the individual membership segregated by gender, male or female. And so there has been now about 20 years of that data. And it's using that database that I'll be talking about mainly this morning. Well, sorry, it's not morning for you, it's morning for me. So the IAU now has 14,000 individual members. The individuals are divided into individual and junior because it's created a junior membership basically for student age astronomy people quite recently. The data is recorded by the country where you work, not your nationality, and by gender. And the data is complicated because the individual and the newly created junior categories are frequently merged. Interestingly, the only gender question they asked was male or female, and out of 14,000 people, only 4 refused to answer that question. I think in future they're going to have more categories, but up till now it's been simply male and female. And so that is the data I've got to work with. So this is data that's about 9 months old as of June last year. I've looked at the data on countries which have more than 200 astronomers in membership. This is so that the root N errors are not too big. And let me just clear my screen a bit better. I've listed them in decreasing order of percentage female. So of the countries with more than 200 astronomers in membership, Italy tops the league with 28% female. It's not a very high fraction, frankly. France, 26, Brazil, 23, Spain, 22, Russian Federation, 21. The world average is 19%. That's over all countries, regardless of how many astronomers they have. The Netherlands is on the world average. And then, interestingly, comes a group of English-speaking countries. Australia, USA, Canada. UK used to be in that group, but UK has dropped down the list. India comes in at 14%, China 13%, Germany 13%, Japan 7%. I'm not surprised to find Japan low. I'm not surprised to find Germany low. There is some pattern to this, though, is there not? Southern European countries do well. Central and South America tends to do well. The English-speaking countries are a bit below the world average. That's really very clever because the USA makes up perhaps a third of the whole membership, a quarter maybe. So to be below the world average is quite an achievement. Japan, we're not surprised at. Russia has a long history of women working. In the world wars and with the flu epidemic, it lost a lot of its male population. So women have always had to work in the Russian Federation, and they've had lots of childcare arrangements as well. Now, there are probably some systematic effects in these numbers. One is you have to be nominated by your country's professional body. and that might be male dominated, it might have a bias. So it's certainly a filter. The data, always for the current year at least, is available on this website if anybody wants to go in and look in more detail. I think I've probably said most about the first two lines. I deduce from this distribution by country that the limiting factor is culture, and it's nothing to do with women's brains. This group probably didn't need telling that, but some groups do. There's believed to be a similar distribution for physics and for mathematics, but the international bodies there do not have membership in the same way as the IAU. So that's really only an impression. So what might be the cultural factors that bring up some countries and push down some others? One might be that astronomy is not perceived to be a very prestigious subject. The men are in the prestigious subject, engineering or medicine or whatever it is in your country, which leaves space for women to do a lot in astronomy. Maybe you live in a culture where you still live near your parents, and your parents could be a great help with childminding. Or maybe you live in a country where there's great disparity of income. There are lots of poor people. There are poor women who would be more than happy to come into your house each day, be your housekeeper, your cook, your laundry maid, your childminder, your cleaner, etc., while you, the wife, go off and be an astronomer. So there are probably a number of factors playing into this. I've looked at the changes over the last 3 or 4 years in the IAU data. And here I've looked at countries with more than 100 members. So there'll be slightly more danger of root N errors. The female world average has risen over those 3 or 4 years from 17% to 19%. That's progress. It's rather slow progress. It suggests it could be a very long time until we have parity. But there is also a complication in that the junior membership was introduced between 2016 and the latest set. And I believe the junior membership has led to a significant jump in the female membership. There's nothing, I'm afraid, we can do about that. The countries that have risen most markedly in the last 4 years are the Netherlands, which has almost doubled from 10% female to 19% female, Chile from 15% to 21%, India from 9% to 14%, and a number of other countries have risen by 3%. It's good to see the rise in India. I don't know how you've achieved it, but that's something you might like to reflect on. I asked some colleagues in the Netherlands how they had achieved this remarkable increase. And they weren't absolutely sure, but they said that for a limited time, they were allowed to appoint women only to certain positions, quite senior positions. And they believed that this had led to quite a change in the situation in the Netherlands. I'm afraid the UK has not risen at all in that period, which rather implies we're going backwards compared with the rest of the world, which is concerning. I've looked at the age distribution of members. So I have, let me get the laser pointer up. So I've done ages in 10-year blocks, 25, 35, 35, 45, and so on. And I've looked at the number of women in that age, those age brackets, and the number of men. And I've also given the ratio here on the right. The number of women peak here, quite young. I suspect this is due to the junior membership playing in, whereas the male numbers peak somewhere about here, perceptibly older. I wonder, is it two different populations? Because they do peak at distinctly different ages. And I wonder what issues around COVID pandemic arrangements are going to do to these numbers. I think we're clear that it's often women's careers that have been more affected by the pandemic and the lockdown. So I don't know how that's going to play out. What I also find is interesting is how this ratio improves even right up here. And given that on the whole, women tend to live longer than men, and so there should be more men dropping out of this category of age than women, the number of men to women is still the highest of the whole lot. I guess that's history, folks. I also want to say a little bit about what's been happening in Britain, the road to equality in UK universities in Britain. We now collect data. How many women, how many men are there at every level? And fancy this, it shows that women are in a minority. The minority gets smaller, the higher the level. That probably won't surprise you. It shows that women progress more slowly than male counterparts. Maybe they present themselves less forcefully. Maybe there is unconscious bias. It also showed that women were putting in fewer grant applications, were less willing to apply for jobs. If their grant applications were turned down, they waited longer before reapplying, and they always apply for smaller amounts of money. So it looked as if our systems favored the brave, promoted bravado. So obviously the solution is to fix the women, make the women braver, more willing to put in grant applications, more willing to apply for jobs, for promotion. And they actually set up special training courses for women to address these deficiencies. Now, there's a false assumption here. Just because the women put in fewer of this and less of that, it doesn't mean that the problem is with the women necessarily. It could be, indeed we now think is, with the way that science and scientific society is run. But for a while, there were these special courses because women were felt to be deficient. Another attempt was setting up special funding for women coming back after a career break, returner fellowships. And there were some things that were open to women only. And it was found that some men would say to these women returners, you only got that position because you're a woman. You're not up to the standard of the rest of this department. You should leave. That has actually been said. And when that got back to the funders, they realized that they had to make these types of funding open to both men and women. And now occasionally in Britain, well, more than occasionally, increasingly, men will take breaks when there's a new baby in the household, for instance. So we've learned not to have funding earmarked for women only, but to have funding that would be attractive for women in their particular career paths. But they also began to realize that giving special funding to women was helping those women, but wasn't changing the systems in the long run. And they began to look for what they called institutional change, making a place fairer for everybody, not just women. And I want to stress that structures can be sexist, even though the individuals working in that structure are not. You can have institutional sexism. There can be possible biases in recruitment or retention. There can be unconscious bias. And my favorite example of unconscious bias is down the bottom of this slide. Have you ever been asked what sex or gender you are? And you're given a choice of boxes. Originally, it would only have been male or female. These days, we include some others along the line of other than male, female, and prefer not to say. But look at these two. Why are they in that order? Does M come before F in the alphabet? That is an example of unconscious bias. We're used to seeing the male first, but it sends out a message that the men are more important. Men come first. And so one of my campaigns, whenever I get a questionnaire with this, is to send it back and say, I'm not completing your questionnaire because you're showing unconscious bias. And the organizers of the questionnaire come back a few days later, very sheepishly saying, we've looked very carefully at our questionnaire. What are you talking about? And I point it out to them. They say, oh, yes. Another example that can happen in Britain is when you're asking about the racial background of an individual. And again, there are some boxes to tick, and it starts white, black, other. Why does white come before black? That's not alphabetical order. Unconscious bias is very subtle, but I think it's important we call it out where we can see it. And the delight of finding an F box before an M box is great, I can tell you. So go for it, ladies, wherever you are. I want to say a little bit about a scheme that got set up in Britain to try and make university in general, but particularly science and engineering departments, more women friendly. There was a small group of women, you may know some of these, Julia Higgins, Wendy Hall, Jill Samuels, Caroline Fox, Nancy Lane, myself. There were 2 or 3 others, I couldn't find photographs of them. We would meet after work at our own expense in a borrowed room in London and try and think about what we could do to make life for women scientists, particularly in universities, but not exclusively, what we could do to make life better for them. And we struggled, I must say, until Caroline Fox, who's a bit of a psychologist, had a bright idea. She said, you know, university vice chancellors, they're all men. They were all men at that stage. We now have a fair number of female vice chancellors, but at that stage, they were all men. She said, men are competitive. If we create a prize for the most women-friendly university, they'll compete. Now, we were broke, but we could afford a glass rose bowl. So we bought a glass rose bowl and we announced this competition for the most women-friendly university. And Caroline was right. We had a number of submissions, not a huge amount the first year, but a number, and we awarded the glass rose bowl. And each year we ran the competition, it got bigger and bigger, and we got better at developing, you know, what we were looking for. And this became known as Athena Swan. After the first 2 prize-winning universities, one who had a scientific women's academic network, Swan, and the other who had a scheme called Athena. And we put together the best of all the submissions we had, and we created this Athena Swan Award. And we quite regularly awarded it. But it grew slowly until one day our Chief Medical Officer for Health was meeting with the heads of medical schools in universities. The Chief Medical Officer for Health holds research funds. And she had the discussion, the kind of discussion that a research funder has with heads of departments. And at the end of the discussion, just before they broke up, she turned to them and said, "You're all men. Where are the women?" And they said, "Oh, it doesn't matter." And she had, as she put it, a rush of blood to the head. And she said, "If you want to apply for my funding in future, you must hold Athena Swan Bronze Level Award. And when a funder makes that kind of statement, people pay attention. She forgot to tell Athena Swan we were puzzled by the sudden rush of applications from medical schools, but good that they got on with it. And we got it duly sorted. So Athena Swan then extended beyond the sciences to other faculties in the university. Arts and humanities is where you have to look for the men, not look for the women. And it's been taken over by Ireland, by Australia, by Canada, and it's coming in the USA in an enlarged form. It's not just gender, it's including the other dimensions as well. So that's enormously encouraging, but it just does show you need incentives, ideally financial incentives, to create some of these changes. Back to thinking about women in astrophysics. We are enabling more women to climb the ranks. But is it a bit like the way Ivy is a very strong climber here in Britain. I don't know if you have it in India. Ivy climbs up buildings. Are we enabling women to climb up the ranks like Ivy climbs up? But Ivy doesn't alter the building underneath. Are we enabling women to climb without altering the structures underneath? Or at least looking at the structures underneath and considering whether they might just possibly need a little bit of change. Have changed, and I finish with a little bit of encouragement. In 1930, the Earl of Birkenhead, a British nobleman, was stupid enough to make predictions about what the world would look like in 2030. In 2030, women will still, by their wit and charm, inspire the most able men towards heights that they could never themselves achieve. Yuck. And from the USA, in 1946, in the USA, 65% of people thought men were smarter than women, but by 2018, 86% think men and women are equally smart. We are making progress, folks. It's probably not as fast as any of us want, but I hope you're aware that the IAU have had its first female president, Evine van Dieshoek, and its first female general secretary, Teresa Lago. That's a good milestone as well. Thank you for your interest and your attention, and I will finish there.
Thank you so much. Can we have some questions? So we have first Firoza, your hands up.
Yeah, thank you. Thanks, Annapurni. Jocelyn, this is referring to the point you made about the IAU membership of women from India increasing to 14%. You were asking how was it done, and I can tell you a little. Hello.
Yeah.
Yeah, and this is what happened essentially. Yes, the number of women in India has been sort of going up for quite some time, but sometime around 2015, there was a definitive push from India to include more Indian astronomers in the IAU. You see, it's much more than just including the women. You will also notice that the number of Indian scientists overall, number of Indian astronomers has increased since that date. And that is because we, especially Prajwal Shastri, my senior colleague, and of course I and a few others, we actually made a concreted push to increase the overall number of scientists going from India into IAU. And that is exactly how you find that the true fraction, well, it's not really a true fraction, but yeah, the number of women scientists who had meanwhile come into the stream also were included when their CVs were forwarded to the IAU.
Good. Excellent.
So that's exactly how you got it, how you got the increasing number of women from India in IAU.
Thank you. Good.
Thanks. It was a wonderful talk, by the way. Very precise one. Just what I expected from you.
Up to nearly 50% of all the galaxies in the universe. So it is a very large population which we cannot neglect. And giant LSPs are a subpopulation of LSP galaxies with extremely massive disk. An example can be seen with the extreme case of Malin galaxy, which is currently known as one of the largest non-spiral galaxy. In the recent years, with the advancement in technology, there is a new interest in these sources, and giant LSPs or LSPs can be considered similar to XUV galaxies and also an ideal laboratory for the study of star formation activity in low density regimes. So in this talk, I will present a paper I published last year based on a new spectroscopy study of Malin 1. I used long slit spectroscopic data of Malin 1 obtained from the IMAX Magellan spectrograph in Chile. And despite the extreme faint nature of this galaxy, I managed to extract spectra from 16 different regions of this galaxy, including a region relatively far from the center at nearly 25 kiloparsec. And an example of the spectra I obtained for the central region of Malin 1 is shown here. And within this extracted spectra, I focused on the H-alpha and O2 emission lines, which was the strongest of all. And using these emission lines, I obtained a new rotation curve and made an estimate of the star formation rate surface density within this galaxy. So these are the main results of this work. We obtained a new rotation curve for Malin 1 and observed that for the first time, there is a steep rise in the inner rotation curve for Malin 1 up to nearly 400 kilometers per second. And using this rotation curve, we made a new mass model and found that in the inner regions, the dynamics may be dominated by stars, but at large radii, a massive dark matter halo is necessary. But in order to better understand about this galaxy, we need a good quality IFU data. One of the other results of this work is an estimate of the star formation rate surface density within Malin 1. The plot here shows a variation of sigma SFR of Malin 1 in comparison with different morphology of spiral galaxies. And in the inner regions, Malin 1 is consistent with an S0 or SA type spiral, but in the extended disk, it is within the level found for XUV galaxies. So the conclusion of this work is that something really interesting is going on within the galaxy Malin 1. And in order to better understand that, we clearly request large IFU observations. Malin 1 was recently accepted for MUSE observation, but unfortunately there was some delays due to the current pandemic. And a similar study can be extended to other giant LSPs and XUV galaxies in a broader context with Malin 1 as a prototype. I already created a sample of 10 H1 selected GLSPs or XUV galaxies for follow-up spectroscopic and UV observation. Two of this sample can be seen in the image in the bottom right. And also with the upcoming instruments like Blue Muse with its large field of view and high spectral resolution, it will be very crucial for LSP science, just like we heard from Johan's talk a few days before. Also with SKA, we'll be able to observe H1 in giant LSPs at 2 redshift 1. For more details about this, we can hear Samuel's talk later today. So I strongly believe that with deep and more quality data in the future, we will be able to uncover the origin of this giant piece. Thank you.
Thank you, Junas, for being in time. So now we can take one question, one quick question.
Sure.
Maybe you can check whether there are questions in Slack or...
Hello, Producer. Can I ask a question?
Yeah, please go ahead. Please go ahead.
Hi, Junai. Thanks for the beautiful set of data and for the work. It's very nice. I was wondering, what is the reason you have a very steep rising curve in the rotation curve?
Okay, here. So yeah, this is very surprising to see such a very large steep rotational velocity in the center. This could be maybe because of various factors. Because of the resolution of our data, or maybe it could be because of Malin 1 is as an almost face-on galaxy. So with an inclination of around 38 degrees. So within this rotation curve, we applied an inclination correction also. So if we have some uncertainty in inclination, that can also affect. the rotation velocity values, but we are not sure. We hope that we took that into account carefully. But that's why it is interesting to know that with better or high quality data, especially in the central part of this galaxy, to really understand what is really happening there. Is this high value, extreme values realistic, or something connected to our data? Yeah,
Okay.
did I answer your question?
Yeah. Thank you, Junes. Thanks for question.
Thanks.
Thank you for this very nice talk. Now we will move on to the next speaker, and next talk is by Somen Bera. I request Somen to put slides. Somen. Hello.
Yes.
Somen, are you there in the
Not
participants list?
He's not present, I think.
Yeah. So, okay. Do we have a talk loaded already or something like that? Is it not yet?
Just have a look at this again. Yes, so we had the presentation actually from Somen Bera. He is not present. And we have next talk. Actually, we can start with the talk series now. So that's from Ramnal. Yes.
Okay. So now we will move on to the next talk, which will be by Dharamveer Lal, and the speaker actually is a faculty at NCRA Pune, and he works on extragalactic radio sources, and so let us hear Dharam. Yeah, floor is yours, Dharam, please.
Sure. Thank you. Thank you, Brijesh. And I would like to take this opportunity to thank the organizers for giving me an opportunity to share this small piece of work. It's an exciting piece of work which I'll be sharing. And this is about study of classical radio galaxies at low radio frequencies. We are talking low, meaning 550 megahertz to 1750 or something like megahertz. And this piece of work is done along with Tiziana Venturi. And since I'll be talking about radio galaxies classification, this is also done along with Bernie Fanaroff, Oleg Smirnov, Marco Bondi, Chitish Thorat, and there are several more from the Sarau, South African Radio Astronomy Observatory, the developers of imaging tools. So I would start with the background, which I'll be building it up. So what you see on the top right is essentially a Fanaroff-Riley class 2 radio source, and top left is Fanaroff-Riley class 1 source. These are two classes of sources coined in 1974 by Bernie Fanaroff and Julia Riley. They were largely determined by how the radio jets propagate further ahead. So you have pencil beam radio jets, which hits the ambient medium to form prominent hotspots in one case, but whereas in other case, the jet dissipates as it moves in the environment. But both forms radio lobes. The right one is largely a high luminosity source compared to the left one. And if you take the left source, the Fanaroff-Riley class 1 radio source, and put it in a cluster environment, and because of the cluster potential, it is going to move around the bright dominant galaxy, and the two jets will trail behind. Depending on the angle the two jets make, you can call them as wide angle tailed or narrow angle tailed source. This is 3C129.1. 129 is an example of narrow angle tail radio source. And this is another wide angle tail source, which is the dominant radio galaxy. Are these the only flavors of radio galaxies? No, there are radio galaxies which are X-shaped or Z-shaped or S-shaped. And I'm sure my colleague Preeti is going to introduce some more phenomenology in this. These X-shaped sources are thought to be either due to merger or reorientation of jet axis or backflow from radio lobes all the way into the low diffuse surface motivation. So lastly, what I'm going to raise is I'll go back to the Spanner-O'Reilly 1974 classification scheme and ask a question. Are these morphologies like classification in terms of FR1 and FR2 sufficient in today's times also? I'm repeating this because in 1974, we were talking about just 200 odd radio sources based on which this classification scheme was formulated. But now with the advent of upgrade of GMRT or MeerKAT or ASCAP in Australia or the JVLA in USA, LOFAR in Europe, and forthcoming SK, this picture is going to change. There are billions of radio galaxies. And are these classifications sufficient enough for us? So we will be going back and asking several questions about these Spanner-O'Reilly class 1, class 2. For example, what is the duty cycle of nuclear radioactivity? What triggers it? And more importantly, does the sharp classification of FR1 and FR2 type still hold when we are improving our imaging capabilities? Or we need more morphological classification. We need to go beyond type 1 and type 2 sources. So to take this question, we essentially had to build little, like we also wanted to pick from 550 megahertz, which is the UGMRT band, 550 to 850 megahertz of UGMRT band 4, and we picked MeerKAT L band, which is from 850 all the way to 750 megahertz. We were particularly choosing this frequency range and these two instruments, lastly because they both give nearly identical angular resolution and identical depth. So sensitivities are identical, resolution scales are identical. So we wanted to pick, now our requirement was to pick sources which have identical structures so that we are not comparing apples to oranges, but apples to apples. So what we put in effort to is build the sample. The source should be spectroscopically identified, hosted by optical galaxy, and we put in nearby systems so that we are not limited by ability to map megaparsec scale. These sources can be as hundreds of kiloparsec and can touch many megaparsecs also. So we should be able to map them easily, and we should have similar fractions of these two classes. And something little technical, we also wanted to have our ability to map structures with both instruments in an identical manner at identical angular resolution. That's called UV coverage. So both should give identical UV coverage in this declination range. So we put in little effort, and we also wanted to make sure that we are picking sources where we can see structures and they are typical radio galaxies. And based on this, we performed a pilot study, 6 Spanner-O'Reilly and 6 Spanner-O'Reilly class 2 sources. And here I'll be talking about results for first 4 sources, 2 of each kind, using these two instruments, MeerKAT in South Africa and UGMRT in Pune, India. And we are covering all the way from 550 megahertz to 712 megahertz. I repeat, we have identical resolution, identical this. This upgrade of GMRT and MeerKAT instrument both are fairly new. So we put in effort to understand how our analysis coming along. So what this plot is showing the flux density as a function of frequency for UGMRT's measurements, which are at 700 megahertz, and MeerKAT measurements, which are at 1280 megahertz, and rest of the data points are built from literature. So we are consistent in terms of flux density scales, and we are not typical synchrotron spectra is what is seen over here. And these are our 4 sources. The black contours in these source, so background image is the DSS image, the R band. Black contours on it are from the MeerKAT L band, and the red contours are from the UGMRT band 4. And these are the 4 sources. What we're happy that we are seeing remarkable similarity, meaning we are achieving identical depth, identical resolution. So we are not missing out any flux density scale in any of the observations. And now we can revisit the questions which we are asking. So with this, I will move to talk about a little bit what we are seeing in this. So here, essentially what I'm showing is, my apologies. What I'm showing here is examples of 3 sources. So you essentially have sources where you see multiple hotspots. For example, top right is showing something like that. And bottom right is essentially showing 2 channels which are feeding 2 hotspots on the southern lobe as compared to northern lobe. Now you can ask, are these easy pictures? further on the bottom left panel, which is 4C 12.03, the meerkat image, where you see you have inner pair of radio lobes, additionally outer pair of radio lobes. These inner pairs were not seen earlier. So this is a new discovery in this source. So what we are seeing, this is not just an X-shaped source, probably there is an inner pair of radio lobes and outer pair of radio lobes. This could be a restarted jet activity or something on lines with double radio galaxy. Next, I want to move to spectral structure. So since we have such broad frequency coverage, we can look at the spectral structure in these sources, and I'm giving one example for this source CG044-046, where we are showing the UGMRT and meerkat. So 550 megahertz data, band 4 data, and L-band data, which has been divided to make spectral structure. Typically, you see spectral steepening as you move from inner core, which is an inverted spectra, and then you essentially have outer part of the tail where it can become very steep. And probably what you see in the top, this little panel over here is, if you look at the transverse direction close to the core, you see the top part, which is slightly flatter compared to the bottom part, which probably means that the source is moving in the cluster environment. So one part is compressed, another part is not so affected by the compression. And particularly with the meerkat data, where we had larger frequency coverage, both using UGMRT and meerkat, we can do this. I'm showing results only for the meerkat data. So what I'm showing is in-band spectral index. What is the, so what you have meerkat data, it gives you not only the total intensity image, it can also give you the flux density across the large bandwidth which it spans. And this is the in-band spectral index for 4 sources, which I'm showing over here. So what I'm showing here essentially is, in this source 12.02, I'm seeing something puzzling, like whole thing is fairly uniformly structured in terms of spectral structure. It's around -0.9, and not just the hotspots, which, so let me go back one step. The background image is the spectral index image. Superposed on it are the radio contours from the meerkat total intensity image. So ignore the radio contours. It's just showing this how the source is looking like. So if you look at the hotspots, which are where my cursor is, these are typically high surface brightness regions or flat spectral features, but these hotspots are of similar spectral index as the rest of the source is, with very little things, which probably means that the continuous injection of electrons from the core has stopped in this source. This is one possibility. Looking at this 12.03 source, here you have essentially core jet emanating out on north and south direction. It further forms eastern wing and the western wing based on the backflow. You can then ask a question, is the jet velocity sufficient enough to form hotspots and then further to form wing-like backflow? Or is it some other mechanism which is merger? So this is being debated. This is where this bottom right is another source where we have dynamic range limited. We are not able to map all the structures, but we see typical structure which is seen in classical radio galaxies, that the hotspots are flatter and the diffuse emission beyond, which is emanating from the hotspot, is steeper. In this source, you essentially see something along the same line, but the source is showing something more than that. Essentially, you have inverted spectrum core and then steep flat spectrum inner pair of hotspots, matter further diffuse. And then you see around this line, you essentially see a sharp transition from flat spectrum emission to very steep spectrum emission, and which further becomes very steep further out. And over here you have an eastern protrusion, which we call, which is very, very steep. So these are some things which to ask, and I'll try to answer for one or two cases. So I'll repeat, essentially, I'll take one example of this thing. So this left panel is a total intensity image. The right panel is the spectral index image. Contours are identical contours placed from one to another, essentially. And you can ask a question, how is the radiative lifetime or the magnetic fields, like equipartition magnetic fields are in various locations, northern hotspots, southern hotspots, or eastern wing and western wing-like region in this. So they are all comparable. The magnetic equipartition magnetic field. Subsequently, the radiative lifetimes are also comparable. And these radiative lifetimes are further roughly equal to the lifetime of the source. So which is surprising. And this is not the case that this should be flat and this should be steep. In terms of spectra, you see that, but in terms of magnetic field and lifetime of these regions, they are comparable. And if you go further lower frequencies, in the past, we have seen the bright hotspots, high surface brightness active lobes, which is northern and southern, have comparable spectral indexes if you go further down in the spectrum. So this is little unusual. Coming to the another example, which I was talking about, so this is inner parts are fairly flat, and then you have a sharp jump, and then eastern protrusion, which I mentioned, and matter for this radiative lifetime of electrons increases as you go further and further.
Dharam, you have 2 minutes.
Yeah. Okay, sure, I'm close to that. So you essentially have something similar, which I mentioned. This particular source is residing in a cluster environment. So when I was saying that the northern part is flatter compared to the eastern in the transverse axis, this is largely because you have several sources in the field of view which are clearly detected and have it's a rich group or a poor cluster environment. And this is probably the reason that the environment is playing a role in this thing. For this source, we also have polarization information. So what I'm showing you here is contours from the total intensity. The vectors which I'm showing is electric vectors. So the eastern lobe has less polarization compared to the western lobe, which probably is largely because the source is residing in a cluster environment and there is projection effect which is playing. So what you can say is one lobe is facing more of magneto-ionic medium compared to the another lobe. Hence you are seeing Line-Garrington effect. The eastern lobe is much more depolarized compared to the western lobe over here. And this is what probably is happening here. So now coming back to the question which I was raising, that you are now seeing complex shapes, you have very good depth. Is it worth going into much more variety of classification scheme beyond Faraday-Riley class 1 and class 2? So what we feel is, though we have very small sample, but what we feel is there's probably very little value establishing a more complicated morphological classification scheme. And thank you for your attention.
Thank you, Dharam, for this interesting talk about galaxies which are not so classical. I think new classification coming up. So the talk is open for questions. We can have 1 or 2 questions.
Dharam, I have a quick question. I just wanted to know if you have been also observing kind of Rayleigh emission around this these kind of galaxies with jet structure, because we have started to detect more this Rayleigh emission in the LOFA data.
Yes, thanks for this question, Mamta. You are right. Everyone is beginning to see Rayleigh emission, and out of these 4 sources, I anticipate the bottom left, this little source, to have some Rayleigh emission, which would probably seen only at 150 megahertz, the low frequencies, or band 2 of GMRT. And we have not explored that, but we believe there should be, because this is in the cluster gas environment. But whereas the other 3 sources are fairly field radio sources. And bottom right is where we can't do much because we are dynamic range limited. So we are still figuring out how to improve what we already have. Thanks.
Okay, thank you.
Yeah, any other question?
Yeah, can I ask one question?
Yeah, you can go ahead.
Yeah, hi. I was wondering about the polarization map. I can see when there is a bend of the jet, there is no preferred direction of magnetic field. Is it correct?
So these are electric vectors, which means magnetic vectors are perpendicular to it. And if you're asking a question, I don't see a preferred direction of, yes. So I would go by that. I haven't done much to it, just to more to say that the western lobe is much more polarized, has much more polarization flux compared to the eastern lobe. Now, asking a preferred direction, how the jet propagates will change the magnetic field, and that has to be taken into. And on top, I also mentioned sources residing in cluster, and there are projection effects. So it's a little tricky to decouple all 3 effects.
Okay, good.
Okay, so let us thank Dharam for this interesting talk. Now we will move on next. I think it's over to Mamta. Want to?
Yes. Thank you very much, Rajesh, for chairing this session and keeping up with the time. Thank you. So I guess the next person who is going to chair the session is Nirupam Roy. So we hand over to Nirupam if he's there.
Yeah, Mamta, thanks. Am I audible?
Yes, great. Yes.
Okay, excellent. So without, because we have a somewhat longer session today, going into quite far into the evening, let's start without. Speaker is Dipanjan. Dipanjan, can you please share your screen and let's see if it's.
Yes, Nirupam. So
yeah, excellent. Yeah.
See my screen. I'll just do a slide change to see if the slide change is working. The slide is changing for you? Okay.
Excellent. Yeah. Okay, so Dipanjan Mukherjee from IUCA will be talking on the multi-scale feedback from relativistic jets by supermassive black holes. And Dipanjan, this is a 80-minute talk, so 15 plus 3, so around 12 minutes. I'll give you a warning. Okay.
Okay. Thank you. Well, it's a great pleasure to give this talk, and I'd really like to thank the organizers for inviting me to give this talk here. So today I'll present some of the results of our simulations of understanding how relativistic jets, as they escape from the supermassive black hole and grow to larger scales, how do they interact with the gas around them, and how do they interact with the gas at different scales. So right from the beginning slide itself, you can see this is one snapshot of our simulation where you can see the volume, the 3D volume rendering of the jet that is breaking out from a turbulent gas disk. And you can see the nice bow shots that are created by the jet as it pushes the extragalactic medium outside. So what we are trying to understand is the effect of the jet on the gas at different scales, starting from the potential of the galaxy to larger scales. And this has been different ranges of simulations in the collaboration with different collaborators, Jeff Pickman, Alex Wagner. And since it's a CEFIPRA meeting, I should also mention that Nicole Nesvadba from the observatory in Nice, in France, is an important member of our team, helping us greatly with providing us important information from the data point of view and then trying to constrain our models by comparing with observations. So going to the next slide. So the main question that we try to understand is, how does a relativistic jet affect the gas around it and affect the galaxy's evolution on the long-term scale? So when we talk about feedback from jets, what we usually think of in mind are these large-scale hundreds of kiloparsecs gigantic structures that heat up and deposit energy from the central black hole to very large scales and heat up the central the outskirts of the galaxy. But before they grow up into such large-scale giants, they do have to penetrate through the gas distribution of the galaxy itself and then grow in size and affecting the gas at different spatial scales. And that is what we try to understand. So the basic questions we try to pose from this study is, does the black hole affect the gas at the galactic scale? Because we all know that jets are highly collimated structures. Do they have a larger impact, or do they just shoot out through the distribution of the gas? And how does it affect the star formation rate? That is a very important question for any agent feedback modeling, to understand how of all these outflows ultimately come in and affect the star formation history of the galaxy, both instantaneous star formation as well as long-term star formation. And then, of course, once it breaks out of the potential of the galaxy, how does it impact the extragalactic gas, ranging from scales of a few tens of kiloparsec to hundreds of kiloparsec? And very importantly, what are the observation signatures that we can predict from this simulation campaign, which will then enable us to compare our results with observed galaxies and observed signatures, and then help us constrain our models. So the campaign involves simulations on 2 different scales and 2 different kinds of simulations. So on one kind, we're mostly focused on the interaction of the jet in the potential of the galaxy itself, where the jet interacts with the gas of the ISM of the galaxy as is contained within the central RE of the galaxy. And then it breaks out. And the major questions we are focused on in this part of the study is the effect of the feedback of the jet onto the galaxy. Feedback in the sense of the energy transfer by the jet onto the galaxy, host galaxy, as well as the effect on star formation rate. And in the next phase of our simulations, what we're really interested in, once it is broken out of this dense region of the galaxy up to scales of a few tens of kiloparsec, what are the dynamics of the jet? How are they affected by internal jet parameters? And how do they can they affect the non-thermal emission, which we can then compare with the synchrotron observations that we can have from different telescopes? So these simulations have been run with relativistic jets with the Pluto relativistic magnetohydrodynamic code. And they are quite numerically expensive and time consuming because it does account for the special relativistic flows and going up to more than 20 million CPU hours and still counting as it's an ongoing project. So what you're seeing, I'm presenting the results of the first phase. What you're seeing now is a slice from the 3D volume with the density on the left-hand side, the temperature on top, and the pressure at the bottom right. And as you can see, this is our initial setup. So I'll just let the jet run, but before I do that, let me explain. So all the scales are in kiloparsecs, and the initial setup is a turbulent distribution of gas. So in this particular simulation, it was distributed as a spherical distribution, trying to mimic the distribution expected for, let's say, an elliptical galaxy or a gaseous elliptical galaxy. Not all of the ellipticals are gas-rich, but if there is a gas, they would be distributed not in a disk, maybe preferentially, but in a spherical distribution. And you can see the gas is a filamentary structure and really turbulent. And we do this by injecting a turbulent spectrum of the density distribution and let it evolve around for some time to make up this filamentary structure, and then we let it evolve. So now I'll let the jet run through. You can immediately see that the jet is finding it quite difficult in the initial phases to break out of this dense distribution of gas. And then finally, once it reaches this about 1.5 to 2 kiloparsec, which defines the distribution of the central region, it breaks out and proceeds much faster. And this is the dentist drill that has been professed by several analytical arguments, that the jet initially almost acts like a drill, drilling through these dense clouds. And in this initial phase of interaction, you can see the jet is not moving smoothly, but bending its head, getting deflected and bifurcated and channelized at different directions. And so you can see from the pressure movie, what's interesting is the jets, as we observe them in radio, are these thin collimated structures. But what they actually blow up in this, at least in this initial phase, is this more roundish spherical bubble of hot gas that's being blown out by the jet. And so this feedback, or the effect of the feedback of the jet, is not just because of the thin collimated structure, but it's more wider in solid angle because of this bubble that is inflated by the jet. And this affects a larger volume of the ISM before it breaks out. Here you can see the temperature movie. The blue regions are the initial cold being gas less than 10,000 Kelvin for our simulations. As you can see, again, the jet-driven bubble, as it's encompassing the ISM, it is creating this hot yellow structure, almost spherically spreading outwards and then escaping. But what's really interesting is inside this hot domain, you can see this cold clouds being embedded inside. So cold clouds get trapped inside this hot bubble, and the hot bubble crushes onto these clouds. And then since the densities are higher, the shock velocities are slower. So the shocks slowly penetrate these clouds as they sort of survive inside this hot environment created by the jet. So this is quite a turbulent scenario that's been created by the jet and affecting not just the central few hundred parsecs of the jet inlet, but over a range of a few kiloparsecs from the central region. Now, this study shows two different jet powers, but impacting the same identical ISM. So on the left-hand side, you have a higher power jet of 10.45 ergs per second. On the right-hand side, you have a lower power jet of 10.44 ergs per second. Now, what is interesting to see here is the higher power jet, because it's higher in power, it's more momentum. It can easily punch through this ISM, and once it sort of breaks out, it decouples from the ISM and then just lets go. But the lower power jets get trapped inside the ISM for a longer time. But the fact that it is still a non-thermal jet with a relativistic plasma and hot gas inside, it is carving out a larger area and affecting the gas over a much larger volume. So whenever people talk of aging feedback, the immediate thing that comes to mind is the more the power of the jet, the more the effect of the feedback. But what we find from these studies, at least, are the low power jets, if they are trapped within the potential of the galaxy, they can also have significant effect on the ISM distribution and the energy budget of the galaxy. So now these are simulations of jets that are impacting a gas disk, and these are for different orientations of the jets. And on the left-hand side, you can see a jet that is launched vertically to the mid-plane of the disk. The middle is 45 degrees and the right is 70. So as expected, the vertical jet immediately breaks out of the central region and just proceeds onward. So it just does create this large cocoon, which then goes and impacts the gas disk and compresses it. But this is sort of expected. But what was not expected was this inclined jets. Since they have a larger column depth of gas to interact with, they are not able to immediately punch through, very much similar to the spherical case. But as they are interacting strongly at these two ends, they're losing the momentum. So this jet in the large scale becomes almost like a sub-relativistic outflow. So these are contours of beta. The white represent 0.5 C of beta. And you can see this two ends of the jet have really decelerated. And you don't see any of this relativistic contours here. But the jet is still putting in a lot of energy. And all of this energy and the kinetic velocities are being channeled along the minor axis of the gas disk, and this creating this wide angle bubble, which is very similar to an agent-driven outflow, to be honest. And in this particular case, on the right-hand side, you can see the jet is still about to break free from this gas disk, since it's going through the gas disk itself. So there are interesting observational consequences of this, and this is something that my student Meenakshi has been trying to follow up on by trying to create mock O3 images that may be observable from the shocked gas that we can find. So the O3 images were created using the mappings code, output of the mappings code using collisional ionization models. And you can see that this is the density on the left-hand side. On the right-hand side top, you can see shocked O3. And since the jet has affected all throughout this ISM, almost all of the ISM is starting to get shocked and is glowing in O3, shocked O3. But what was interesting was when we tried to create mock line profiles, we found that regions perpendicular to the jet shows large velocity dispersion. So this is W80 widths of the line profiles or mock line profiles that we can get from the mock O3 emission features. And perpendicular to the jet, we find higher dispersion. And this goes to, along with the previous scenario where the jet, although is progressing through the disk, it is launching these outflows along the minor axis. And these outflows create a lot of dispersion and then create larger widths. And this is exactly what was observed recently by this Magnum survey on this particular. So I'm showing one particular galaxy, IC5063, but this was observed for a few others by Giacomo Venturi and collaborators. So the jet is in this plane, and you can see that perpendicular to the jet, this direction has large velocity dispersion. So this was quite interesting match. And then there are other important consequences of the jet acting on the ISM. Again, something that Meenakshi has been working on, trying to take our data from the simulation and run photoionization models of cloudy through it to understand how does the impact of the jet affect the ISM to increase the photoionized zone in the central region. You can see here that on the left-hand side plot, the yellow regions are ionized regions and the green are non-ionized. So you can see that some lines of sight are penetrating inside the disk, but not going up to all the way to the end of the disk. But here you can see the classic ionization cone. But what is interesting is beyond these two blue lines, you can see that the ionization cone is patchy because there are some clouds that have been lifted up from the disk that is still creating some obscuration. And you get this patchy ionization cone. And this is very similar to the crepuscular rays that's been observed for the galaxy IC5063 by Josh Blanhorton and their colleagues. What we really conclude from this is this plot where you see the effect of the average ionization radius, or the average radius up to which the ISM is photoionized. For the no jet case of the control simulation, where we just have the disk and not the jet, the central region is only ionized up to a few hundred parsecs. But as we have the jet run through, it creates a central cavity, then that opens up new lines of sight. And you can see that the central kiloparsec, it also increases with inclination of the jet, because the jet more inclined creates more cavity. So as the jet improves, so this also opens up more lines of sight towards the central AGN, and that will further ionize the gas, further reducing the potential star-forming gas and affecting the star formation budget. Now coming to star formation.
You have about 2 minutes more.
Okay, thank you. Now coming to the effect of star formation. So in the classical theoretical simulations, what people have always used is to estimate the star formation of a region by taking the total mass of the gas parcel and dividing by the free fall time. So this is a standard expression that people use, and this is done for a density greater than some threshold density. So you can see for estimating the star formation rate, the only physical variable that comes into play is the effect of the density. So you do not consider the effect of turbulent velocity dispersion or Mach number. So this is something that we should improve on, but in large-scale cosmological simulations, it's a very difficult task to do because you do not really resolve the individual star-forming regions properly because their resolutions are not much more than 300 parsecs. So then this is something is being carried out by my other PhD student, Ankush Mandal, where we're trying to include turbulence-based prescription of estimating the star formation rate. So what we do is since we are resolving the central clumpy structures of the ISM a bit better, we can identify potentially star-forming clouds using a clump finder, and then compute the various turbulence statistics like the turbulent velocity dispersion, Mach number, etc., and then use the standard star formation prescription used in the turbulence community from a very different community who actually model star formation in giant molecular clouds, and use their models to understand how the effects of velocity dispersion and Mach number shocks induced in our simulations can affect the star formation rate. So just to show you what we naively expect is as you increase the velocity dispersion, the star formation rate is supposed to be reduced. And we find hints of that. So you can see on the top right, top left plot, the velocity dispersion is plotted. The gray lines are for the control simulation without the jet. And for the red line is for the jet at 1 mega year, and the blue line is for the jet at 2 mega years. You can see that initially there is indeed a substantial increase in the velocity dispersion going up from the standard disk had velocities of 60 kilometers per second, but this has velocities going up to 100 to 120 kilometers per second. By the way, this is the dispersion of the dense gas. But over time, the velocity dispersion decays due to natural decay of the dispersion due to turbulence. And as the turbulence decays, the star formation rate picks up. So another interesting diagnostic of this is the velocity dispersion of the y-axis and the mean density on the x-axis. And the gray dots here show you the velocity of the typical clouds you find in the control simulation, the no-jet simulation. So what you find is the blue points, which are the outer parts of the disk, they form stars at efficiencies similar to the fact that if they have not seen the jet in the first place. And you have this extended tail over here, which is from the inner central 1 kiloparsec, where the jet has strongly interacted with the gas and has increased the density. So what this really affects is in the Kennecott-Schmidt plot, if you show the evolution or the tracks of these plots, you can see that the star formation rate initially shows a decline and then comes back up onto the Kennecott-Schmidt plot. And what is interesting is, so the Kennecott-Schmidt plot gives you an efficiency of the star formation. There is, in our simulations, a global decrease in star formation. So there is negative feedback or quenching. But the efficiency is coming back up to the Kennecott-Schmidt plot. So yeah, I'm showing you here the mean values of star formation, total star formation for the different simulations for different inclinations. And as you can see, this is the no jet, which is as the typical star formation of a few tens of solar mass per year. And then it is decreasing in absolute value as I increase the inclination of the jet. So the jet is disrupting the density distribution, but the efficiency is not that increasing too much. And this is very similar to the observations by our colleague Nicole Nesvadba, where we observed in last year this particular galaxy 4C 41.7, and the galaxy in the center here, and the red contours are from 1.4 gigahertz radio images. So jet has come out of the central region and affected to the gas. And when we computed the Kennecott-Schmidt plot of this particular galaxy, we found that it's not too different from the standard distribution of galaxies in the Kennecott-Schmidt plot. So what we sort of finally conclude from this study is the effect of star formation is it will get quenched. So it will potentially reduce the potential star forming fuel of the galaxy. But the efficiency over due course of time will come back to the standard efficiency of the star formation. So I guess I'm running out of time, so I'll end my talk here and just sort of summarize in a few sentences that the jets do affect significantly the distribution of gas in the central potential of the galaxy. the staff and we can sort of now start predicting kinematic signatures because we are starting to resolve the individual shocked filamentary structures inside the jets. And star formation, the jets do quench star formation in the long run by potentially removing potential star forming fuel. But the efficiency of the star formation sort of starts to come back up as you have a conspiring effect of both the decrease in the velocity dispersion and increase in density to the jet. So I'll end my talk here and I'll take a few questions if there are any. Thank you.
Thanks, Dipanjan. Maybe we have time for one quick question. If any of you have a question, please go ahead. Okay, I don't see any raised hand or any question in chat. Yeah, if you have any question, you can type it in chat or in the Slack. Then maybe for the sake of time, we will move to the next talk. Thanks again, Dipanjan. So next speaker is Preeti. Preeti, can you
yes,
please
hi.
share your screen?
Yeah, I just share it. Let me know if it's visible.
So Preeti will be talking about jets in radio quiet AGN.
Is this okay?
Yes, but it's right now. It's fine. Yeah.
It's fine.
Just move ahead your slide once and see if it's working fine. Yeah. Excellent. Yeah.
Okay.
Yeah, Preeti. So please start. And again, I will remind you when you have about 2 or 3 minutes left.
Okay. All right. Thank you. Hello, everyone. I'm going to speak about this particular subclass of active galactic nuclei, which are loosely called radio quiet AGN. And to start with a little bit of history, it was in the 1940s that Carl Seifert, when he looked at a sample of spiral galaxies, noticed that some of them seem to have a star-like nucleus in the center of it. And also peculiarly, it had a spectrum which was dominated by emission lines, as opposed to regular spiral galaxies, which were dominated by absorption lines. So these two criteria, obviously, he realized that there was something peculiar going on here. These class of objects was kind of noted as peculiar and like stored away for a while. Also, it was found that the spectra itself showed peculiar characteristics in the sense that some of the spectra always was dominated by narrow emission lines, which had Doppler widths of hundreds of kilometers per second, whereas others had broad lines, which had Doppler widths of 1,000 kilometers per second. So this gave rise to the subtyping of creating subtypes called type 1 and type 2. Later, it was found that there was another group of galaxies called low ionization nuclear emission line region galaxies or liners. And these were very similar to the type 2 CEFIPRA galaxies in that they had narrow lines, but their low ionization lines were very prominent. So it took around 30-40 years for the advent of radio astronomy to actually come about before these galaxies also then became important. And what these radio observations found was that when you looked at these CEFIPRs and liners, they seemed to show some radio emission from the centers. So on the top, you see a spiral galaxy in the optical, and the green contours are the radio emission. So what you see is just a radio point source. And this is how most of these CEFIPRs and liners look like in arc-second scale radio observations. And when they were slightly higher resolution observations, they found that some of these CEFIPRs and liners also display bipolar jets, which you can see in the middle panel, which is an image of NGC 1068. Where the green emission that you see is the spiral host galaxy itself, and the red emission is X-ray gas, which has been detected by Chandra. The blue bipolar structure is the radio emission. So these extents are of the order of tens to hundreds of parsecs. And in a few galaxies, few CEFIPRA galaxies, more extended structures were observed, which you can see in the bottom panel, which is an image of NGC 4225, which show these bubble-like structures being ejected from the galaxy disk. And these extents are of the order of 10 kiloparsecs. So still these are not very large sources. They're still of the order of maximum 10 or 20 kiloparsecs in extent. So this radio emission in CEFIPRA liners, it was debated for a long time, and there were contradictory findings in the literature. So for example, Baum et al. Suggested that these kind of kiloparsec scale structures, or KSRs for short, were actually driven by starburst superwinds rather than AGN jets. Then there were other astronomers who actually took comparison samples with starburst galaxies to see if there were some differences, and they found that the radio outflows in starburst galaxies were different from the radio outflows in CEFIRT galaxies. So it was suggested that these were related to the AGN. So this slide is to show that more recently, in the 1980s, a scheme came about, which was actually, it was a study by Kellerman, who studied this very large complete sample of Palomar green quasars, and found that most of the sources, 85% of those sources in their sample, have this ratio of flux density in the radio to flux density in the optical greater than 10. And so they call them as radio loud AGN, and radio quiet AGN, which includes CEFIRTs and liners, have values of are much less than 10. Visually, what you can see here is on the left, you have a radio quiet AGN. The extent of the radio outflows are very small and confined to the host galaxies. And on the right, you see a radio loud AGN, where you see the elliptical host galaxy in blue and the jets, which are much, much larger. So this is how you could divide this AGN class. Now, what produces this dichotomy is an open question, and people have suggested differences in black hole masses, black hole spins, accretion rates, environments, jet medium interaction, etc. Also from independent, there is independent evidence to suggest that activity in these radio quiet AGN is short-lived. So this is, for example, work by Sanders et al. And what they suggested, and this seems to be true also in these in newer data, is that a CEFIRT activity episode happens when there is a fresh inflow of accreting gas, and which forms a temporary accretion disk, which then ejects jets, and then the fuel runs out and the AGN becomes passive, and then again you have another inflow of gas, which will create an accretion disk in a different direction. So you could have multiple radio outflows, but none of them very long. So in this kind of a scenario, you expect that there should be some kind of relic emission surrounding these CEFIRT galaxies. So relic lobes should be present. And one place to look, or one telescope to look for relic emission is the GMRT, which observes at low radio frequencies. So here is an image of the same galaxy, which I showed you in the previous slides of NGC 4235, the double-lobed galaxy, where we found that there were, the right panel shows the spectral index image, and you see the two radio lobes, but there seems to be some kind of diffuse emission having a very steep spectrum surrounding that primary lobe. So could it be relic lobe emission? We're not sure, but it has a spectrum which is actually what you see in relic emission. So it had a spectral index of -1.8. So with this intention in mind, we expanded our search of CEFIRT observations, looking for radio lobes with the GMRT. And this is work done, which is currently being done also by our postdocs, Sumana Nandi and Rubinur Khatun at NCRA. And these are observations at 325, 610, 1.4 megahertz, 1.4 gigahertz observations. And on the right side, you see the radio contour images of two of these CEFIRT galaxies, which look like any other radio loud AGN, in fact, but the extents of these sources are much smaller. So they are around 10 kiloparsec in extent. And these particular sources belong to the S7 sample. And you must have heard Prajul's talk 2 days ago on the S7 sample itself. So GMRT, because in these low frequency observations, and because of the resolution, which is poorer than the high frequency observations, you find a lot of emission also coming from the host galaxy itself, which is shown in these three images. So the color is the optical galaxy, host galaxy, and the green contours are the radio emission. So you see, you have the emission from the center, which is the AGN, but you also have emission from the surrounding stars. And so that we tried to see if you could separate this AGN emission from the stellar emission on the basis of spectral index images. And this is one example where we've done that, NGC 4051. So on the left, you see the optical image, which shows a lot of young stars forming. And on the right, you see the spectral index image made with the GMRT and the VLA at 325 and 1.4 gigahertz. And what we found was that the region where the stars, young stars were, that seemed to have a spectrum which indicated it was relatively flat around -0.1, which is consistent with 3-free emission. But in the center where the AGN is, the spectrum was steep. It was consistent with the presence of double lobes in a Cepheid galaxy, and it was around -0.6. But this is not always true. I mean, that is a rare case. Most of the time when we look at these sources in spectral indices, so like you can see here in this galaxy NGC 1056, on the top you have the radio optical overlay with the 325 megahertz contours. And you find in the spectral index images, which are shown at the bottom, that the spectrum is steep throughout. So there is no clear division between the AGN and the emission from, for example, the radio continuum halo that you expect from in these galaxies. So therefore, we have now expanded our study of Cepheid galaxies to also include polarization. This is work that was carried out by my graduate student Binny Sebastian, and these are a couple of images from her papers. So what is shown here are 4 Cepheid galaxies, where the black contours are the radio emission at different frequencies, and the red ticks or black ticks in the top panel are the polarization electric vectors. So for optically thin emission, the B field is perpendicular to these electric vectors. And in most of the sources, we find that at the edges of these lobes, the B field is actually aligned with the edge. So that was an interesting finding. We also found that because Binny had also compared, had a comparison sample of starburst galaxies, that they did not seem to show such quick changes in magnetic field orientation. I mean, they had much larger magnetic field structures. So we've now extended this search by also using the GMRT. We've just started this search with GMRT polarization, and this is an image of what is sometimes called the Cepheid galaxy, but this is basically a radio intermediate QSO called 3s-Wiki2. It's a famous source, and the ticks here now denote polarization vectors using the GMRT. So this is a 685 megahertz image with the GMRT. And this is work that's being carried out by my second graduate student, Shilpa Shashikumar. Now, let me come to the last part of the talk, which was looking at the sources which basically show point sources when you look at in arc second scale observations, which is the majority of these CFITs and liners. So here are 4 CFITs and liners shown, where the color is the optical image and the green contours are the VLA radio contours from using the first survey, which have a resolution of 5 arc seconds.
Preeti, you have about 2 minutes.
Yes, almost done. So 5 arc second corresponds to extents of 5 to 6 kiloparsec in these sources. So at 5 to 6 kiloparsecs, there is no jet emission that's clear. But when you look at, so we looked at these sources with VLBI, very long baseline interferometry. So now we are now really zooming into the core, doing a very high resolution study of these. And when we look at these sources with VLBI, we find jets. And so this is an image of KISAR 434, KISAR standing for the KPNO Internal Spectroscopic Survey. And this is the image on the right shows 150 parsec long curved jet. And only the inner 10 parsec of that was also detected at a higher frequency of 5 gigahertz. So the spectrum is steep. But we see the jet is one-sided, and one-sided jets normally in radio loud AGN are suggested to be because of relativistic motion and Doppler boosting effects. So if under that assumption, we find that the jet speed should be of the order of 0.75 C or something, so high jet speeds. Similarly, here is another source, KISAR 872. You see another jet. On the top, the VLA first image shows a point source. Nothing very interesting. It's a weak point source of only a few millijanskis flux density. But you see a 200 parsec long jet in VLBI images. These are a couple more jets, which we see. Again, if you see on the top, the first flux densities are really small, very weak point sources, but you see jets. So we are finding that in this particular sample that we looked at, more than 60% of them show jets, and they are one-sided, which suggests that the speeds can range between these values that I've noted here for a certain inclination angle. So to summarize, the radio outflows in radio quiet AGN, which include CFITs and liners, are not completely understood yet. We have been chasing these using GMRT and VLA, and we have found already at least some sources where there may be indications of relic emission. But the spectral indices are not enough to segregate the AGN emission from stellar-related emission. But the polarization seems to do better, and it's already showing that there are some characteristic B-field structures that we see in these CFIT lobes. So now we've started that search also with the GMRT. For a particular sample of sources that we looked at, which had point sources on kiloparsec scales, when we looked at them with VLBI, we find a large majority of them have jets. And this is actually consistent with other studies in the literature, for example, by the Lemmings survey, which is even a much larger sample of CFIT galaxies and liners. They find majority have jets. What was interesting was that when we estimated the kinetic powers, jet kinetic powers, they are in the range of 10 to the 41 to 10 to the 43 ergs per second for these, for our sources. And at the higher end, they start approaching the kinetic powers that are reported in the FR1 radio galaxies, which are radio loud AGN. So that was very interesting because it seemed to suggest some kind of a continuum in properties going from radio quiet to radio loud AGN. Finally, these sources were chosen to have double peaked emission lines because the search was to see what produces double peaked emission lines. And it turns out from this sample that jet medium interaction is likely producing that. So overall, from our research is showing that jet medium interaction along with short-lived jet activity can actually explain the outflows in radio quiet AGN. I'll stop here and take questions.
Thanks, Preeti. So questions? Okay, I don't see any raised hand or anything on the chat here. Yeah, there is one. Okay, Aishwarya, please go ahead.
Yeah, thank you. Thank you for the very nice talk, Preeti. I've gone through this paper of yours where you explain the double peak emission arising. But what makes me wonder is, do you then also see like a separate, broader component because of the outflows? Or do you attribute one of these to the outflow and one of them to jet peak? I mean, I'm trying to understand this.
Okay, so we don't. So these sources were chosen as type, like these are type 2 AGN. So actually they didn't show broad components at all in their spectra. So we think that the two peaks are basically NLR gas clouds being pushed by the jet in opposite directions. That's all. So there is no signature of another outflow, emission line outflow. There isn't.
Okay, thank you.
Thanks.
Okay, any other question?
Yes, sorry, apologies. So thank you so much for this wonderful talk. I was wondering if you are able to trace maybe the ionization structure, the morphology of the ionized gas as a function of kinetic energy.
Right. Yeah, so that's a perfect question. I think that is what we really need to do, is to do this radio emission along with the emission lines. But so far, what we have, I mean, these are VLBI observations. So this is now we're talking about parsec scale images, and what's happening on kiloparsec scales is actually not showing any jet structures. So I think we may need to look at a different sample of Cepheid galaxies which actually show some large-scale radio outflows, and then compare. But that is something we want to do in the future, yes.
Thank you so much.
Thank you.
Thanks, Preeti. And please continue discussion if any of you have any more questions, but let's now move to the next speaker. Samuel, maybe you can start sharing your screen so that we can check if it's working fine. So our next speaker is Samuel Vasher, and he will be talking about studying low surface brightness galaxies in the future. So Samuel, please go ahead.
So, okay. So thank you for being still there. For some of you, it's starting to be a bit late. And thank you to the organizers for giving me this opportunity to talk about low surface brightness galaxies that I think are going to be an important topics in the future. Before starting, I should say that some of this presentation includes material from collaborators, of course, and I wanted to mention especially Junais, who is doing a thesis in Marseille with me, and but that you've seen already before in a short presentation. So let me start by putting this this into historical context. There was the low surface brightness galaxies have been studied only since the 80s, let's say. On the right here, you can see an histogram of the number of publications, including low surface brightness or ultra diffuse galaxies in their title as a function of time. You can see that they were started to be studied in the 80s. There was a peak around 2000. After that, it was declining, probably because we had done everything we could with the data at that epoch. But in the last few years, since 2015, there is a big peak, it's increasing. And there is a renewed interest in this type of galaxies. And this is due to the fact that we have new instruments, new detectors that allow us to go dig deep in below the level of the sky, basically. And this, for instance, there is MegaCam at CFHT, there is MUSE at VLT, there is instruments dedicated to low surface brightness science like Dragonfly. And there was also a branding about ultra diffuse galaxies, which is a new name that was invented at that occasion by Van Dokkum. And there was a lot of interest for this new type of galaxies, even if they are not completely new, but at least they have been found in large numbers in the last years. And so there was a big interest for them. And it's going to keep on, as we will see a bit later. So I think it's going to increase again in the future. Let me go back to some very basic definitions. Actually, we heard already a bit about that before by Ramya. So the historical definition of low surface brightness or LSB galaxies is based on the disk component. So here is a textbook definition of a bulge plus disk decomposition of a profile. And the disk component is characterized by two numbers, the scale length and the central extrapolated value of the surface brightness, which we will call mu0 sometimes. In this case, it's in the B band. And that's what we use to define low surface brightness galaxies. And in fact, we do that because a long time ago, Freeman actually studied a sample of 36 galaxies and made this decomposition, this measurement, and he found that the mu0 value was 21.65 with a standard deviation of 0.3 mag. So I made a plot here showing you what it would give is a number of galaxies as a function of the central surface brightness. And this is for the disk component. But it's based only on 36 galaxies, and it's based on the observations from the 70s when we could not actually observe at the low surface brightness. A bit later, in around 2000, O'Neill and Button produced some distributions which are more like that. So you see that if there was brighter galaxies than the Freeman value, we would have seen them. So it's dropping. But on the low side, actually, McGo and O'Neill and Button and all these people found a lot of these galaxies which are much below the Freeman value. And so these people start to say maybe the universe is actually dominated by the low surface brightness galaxies. And indeed, if you look at the simulation of Martins et al., which are much more recent, it's based on Horizon AGN, you find that if you take a threshold of 10 to the 8 solar masses, almost 50% of galaxies are low surface brightness galaxies. If you put this threshold at 10 to the 7, it's actually 85%. The number is much smaller when you look at the contribution in mass or in light, but for the mass, it's the stellar light, actually. And if you wanted to put the gas mass, I don't think they've done it, but the fraction will be much larger because these objects are often gas rich. to keep on this definition, this is to see it in another way. Okay, the historical definition was to say that the central surface brightness had to be much below, well below this value of Freeman value. And the Freeman value is the red line. And here it's two galaxies which are matching in scale. So this is a normal spiral galaxy. And this is Malin 1 that we actually heard about before by Junais. This is probably the first bulge disk decomposition of this galaxy that was showing that there is a disk which is way, way below the surface brightness that you see in normal galaxies. Okay, so that's why it was interesting. That was the profile, and now I'm showing you some images. So the discovery image from David Malin, you can see that there is some stuff here, but it's actually kind of difficult. And you can see the jump that we make when we use megacam data, where we can see the spiral arms in details. We can see diffuse areas that are maybe related to past interactions here and there. And so the new data allow us to go much, much further than it was possible before. So this was from a recent work of myself, but there was a lot of people of work in the recent years on this galaxy from all over the world, and especially by Junais that you've seen before, and but also with by Sarah et al. With UVIT, very recent paper. You see I've put some little flags. You also saw some contribution before by Junais and Ramya. And so there is clearly an interest on both French and Indian side, obviously. For Junais, I put two flags because you may have understood that he's Indian, but he's doing his thesis in France. So he deserves both flags. To keep on after this basic definitions, people have proposed some, try to propose some more interesting definitions to define what was giant LSB or low surface brightness galaxies, because the definition was a bit vague. It was okay, below the mu0, below the standard value, but where do you put the line and so on. And actually, we heard about the Sprayberry et al. Criterion, which is indicated by the green line here, which is a combination of scale length and central surface brightness. And the idea was that galaxies which are relatively normal are in this plot in this side. And if you look at galaxies with the same magnitude, but which are much more spread out, they have a larger scale length, they will move along this line. So in this area of the plot, you can find galaxies which are massive as normal ones, as much light, but which are much more diffuse. And that's basically the definition of the giant low surface brightness galaxies that you heard before. And the Sprayberry criterion line, the selection is here, is the green one. Malin 1 in this plot is here, so it's the most extreme case, but other galaxies similar have been found recently, like by Hagen et al., this one. And there is a population here, and probably many more intermediate cases still to be found and discovered. So it's very interesting. And in the meantime, there was another definition that appeared recently, which is the ultra diffuse galaxies introduced by Van Dokkum. I mentioned that earlier. It's rather based on the effective radius, not on the scale length, but you can sort of cheat and make a selection on scale length if you want. And if I put it in the same plot, it would be the red box like this. So you see that there is some common area with LSB, diffuse, and all of this. There is other definitions. People doing simulations usually use different definitions because they cannot resolve all the surface brightness or stuff like that. There is threshold on mass because in the simulation cannot do the very small mass usually. So there is other definitions. And in fact, another proposition which is very recent is to look to outliers in scaling relationship. So the idea is always to select not only galaxies below some values, but which are intrinsically different from the general population. And this is done by Limetal in the Virgo cluster, where you have the normal galaxies, which describe scaling relationship. And if you go below the density, the effective surface brightness, let's say, below a few sigma of the scaling relation, you can define the galaxies which are extreme in this case. And so you can decide that those are the galaxies of interest, and it's low surface brightness in the sense that they are below the normal family. And it's not an absolute threshold, it's relative to galaxies which are otherwise of the same properties. So what we are doing actually with Junaïs now is to look in Virgo, because in Virgo we have many surveys that have been looking at these galaxies. In the optical there is the next generation Virgo survey. There is UV data from GUVIX, and more recently H-alpha narrowband imaging from the Vestige project of Boselli et al. Alessandro Boselli, who is working in Marseille too. And in this diagram, again, scale length versus central surface brightness, we have the full NGVS sample here, and we can make selections which are like the Sprayberry ones, that's all the galaxies below the green line, a Van de Koom-like selection, the red box, or the outliers like Limetals, those are the blue points. And so what we plan to do is to study all of this sample, and also to study what happens when you actually have you make different selection criterion. Okay, so that's what we are starting to do, and I should say actually Junaïs is doing this in this year, and he's going to defend at the end of the year. So he's actually looking for a postdoc, and to convince you to propose a postdoc to him, I'm going to show some of his fantastic results. So here is a paper that has been just accepted actually, and it's one of these galaxies, one of these in the sample, which is here. It's an ultra diffuse galaxy, so it's spread out. It's not very massive, and we have the surface brightness profiles in all the bands. Here I show only a few ones from Z, I, UV, and H-alpha. In some cases, it's only upper limit. In some cases, it's detection. And we have been studying this galaxy. We've been fitting some models. So I will not give the details of the models here, but if you are interested, we can discuss after. But these models are basically simple chemical spectrophotometric evolution models, including ram pressure stripping, because we are in a cluster, so the galaxy can suffer ram pressure stripping. And when we do that, we can fit all the profiles simultaneously with a model which has ram pressure stripping, so the gas is removed in the last few 100 million years. And this explains the lack of detection in H-alpha. This explains the fact that it's faint in the UV, but you can still match the properties in the optical bands. So you can match all of these together. And in this case, really what makes us really believe it's ram pressure, it's because like it happens in other spirals, there is detection of H1 outside the galaxy. So the idea is that the galaxy has been completely stripped of its gas, but some of the tail of the gas is here. There was an alpha-alpha detection, which has been also observed with VLA at this place. And at the same place in our data, we find knots of regions, basically, which are very blue, probably with star formation that is very recent, which is confirmed by the fact that we have H-alpha detection in some of these places. So it's a first case, I think, that for an ultra-diffuse galaxy, we see this process, ram pressure plus formation of stars in gas that has been stripped just in the area. So if you put this into try to put it in a global context with what we try to do here, here is the mass of gas of H1, here is the stellar mass. The black points are regular galaxies, basically. And the orange points here are blue H1 bearing UDGs. So it's ultra diffuse galaxies, but which are also found in gas with alpha-alpha. And the model that I showed you before the ram pressure stripping, it's exactly here. So it means it's completely consistent with being a blue H1 bearing UDG that have been found by these guys like Liesman et al, Janowiecki et al. It's also consistent with Pro et al. We found some blue field UDGs. So we have a population which exists here. And when we make this galaxy enter into a cluster and feel the ram pressure, it loses its gas. It makes this galaxy that we observe, which is a red UDG, gas poor, like we found many of them in clusters. And at the same time, in the stripped gas, we can form stars in small clumps of gas, which has basically what people call sometimes dark galaxies or almost dark galaxies. And it's a low stellar mass into a relatively large H1 gas. So this scenario works for one galaxy. But we are actually also now looking to the full sample and trying to make the same sort of fit with the models. That basically the models tell you when they fit well the galaxy, you can say, okay, if I believe them, they tell me how much gas there was before the RAM pressure stripping, and that's the blue histogram. It's consistent with the galaxies found by these guys, the gas-rich UDGs. And after the RAM pressure stripping, that's a red histogram. So a lot of the gas, major part of the gas has been removed. Okay, so that's very preliminary, but it's a work that we are doing on the full sample, and I think it's going to give very exciting results. So now I promised you to talk about the future, so let's go to the future. Of course, futurology is a bit risky, so maybe I will say some stupid things, but I'm taking the risk anyway. So there is outstanding questions on this type of galaxies that I presented before. There is questions on the giant LSB. So if you remember, the diagram that you've seen before is the one which are in this part, in the red shaded area here. First, what is the star formation and the properties of the extended disks that we found that are very hard to study. What is the link with XUV galaxies? And Junaid mentioned that, so we can keep on studying with galaxies and now with UVIT, for instance. What are the dynamics in these galaxies? Because this is related to the scenario of formation, and more generally, at high redshift, are we going to find more of them? There is maybe 10 of them in the nearby universe if we take the Matthews et al. Sample, but we have seen before that maybe there is many more of that. We have to look at them in details. And at intermediate redshift, some people have found galaxies that seems to have large scale lengths. So maybe there is also large galaxies at high redshift, and we have to go and look at them. And for UDGs, there is also a lot of questions. Do we have a complete census of this population? There is a big difficulty, which is confirming the distance. What is the dark matter properties? And more generally, what are the origin of these diffuse galaxies? There were several scenarios that have been proposed that would be failed massive galaxies that have failed to make stars, basically, but would be rich in dark matter in this case. There is puffing up early on via feedback. Some people say it's just a large angular momentum tail of the halos of dark matter that makes galaxies more extended. So we have to tackle all of these questions. So the good news is that the future is actually bringing to us a lot of data. Here I'm showing again the same galaxies in the NGVS data that we have. So that's surface brightness limit of about 29 magnitude by arc-second square. This is a Sloan image of the same area. So you can see the jump that you make when you go to deep imaging here with the CFHT. And in NGVS, we have observed the Virgo cluster, which is about 120 square degrees. So if you put this 120 square degrees to this scale of these small circles, here I've done circles at the same scale for some of the surveys which are coming right now in the optical. So for instance, the DES, there is a paper by Tanoglidis et al. That shows that they found a new population of low surface brightness galaxies. It's in 5,000 square degrees now. So we are surfaces which are much, much larger. CEFIS is coming also. It's a companion survey to Euclid, basically, and with pan-stars are from a joint adventure, let's say, which is called Union. We're going down to very low surface brightness too. LSST is going to be also amazing with, depending on the source that you find, we can hope to have galaxies with central surface brightness of 27 and maybe a limiting magnitude for structures of 30 or 31. So, and over a very huge area. So that's very interesting. And moreover, there are going to be space observation of large area of the sky too. So that's a map of basically exposure for Euclid. You can see that the yellow area is what's going to be observed with Euclid. It's 15,000 square degrees. It's going to go down to very, very low surface brightness in Gibbon. So it's going to be complementary from the optical surveys. Here, actually, this map is from a Kapak et al. Paper, which is a proposition to extend LSST to the north to have more overlap with Euclid. And there is also dedicated projects that are going to come. I mentioned just the idea of Messier, was that would be a space surveyor dedicated to LSP that has been discussed in France. In Marseille, we have a castle that is basically a ground demonstrator of the use of curve detectors, and curve detectors make less optics, so it makes less reflection. So that's good for LSB. So that's going to be interesting. And it's also a test to see if you can use them for BlueMuse later. So that's going to be also very important. Okay, so all of this is nice, but there is some difficulties to tackle in all of these surveys, so I'm not going to mention them in detail, but obviously the observational design of the surveys is going to impact what we can do. The extraction of the source may be difficult. This is an image by Miville Deschênes showing that the interstellar medium of the Milky Way can actually create structures on every scale. That's the power spectrum of the diffuse light in this image. Combining Planck over the large scales, WISE and optical on different sides. So you can see structures linked to the dust of the Milky Way on all the scales when you go very deep. And so that's something that we have to study to understand how to take into account and to remove from the samples. And of course, there is possible biases depending on how you define things. So all of these are the difficulties linked to these optical surveys, but nevertheless, for sure, there will be a lot of very interesting data to come. So now we need more. So because I was talking just about imagery actually up to now, but this has some limits. The limits of imaging studies, especially for ultra diffuse galaxies, are that first you have no details. It's very hard to get details on the stellar population, on the metallicity, on the dynamics, because you have just a few bands and it's red, okay, but it's not bringing much constraints. In the clusters at least. Very often you have no redshift because they are so faint, these galaxies, that there is no spectra, so no redshifts. That makes a big uncertainty on the distance. In this case, we are in Virgo, so we assume we are at the distance of Virgo. We have also spectroscopy of companion region, it helps, but it's not always the case. And here we have H-alpha detection, but it's in narrow band, so we absolutely need to do some confirmation and study this in spectroscopy also to check really the properties in details of these regions. So we need spectroscopy for cases like that, and in general for many more UDGs. And this can be done, and it has been shown by French et al., for instance, that have done a study of these ultra-diffuse galaxies with MUSE. The image is actually a reconstruction of the continuum image with MUSE, and the circles show globular clusters and planetary nebula that have been detected in MUSE data. So MUSE is going to can do this sort of job, and we need to do that type of spectroscopy for many more galaxies. But even if we don't have the spectra of the stellar population, the good news is that for the gas-rich one, at least, we may have it if we have H1 data from the H1 cubes. And just to illustrate that we are going also to have a lot of information on this side, I'm showing here something that we heard about as the SKA1 projects. This is Stavely or Sterlou proposal to do some blind surveys of the sky in H1, and it's basically showing that you can detect galaxies up to quite a large distance, and it's redshift up to redshift 1. And if we apply to the science case I was mentioning, if I show you the histogram of gas masses that we had found in our little work with Junaid, even if it's preliminary, basically the blue area here show you where we are. So it means that these blind surveys, if there is a population of field UDGs, they are going to be found also at intermediate redshift up to 0.2 or more in some cases. Okay, the one which are devoided of gas, it's much harder to find, obviously. So here in this case, it's more for the blue ones. However, there is also precursors which are already working. That was actually, we also heard about that, Mamta, about the Wallaby survey, which is doing a blind survey of the southern sky, but also a part of the northern sky. So the Virgo is included in the sky. So there is data, but actually I don't know in which states they are yet. We heard about it, but I'm showing again here our prediction, and you can see that in this survey we should be able to find if there is some blue UDGs at the distance of Virgo, we should find them without problem. The detection limit I put myself, so maybe it will depend on the precise reduction of the data. We may have to look again later. But also the more massive ones of the one which have had RPS could be detected actually. So of course this is in the case of prediction of a model, so the model might have problems. of course, it has not been tested in this area, so that will be a completely new test for the model. So that's quite interesting also, and I look forward to have more information on this. Since I was on the large H1 samples, I also wanted to say this is also true for the giant low surface brightness galaxies. I was showing the case of ultra diffuse galaxies, but the giant LSBs that I talked before, they are also very gas rich, at least if they are the ones which are like Malin 1. Okay, so Malin 1 has more than 10 to the 10 solar masses of H1. So it means that in these blind surveys, if there is more Malin 1 at high redshift or Malin 1 like galaxies, you're just going to find them very easily. Probably the harder part will be to find the counterpart in the stellar light. But so this is a very interesting prospect too. And this shows the size of Malin 1 in kiloparsec versus the size of the beam in this plan surveys as function of redshift. And this is basically showing that yes, below redshift 1 or 0.5, depending on your assumptions and on your type of surveys, you will be able to detect Malin 1 and to resolve it as a galaxy. So that's quite interesting. Wallaby should also detect Malin 1 galaxies if they exist in a more reasonable volume within 1 gigaparsec, but that's also something interesting. And of course, with the full SK, we will have even other prospects that would be very interesting, but I'm not going to insist too much on it. That was for the H1 for giant LSB, but spectroscopy can also bring us a lot of information. So it can inform us on different subjects. You've seen the talk by Junais, so he was talking about what we have done on Malin 1, and it shows that we can have information on the star formation. Actually, in the disk, if we had better data that we hope to have in the future, we could also look at really the stellar population, for instance, in the center of the galaxy. We could look at the properties of the dust of our metallicity within the disk, and that's other constraints on the models on the formation of such galaxies. And
Samuel, you have about 5 more minutes, maybe?
Yeah, I'm going to finish shortly, so we will have more time to discuss and to finish earlier, maybe, if we are tired.
Okay.
So I will be quick now. And also the dynamics is very important, and we show that we have a steep rotation curve, but strange values, and which are hard to interpret in the center of Malin 1. Obviously, EFU data will be very important to understand what happens. It was what we were discussing in the chat, actually, to understand what happens in the center of Malin 1 and of such galaxies. And Saburova actually et al. Has shown that there is several scenarios for the formation of Malin 1 like galaxies. And depending on the scenarios, you're going to have some signatures or others. And like what are the dark matter properties, if there is a dynamical peculiarities, counter rotation of stuff like that. So all of this you could study much better if we had a complete EFU. So you've seen that we have done some stuff already, but in the future we will be able to do much more with future instruments and survey are going to bring us a quantity of LSB targets, which is phenomenal. And we will need to study them and to follow them. So spectroscopy will be important. The role of big large field IFUs will be very fantastic tool for some of these subjects. And SKA should also allow us to find the H1 bearing UDGs, and that's a very important subject. And I hope that we will learn much more on this subject in the coming years. So I'm going to stop there, so we have time for a few questions, or we can finish a bit earlier if we can.
Thanks a lot, Samuel, for this very exciting talk, and also giving us what to look for, all the futuristic, interesting things that are going to come. Certainly, very exciting time ahead. So let's see if people have questions. Please raise your hand or type it in the chat box and go ahead.
Can I ask a question?
Sure, yes.
Yeah, thank you so much. It was a wonderful talk. Lot of work to do.
I think maybe you have to speak a bit louder. It's not coming clear to me.
Okay.
Yeah, now it's good. Yeah.
Sorry. Thank you, Samuel, for a very nice talk. Could you elaborate a little bit more about the cover detectors and the kind of instrument work which is going on?
Sorry, you asked about elaborating about the instruments, but I didn't
Yes.
understand in which case in general.
The covered detector, which
Curve detector. Sorry. Okay. Yes. So actually, in Marseille, there is some people who are developing curved CCDs, let's say, detectors, which are so the focal plane, instead of being flat, is curved, which allows you to avoid to have optical elements in the path of the light to make the focal plane plane. So you can. It's like in the old time when you had the photo, I don't even remember the names in English, photo, the pellicule, the photo plates, which were you could put just in the focal plane like you want. And now these curve detectors allows you to have a simpler design in the optical, so less lenses, less mirrors. And each time you put a mirror in a pathway or a lens, you create ghosts, you create reflections that's going to make put structures in your image that is not physical. For CFHT, for instance, it's the case. There is a big star near Malin 1, which actually you don't see anymore, but it's below, and we had to remove a gradient due to the presence of this star in this image. And it happens a lot for when you go to low surface brightness, you see a lot of these halos of stars or artifacts, which are due to all of these defects in the instruments, due to the fact that each time you have an optical or surface, you create these artifacts. So the curved detectors allow you to put less elements, so hopefully to have a more direct path from the sky to your detector, and so to have a cleaner sky. So it should allow us to better study the low surface brightness component, especially, which are very polluted by these effects. So the consortium in Marseille is making these detectors now, and the things that they have not yet been used for astronomy. So we hope to demonstrate with Castle, which will be a demonstrator in Spain, that they work and that we can get data even with a modest telescope. And then we hope also that they can be implemented in Blue Muse, so that would allow to have a very big field of view without introducing these defects.
Great, thank you.
You're welcome.
Impressive.
Sure. I have one question. You mentioned about this diffuse galactic emission itself, which will be a challenge when you go into deeper imaging for this target. So, have you, can you tell us about the way out? I mean, what can be possible resolution to this challenge?
That's a good question. The way out is first to study very well the dust to understand in detail its properties, and to combine what we will have in these big surveys with the other information that we have on the dust of the Milky Way. So, for instance, with Planck, but which has not a very good resolution. So we have to understand the properties of the dust in the best possible way to be able to recognize it from the combination of multi-wavelength light and remove it eventually. However, in some cases, it's going to be impossible, because if you have a very big cirrus at some places, you can do whatever you want, but the source behind is going to be extinguished. So the detailed consequences of this effect, actually, they are still to be studied and to be understood. So here I put some stuff from Miville Deschênes, and he's working on that with some other people, and we hope to work with them also to study the dust actually in details, to be able to better remove it. But in some cases, if you have a nice target which is just behind the big cirrus, you will just lose this target, I guess. And for galaxies, it's still okay, but I didn't mention, of course, there is also a lot of stuff to do with low surface brightness structures, like around galaxies, like tidal arms or maybe shells or stuff like that. And tidal arm may be very hard to distinguish from an elongated diffuse cloud of the Milky Way. So the multi-wavelength approach is the only approach to be sure if your structure is real or if it's due to the dust of the Milky Way.
Mm-hmm. Okay. Any other question from anyone?
Nirupam, can I ask a question?
Yes, please. Yeah, go ahead. Yeah.
Yeah, thank you, Samuel, for a very nice talk. You mentioned about 2 discs in Malin 1 in your last slides, right?
In my last slide, I mentioned what? Sorry.
2 discs for the inner or outer discs for the Malin 1. And what is the reason for the formation of the outer disc? Is it some...
Okay. So this is something a bit still to be understood in detail, but it's not especially for Malin 1, but also for other Malin 1 like galaxy. So we've seen that there is a central part which looks like a normal galaxy, and actually it looks like an S0 indeed, with a bulge plus a disk already by itself, and then this very extended disk which is much flatter and that goes very far. And the reason for this very extended disk could be independent from the normal galaxy part. So that's something that I think is not completely sure yet, but maybe could be late accretion from gas that comes to the galaxy at a later time, and that has larger angular momentum, and so that would make a more extended disk. Or it could be interactions that may have redistributed some of the gas that was there, or stuff like that. But I think it's still a bit of an open question, and we really need to look at full samples of this type of galaxies with IFUs, and to have the complete dynamics, and to be sure that the disks are well rotating, and there is no they are co-rotating with the inner disk, for instance. We have to be sure of that, and it's still to be looked in detail, I think.
Thank you.
Okay, so if there is no other immediate pressing question, I will suggest maybe we can move to the next talk. We have one more talk. We can of course continue the discussion and the question over chat, and the chat here and over Slack channels. So thanks, Samuel, for your talk. So maybe we move to the next talk now. Shubhashish Roy is our speaker for the last talk of the session, last talk of the day. Shubhashish, can you please share your screen?
Yeah, let me try.
And Shubhashish will be talking about the low radio frequency observations of nearby galaxies.
Yeah, can my screen be seen?
Yes.
Okay.
Yeah, maybe you want to make it full screen, and yeah.
Yeah. Right. So today I will be talking on the low radio frequency studies of nearby galaxies. So the main thing to say here at the beginning, that whatever the earlier studies and so on, well, there have been many studies of nearby galaxies, but most of these nearby galaxies have not been studied below 1 gigahertz of frequency. So that means below, let's say, the 20 centimeter or above 20 centimeter in wavelength. So these are some of the studies, just for example. So the issue is, why should we observe? So one thing is, as I said, that most of these galaxies have not been observed at lower radio frequencies. It opens up many windows to look for. So the first thing is that spatially resolved synchrotron emission for most of these galaxies are not known or have not been really studied. So what are the outcomes from the synchrotron emission, study of synchrotron emission? So for example, how the spectrum of non-thermal emission changes with distance from the center, or with, say, with star formation rates of galaxies. Then what is their spatially resolved radio FIR correlation? We do expect that the radio FIR correlation would be valid at different parts of the galaxy, but the thing is, can we though find it out? Can we study it in a spatially resolved way to see that how the properties change, particularly between 20 centimeter radio, which is well known, and the FIR, or versus 90 centimeter radio and FIR. So then the next question is, of course, how the cosmic ray electrons propagate in these galaxies. Then what is the distribution of magnetic field strength in these galaxies? But here, of course, one is talking of, or what one can do from radio observation is equipartition magnetic field. We can't go beyond that, assuming equipartition. The other thing is, then the comes up from the equipartition magnetic field is that how the magnetic fields and star formation rates are coupled in nearby galaxies. And the typical resolution would of course be linear resolution would be maybe few hundred parsec to of the order of a kpc size scales. Then the other thing is how magnetic field and gas are also coupled in nearby galaxies at the above scales. So these are some of the questions which we will like to or try to see today. So what are the requirements? As I said, that the requirement would of course be multi-wavelength observations to trace different components. We of course need images with high resolution and high sensitivity. And this would allow essentially estimation of physically relevant parameters. For example, the thermal subtracted spectrum, the radio FIR correlation, which I've already mentioned, the cosmic ray electron propagation scale, magnetic fields, gas density, star formation rate, surface density, and so on. So the non-thermal emission, or rather how the emission of galaxies looks like, this is the typical the galaxy emission, which you can see at frequencies of about, let's say, 100 gigahertz or so. A minimum of emission is reached, where basically the thermal emission goes down. Afterwards, it is the non-thermal emission which tends to peak. So that plays a dominant part, and around 1 gigahertz or even below, it tends to go up. So this is from Condon's paper in 92. So the point is here what we are trying to do, we of course from radio, if we want to find out what is the non-thermal emission, we have to then model the thermal emission, which can be done through their H-alpha maps, H-alpha observations, and also from 24 micrometer observation, which traces typically the thermal emission. The resultant non-thermal emission provides the quantities which I mentioned before. That is basically the spectral index, the radio FIR correlation, study of cosmic propagation, and so on. Now, so which are the galaxies we are trying to study? So we checked that among the galaxies one would like to observe the Spitzer local volume legacy sample, which is about 11 megaparsec, all the galaxies and which are there. And there are about 12 to 58 galaxies in this LVL sample. These galaxies have also been observed in infrared, in MIPS, so the Spitzer MIPS, then in UV, H-alpha and optical band data. It has also been later on studied, or many of the sample galaxies have been studied by also Herschel, then in radio by VLA, also through CO and H1 line observation data. So for GMRT study, we selected 46 out of 258 galaxies, and these were dictated by the following things, that you have something called the interferometer. This GMRT giant meteorite radio telescope is an interferometer, and so even at 330 megahertz or about a meter wavelength, given the short spacing, missing short spacing, you can study diffuse emission for of the order of about 16 to 17 arcminute size scale, beyond which it tends to have problem in reproducing the emission. So that sets the upper limit. The lower limit of galaxy sizes, angular sizes, are set that you should have at least 10 resolution elements across the galaxies. So that we have taken about a few arc minutes to about 16 or 17 arc minutes. That was the criteria. And the galaxy should also be visible every day, meaning typically with GMRT, let's say more than 4 hours a day. So these all sets about 46 out of 258 galaxies. And we initially carried out a pilot observation of 7 galaxies, which included 2 phase-on spirals, 3 age-on spiral, 1 interacting starburst, and 1 irregular, as pilot observations using legacy GMRT at 330 megahertz. Archival VLA data was also analyzed at L band. So these are the images which you can see. So this includes, for example, galaxy like 2683, which is on the top left, then 3627, then 4096, 4449. These are the 4 here shown. Another 3 will come in the next page. The typical resolution which you have achieved is of the order of about 10 arcsecond. And the RMS noise varies from maps to maps, but it varies typically from about 60 to 200 microjansky per beam, except for 3627, which has the RMS noise of about 450 microjansky per beam. And this is all, remember that with legacy GMRT, which had about 32 megahertz bandwidth, These are the other three images. Of course, the central one is M51 or NGC 5194. This was more included because this has been well-studied galaxies and how we can get the images and so on. So this we got about 100 micrograms RMS noise. And then you have also 4490 and 4826. So these are the galaxies, and the contours basically show the radio emission at 330 megahertz or meter wavelength, whereas the 24 micron show the is superimposed in grayscale. Okay, so next I come back to galactocentric variation of non-thermal spectrum. So the typical spectrum which we expect is basically which is controlled by cosmic electrons, which are accelerated, freshly accelerated, are believed to have spectral index of about minus 0.5. Whereas as you go away from the central region of galaxies, and the star formation rate also goes down. So that means the cosmic electrons are traveling further and further from their place of origin, and they would basically lose energy and would tend to, the spectrum would tend to stay. And this spectrum, so that's why for some of the galaxies, you don't see much variation. Like this is the top left is 268, then come 3627, 4096, 4490, then in the middle left, 4449, sorry, in the left, 4490 middle, 4826, and 5194. So the typical tendency is that as you go away in galactocentric radius increases, the spectrum tends to steepen. This is consistent with what people knew before. But yeah, these are galaxies which most of them have not been studied in meter wavelength, but people have studied it between 20 centimeter and higher frequencies and 5 gigahertz range. We also then show their radio FIR correlation. So the radio FIR correlation I'm not showing for all, but 4 of the representative cases. So the top panel shows the 70 micron versus 90 centimeter. Y-axis is log of radio, x-axis log of FIR. And the FIR, here we are using 70 micrometer monochromatic radiation as the representative case. And the 90 centimeter comes up and the 70 micron comes down. There is an offset also we have introduced between them to show the two plots well separated. And so this is the 2683. Then the right top right is 3627. Then comes 4096. And then comes 4490. The parameter for all the 7 galaxies, that is the radio FIR slope, which is shown in B between 90 centimeter and 70 micron, and 20 centimeter and 70 micron are shown on the second and third columns. So typically what you can see here is that the radio FIR slope tends to flatten at 90 centimeter using 90 centimeter radio data as compared to 20 centimeter. So in 20 centimeter, it's more like about 0.8 to about 1, whereas it tends to the flatten at 90 centimeter. This is due to propagation of cosmic electrons, so the correlation goes down because not from the same place where the FIR originates, the radio originates. The radio tends to spread out. So that's why the correlation tends to go down. So there are exceptions. For example, 4490, the slope is, which is actually an interacting galaxy with 4485 on top of it on the north. So here it shows that the slope actually steepens, and this could be partly to do with the interaction. Then of course 5194 and arm and interam, which we have separated. So it is like this, and these are the intercepts which are shown in log A that we won't go for anything right now. So next we come to cosmic electron propagation. So the cosmic electrons could move away from source by diffusion. However, other methods are also possible, which includes things like streaming instability or even galactic outflow. They could play important roles depending on the galaxy type. Velocity of propagation have different dependence on frequency. So meaning all these three, that is diffusion, streaming instability, or galactic outflow. The diffusion goes as lambda to the power 1/4, whereas streaming instability goes as root over of lambda, whereas galactic outflow is expected to be independent of frequency or roughly independent of frequency or wavelength. So to estimate propagation distance, we assume here the cosmic electrons to lose energy as expected through calorimeter model, radio FIR correlation, which initially was started by Hall in the 1989. And they predict radio FIR slope of unity, but though it is not necessarily true as we know now, because there could be leaky box model and so on. that would not be exactly valid with our assumptions. And so what we did is basically to use different convolution sizes of the FIR maps of the same galaxy and then plot with respect to the radio, that is radio FIR correlation, but where the FIR has been converted with larger and larger size scales till we get a B of 1. And this we are using both the 330 megahertz and 1 gigahertz, 1.4 gigahertz maps. And with that, we do the radio FIR correlation. So these are the results, which you typically would see that, which typical case is that the full width half maximum of these galaxies, that is the CRE propagation scale, are typically significantly larger at 90 centimeter as compared to 20 centimeter. And but though I'm not going into any details here, but though it tends to indicate we can't say for sure right now because there are many assumptions which is going into it. So, but it tends to suggest these results that they are not probably very consistent with the simplest model of diffusion. But again, that would depends on multiple the things, multiple parameters which we are assuming here. So I'll go to next slide now. Next, we come to measurement of magnetic field. So this is we use the minimum energy condition, but this is a modified minimum energy condition which was used by Brake and Krauss 2005 minimum energy with the formula, not the classical equipartition, but there is a modified equipartition which is given by this and was published by Brake and Krauss 2005. So this is one case of M51, which you can see the magnetic field shown in the color scale. So it is the strongest around 50 microgauss at the center and falls down to about equipartition magnetic field to about 15 microgauss or so, 10 to 15 microgauss at the galaxy edge of about 10 kTc. But this typical tendency is similar, so I'm not showing all the maps now. The time is short, and so this is one case. But typically, the magnetic field is strongest at the center, and it falls down by a factor of 2 to 3 as one approaches the galactic edges. But this is equipartition magnetic field. We now study the magnetic field and SFR coupling. So the magnetic field and SFR coupling as such, numerous studies show that gas turbulence amplifies the galactic magnetic field in short time scale. There are various references are there. So the semi-analytical model have shown that magnetic field and SFR surface density are coupled through B as sigma to the power 1/3. This global correlation is found in 20 spiral galaxies by Vanek, which has been published. Magnetic field and star formation rates are correlated also globally with power law index of 0.3 plus minus 0.04, as was expected already for 12 local group dwarf galaxies. Studies of a sample of Magellanic type galaxies and dwarf galaxies reveals that coupling constant is 0.25 plus minus 0.02. Local galactic magnetic field has also been studied in IC10, and which is correlation has been published by Basu et al. 2017. But spatial correlation is not studied yet for almost all the spiral galaxies as we know now. So these are the correlations which we find. So it shows a typical slope of about 0.3. You can see that these are all very close to 0.3, like 2683.3 plus minus 0.03, 3627.37 plus minus 0.02, and so on. So it typically then comes 40964449. So this correlation seems to be pretty tight. The mean value of this power law index is 0.3 plus minus 0.02 and support the semi-analytical model of Selkard and Beck, which they expected this. Our result is also in good agreement with the expectation of star formation given application magnetic field, which would basically cause this. We now come to magnetic field and gas energy coupling. So the magnetic field and turbulent gas energy densities are expected to be coupled. This was shown long back in 1950s by Chandrasekhar and so on, was expected through equipartition of magnetic field and gas energy density. So that goes as B is expected to go as root rho, where rho is the gas energy and the gas the density. So the mean ratio in our cases only CO maps could be found for only 3 galaxies, where the most of the gas energy density comes to turbulence, and that could be studied for 3 galaxies 5194, 3627, and 4826, and their mean ratio, that is the gas density and magnetic energy density, are roughly consistent with 1.64, 1.75, and 0.73. Mean ratio in the arm in the interim region at about 1.3 and 3.0. So in the arm regions, they certainly seems to be valid given the assumptions and so on. They're roughly consistent of the order of 1, I would say, of the order of 1 or so, But in the interim region, it can change. It need not be the same, meaning it does seem to be that interim region, the magnetic field could dominate magnetic field energy density compared to, there is some indication of it, I would say, at the moment, because there are various assumptions which has gone into it. So
Subhash, you have about 2 minutes to
talk? Right. So I'm also going to finish soon. So now I will come to that. Well, having described all this, we know this show in short the motivation for UGMRT observations, because we expect the RMS sensitivity to improve by factor of 2 to 3. On the scale, we will do better than UGMRT at 330 megahertz. So we have observed another 24 galaxies, about 120 hours of observation with GMRT using 300 to 500 megahertz observations. Though we have not done any significant science with them yet, but images of some of them are already being made. So this is one such case of 4096, which I have shown before, which was done with GMRT, which gave us about, I think, a factor of 3 higher noise. Here we got about 18 microgen scale. So about 58 versus 22, okay, 20, 50, 22 here I'm writing because the RMS noise is very close here estimated to the galaxy, not in general of the field. So you can see that about 2.5 times improvement for the same galaxy between legacy GMRT and UGMRT. This is another case of 4631. This is an Aegean galaxy with massive radio halo, and you can see the halo is pretty well caught at 330 megahertz. And you can see a comparison of EVLA image, which is by Irwin et al. This is L-band over optical, and you can clearly see, given the coordinates, if you see that it goes about up to about 35, whereas here it crosses 35, goes to about 36 or so, the top part, if you see. So the more extended emission at 330 has been detected as for this galaxy at least, compared to what has been seen with EVLA or JVLA rather at L-band or 1.4 gigahertz. This is another case of NGC 0628, which has also been seen. A 24 micron is shown in color, whereas in contour we are showing the radio emission, and you can see the radio emission is seen all the way, though not at the very faintest part, but this is tracing the arms pretty well, and even outside the arms we can see, but not at the edge. So the FI are still slightly more sensitive. Here we got, of course, not very high, but about 50 microgens RMS per beam. So with that, I will basically finish. This is the summary. So we have made spatial resolve maps of 7 galaxies at 330 megahertz. Using them, we started the northern spectral index between 0.33 and 1.4 gigahertz, and they tend to steepen from galaxy center towards the edge. Slope of radio FR correlation using 90 centimeter data tend to be more flatter than 20 centimeter. Propagation cells of series at 330 megahertz is of the order of several kpcs and is typically significantly larger than that at 1.4 gigahertz. Simple diffusion do not appear to explain these ratios. Magnetic field is strongest in the central region, goes to a factor of 2. Total magnetic field strength, the star formation rates are correlated strongly with average coupling of 0.3 plus minus 0.02. Magnetic and turbulent gas energy density are in equipartition. Small scale turbulent driven amplification of magnetic field is supported by strong coupling. So further analysis of 24 more galaxies observed with UGMRT and all. So with this, I will basically finish.
Thanks, Subhashish. So there are questions. So I have one. Yeah, Mamta, go ahead. Yeah.
I was just wondering if you've seen any kind of change in the magnetic field properties with respect to redshift in these galaxies.
With redshift?
Yes.
Okay, these are all about 11 megaparsec, so we can't do, but yeah, that is an interesting question, meaning interesting thing to do for future, because such things may be useful, meaning and I know that people are thinking about it as part of various SK thing and so on. Yeah.
So I have one question. This radio FIR correlation, when you compare it with 90 centimeter versus 20 centimeter,
yeah.
How about the tightness of the correlation? Does that remain the same? Have you tested that?
What you see the slope of the correlation?
Not the slope of the correlation. See, slope of the correlation may change depending on at what frequency you are measuring. But I'm asking about whether the tightness of the correlation is different in 90 centimeter versus.
Yeah, so the scatter you can see here that I think the scatter you can see that the last two columns, that is that the rightmost two columns, I don't see they are very different. You know that they are very more or less the same. I don't see.
Sure. Does it essentially mean that it's, in terms of modeling or understanding, moving from L band to 90 centimeter does not have any special advantage?
No, the 90 centimeter, we do expect that the cosmic ray electrons to have propagated more further away from the source. So the correlation will go down. Now the scatter would depend on multiple parameters, So the scatter is one thing, of course, is the noise in the data, but leaving that aside, the noise would essentially also could come if you have, because this is all the data, all the pixels from the same galaxy. Now suppose there is a radial dependence of the radio FIR slope, depends on the position or the galactocentric position of the pixel, then it could change. But probably that we are not seeing here. We are not picking up anything, any such thing here. So
Okay.
I would say we are not picking it up, but we can't rule out. Yeah.
Okay. Is there any other question? Okay, I don't see any other questions. So that's sort of the end of this session. So I will hand it over to Mamta if there is anything you want to say. Is there any announcement or something?
Yes, thank you very much, Nirupam, for keeping everyone on time. And thank you very much to all the speakers for their excellent talks, and especially Subhashish and Samuel, because their talk has been shifted at the very end and they were with us for all time now. So we don't have many many announcements to do, just a quick thing that I wanted to share with everybody. So I'll just share my screen. But we are meeting anyway tomorrow. Tomorrow is the last session. So remember, we are going to have the physical meeting, at least we can hope for end of this year. Besides that, we had this great, excellent talk. So we finally managed to have two distinguished note speakers today. So that's the book which all we have read in radio astronomy and the photos that we have seen. And today we heard the lady. So it was great and everyone was there. We have the group photo, which is already on the website. We have this exchange program between France and India. So Samuel has been showing a lot of interesting work which can be done. So use the opportunity and try to apply for them. And finally, whatever we are doing is kind of being followed by people on Twitter, including CEFIPRA. So we have some appreciation coming from the CNRS, from the Director of Research and Cooperation International of the CNRS, and from the SK Observatory as well as IAU. So I think it's a contribution of everyone's, I think, yeah, it is a team spirit and a contribution of everyone to the best what they could do, which is making it all nice. So that's where I would like to stop today. And thank you, everyone. And let's meet tomorrow.
Yeah, thank you. And the photo has come out very well, the group photo.
Yes, yes.
Nicely arranged. Thanks.
Bye, everyone.
Bye-bye.
Okay, thank you. Bye-bye.